Professor Sudhir, are you there? Good morning.
Good morning. Yes, I'm here.
Okay, very good.
Should I start?
Yeah. So I think it's
Two more minutes. One more
yeah,
minute.
I think 2 more minutes because my computer person is going to. He has to walk to upstairs. So I think those 2 minutes will be enough for us to make the things ready. Sorry, we have a COVID patient here in the guest house in the hostel as a PhD student. So we have sort of decided to not to sit here in this room for the local participants. So they are participating through Zoom only from their respective rooms. Yeah, so good morning all. I welcome you all here on third day of this workshop dedicated for X-ray binaries and microquasars. And I hand over the session now to the session chair, Professor Sudeep Bhattacharya, to start with. Professor Sudeep.
Good morning. Welcome to the third day of the conference on astrophysical jets. Today will be the session on X-ray binaries, and the first talk will be by Professor Ranjib Mishra on X-ray binaries. It will be a 50 minutes talk plus 10 minutes question and answer. I'll give a warning before 5 minutes. That is at 45 minutes. Ranjib.
Thank you, Sudeep. I hope I can be audible properly.
Yes.
Good morning. Thanks, Sudeep. Good morning to all. And I'm Ranjib Mishra. I'm from Mayuka. And for those of you who know me, you will realize that this is very early in the morning for me. But so if I'm incoherent, please, you will know that I need to be excused. As a member of SOCIM, first let me certain that we had plans to have this review talk to be given by some people. I mean, especially Professor Rao, but unfortunately he could not give it, and I'm last minute substitute for this. And this has made me most uncomfortable, and I had to try to find out how I can do this. Well, the reason being is that X-ray, I mean, when you give a review is a very difficult thing to do. You can give a review easily if you know a lot of things, and then it's quite an easy one. Or the other alternative is if you work very hard, you read a lot of papers, a lot of work, try to figure out what's all happened, and then do this. Well, I do not know a lot of things, and also I do not have a tendency to work very hard, so I was in a fix to do this. The other alternative is to just talk about a very specific topic which you think you know, or which I think I would know, and then give a review on that. But I thought that I will use a fourth technique, and I will going to to present is I'm going to give a very broad review with an Indian perspective. A very broad review means that I'm not going to talk about any specific results. I'm going to touch on a lot of topics and see why they're important for the subject. And I will keep the Indian perspective in mind when I'm talking about. And also, on the onset, let me give my apologies for the absence of references. Putting a lot of references would have been difficult at this stage for me. And of course, although I'm going to give a possible broad review of this very large big topic called X-ray binaries in general, there are obviously going to be several possible omissions, and I hope that we will discuss them later as we go along in this meeting, especially today. In the so this is the image I'm going to start with, and I'm going to look at various aspects of this image and go through cells. First, I'm going to talk about the very large scale things. That is, what do we have here? We have here a regular star and a compact object, which could be either a black hole or neutron star, and such a system is called an X-ray binary, especially if matter flow from the normal star falls to the compact object. Now, the thing to notice here is that the, the first aspect of an X-ray binary is that there are two objects, a companion star and an black hole or neutron star, a compact object. And the reason why this whole field has improved is that we can do something called a dynamical mass measurement. Now, what you do is you just briefly to tell you what this is about is that you look at the optical emission from the regular star, you measure a line emission, and as the star moves around the compact object, the line will get Doppler shifted, and from there you can get to know the velocity and the orbital period of the orbit of the X-ray binary. This allows you from using simple Newton's law to get a dynamical mass measurement. And this has been, of course, the starting point of our thing because many of the dynamic mass measurements are important because they can distinguish between direct distinction between neutron stars and black holes. And in the early years, this was the main evidence for black holes in the system. I would like to just put in a perspective here that not many people in India are working on this now. This was done in the 30, 40 years ago. And over the years, even internationally, the number of X-ray binaries for which we have dynamical mass measurement has tapered off. Like we had about 20, 30 in the first before 2005, and now we have maybe added one or two more in the last 15, 20 years. I do not know the reason for this, but I think this is quite a thing because dynamical mass measurement is an important concept over it. Another important aspect of this is how did these two objects come about, and which is a topic of binary evolution, and and what it means is that how do you have a regular star and a compact object going around each other, and this has been worked out many years ago, 30, 40 years ago, and in various detailed topics. That is, you have two regular stars, and one of them goes through a supernova and leaves behind a compact object, and this is how they align and they perform. And like many other subjects, this is also I feel that there's not much enough work, especially in India, being done on this topic. And the reason for that is that it somehow people feel that this is a topic which has been already been solved and most things are done. But I think that there is a big aspect to this, that especially that since now we have LIGO events and we now have evidence for black hole mergers of different kind of black hole masses, uh, the connections between these events is going to be a very important one. Do these things which we see in LIGOs, did they ever go to an X-ray binary phase? What about these ultra luminous X-ray sources which are in other galaxies we see? And these are the kind of questions which are coming up and but are not being addressed. The second important thing, sorry, there is disturbance. Okay. The other important thing of this binary evolution is what is the spin of the compact object after it forms? Does it evolve? Whether the spin axis is in aligned with the orbital axis or not. And this is a very important thing because as we come later, we will realize that uh, whether the spin axis of the black hole is aligned to orbital axis has a lot of implications on how we understand timing properties of these systems, rapid timing properties of systems. And these are all things which we should be doing with the binary evolution, but uh, that's a subject which we are doing. I would like to just inform people that something very interesting has happened over recent years. That there's a Gaia, which is a satellite which is measuring parallax motions, and with this parallax movement, we can get very accurate distances to these X-ray binaries, something which we have not got that well before. And these gives us the accurate distance gives us very good luminosity of these sources. And since we have a physical concept called Edigman luminosity, and that comes in very importantly in our all our work on X-ray binaries, this is now a thing. What we have been doing as a community has been that for X-ray binaries, we have been doing orbital period evolution, especially for those objects through which going through eclipses. We can measure the eclipses very accurately, and then from there we can get a understanding of how the orbital evolve, and which is by itself is interesting. Now, two stars don't make an X-ray binary. The mass has to be transferred, and the two important ways mass is transferred is again wind accretion. That is, the stellar wind is captured by the compact object, or through a rho slope overflow, as shown in that program before. There's also another interesting way where the accretion occurs from the B stars disk. The disks of the stars put matter into the compact object, and that's the third way which can happen. And the primary questions about this, again, is something which we don't work too much about in India, is what are the detailed modeling by which we can get to know what is the mass accretion rate going in, and more importantly, what is the circularization radius? And circularization radius, by which I mean, is this, uh, sorry, is this radius, outer radius of the disk, which is formed, and that is quite important to figure out. And what is happening more applicable nowadays is that is the long-term variation of the mass accretion rate. How does it vary? Is it because of stellar variations of the compact object? Is it because of clumpy events? There have been simulations being undertaken in the interest of learning about how these clumpy events can give rise to accretion rate variations. But and how do the stellar variations, even small scale, small time, long terms, how do they vary? The important question going into the thing is the angular momentum distribution, that what kind of angular momentum uh, is falling into this transfer. Is it a very narrow angular momentum, that is all particles are coming in with the same angular momentum? Is there a disparate range? Are there very wide ranges on this? This is also a question because that reflects on the boundary conditions we use later to model the systems. This study would have also have implications of why we have so many different kinds of X-ray binary systems, even when we know they have the same black hole mass, same systems, but we get a very large variety of resources. Is there a connection between how this wind accretion takes place, how this mass accretion, what is a binary period, and with the thing, especially is there a connection with abundance, and that is something which you have to come to. So these are the important questions for that one. Now, leaving aside the binary, now let me come closer towards the object and come to the outer edge of the disk. And what happens is, as soon as matter falls in, it forms something like a hot spot, and then it starts circulating all over the matter. And this is still giving out optical emission. And this hot spot and warp disk give rise to optical variations, and which are different than the orbital period. And it's important to realize that to understand the dynamics of the system using this kind of analysis of what kind of orbital period is, what kind of a variation in this optical is seen in the ring. But the more important part of this starting region or outer disk is something called a hydrogen ionization thermal instability, which I will just talk about real briefly. And that is that what we observe is many sources go through long transients. Like this, some of these X-ray binaries are quiet for 10 years, nothing happens. There's no X-ray emission, and suddenly, suddenly means in a time scale of days or months, it will start increasing, and this activity stays for about 6 months to a year, and then again the system goes to quiescent. That's called X-ray nova. And over it's now known for the last 20 years that one of the most prominent ways of doing this is something called a hydrogen ionization instability. That is, the outer part of the disk, the hydrogen is not ionized, and as the matter flows in and gets heated, a part of it gets ionized, and this causes a kind of instability, and this instability is the cause of all this bursts, which we long-term variation which we see in the whole thing. Uh, this is a very well-known kind of development, because it was already been developed for CVs, and so we know that this kind of instability works. And while there were a lot of research done earlier on this topic, uh, over the last 15 years, 10, 15 years, again, this has not become very important because people think that the problem has been solved. But in reality, it's not. A lot of questions still remain. Any of these models would give periodic outbursts. We don't get periodic outbursts. Why are the irregular bursts is something which we don't know. What are the effect of irradiation of the X-ray binaries on the outer disk to do this? How does composition matter? These are questions which are fairly unknown, and we have to, and people have, we need to work on this to get the ring. And perhaps the most important thing is that and this is considered to be the most important uh, confirmation of the standard disk theory that we have, that the standard disk theory predicts that hydrogen is thermal instability, and this is the exact one which we see in the thing. So it is a way to measure how well we understand the theoretical works of these objects. So uh, 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 there is a lot of scope to be working on this, but I do not think that many people in India are working on this. The other important reason why we should be started, that now we have much more data about how these X-ray transients have behaved. Like for example, for a source like GS339 and 4, we have now some 7 or 8 such outbursts been done. So we can now look at the profiles and start testing these models more effectively, and this may give us insight into much of the nature of accretion disk theory and the other models there. So that is an important part. So now, if we leave the outermost part of the disk, and move further in, there is a region in between the innermost part of the disk and the outer one pass, which I would call the uh, unseen uh, middle region. Now, because here we expect emission to be in far ultraviolet wavebands, and because of absorptions around them mostly is unseen, and this is inferred and not directly observed. However, this is perhaps also an important part of the X-ray binary disk, because it determines the variability of system as we go in. So, on long-term variability of system is determined by this region. That is, in time scales of days and hours, how does the system vary will be determined by this region. Or perhaps a more important one is that it is it is gives rise to a boundary condition that determines what happens inside. Now, here let me make some uh, interesting points about boundary conditions. We have uh, in in a physical system like this, that where you claim to know all the physics behind it. If you give the boundary condition at some outer points and you know what happening, in principle, you should know what will happen when as the matter flows inside. Now, interestingly, there are debates on this. Some school of people believe that yes, it is the boundary condition which determines exactly how the flow happens inside, and there is another school of belief which says that the boundary conditions are important but not the sole driver of this behavior of matter as it falls under, and that is because of non-linearity in the systems, which can give rise to limit cycles and other kind of behavior which are not related to the boundary condition. And this is an interesting debate which will carry on for a little while, as to understand our understanding of how the system behave, but in the middle. Now we'll come to the more interesting part as we zoom in further and we come to the near the compact object, where all the action happens, and the reason why these objects are called X-ray binaries. Of course, the cropping of the picture which I'm making is that of a painting. We don't really know what is happening so close in there. I wish we had such wonderful pictures out there, but we do not have that kind of thing. So here's a crude diagram, which I always show to show what is our actually understanding of what happens there. And what we know is that you have a standard Shakurasanav cold disk, which is called a standard accretion disk, and that is comes close to the compact object, and then a lot of strange thing happens whereas this matter falls under a compact object. That is, and this is the kind of a broad picture we have. Then there's some kind of a hot disk, a jet, and a cold disk. But now I would like to revert that there is will make important distinctions between. Now it'll become important to realize what kind of a compact object is, whether it's a neutron star or a black hole, and especially if the neutron star is a magnetized one. And here is another my apologies for this very crude diagram for what happens when the neutron star is highly magnetized, and that is when this is you have a strong magnetic field. Let us say it's not the shape is not a dipole, but it could be it is more realistic that it was a distorted. But you have a this line is supposed to be a magnetic field. Now the accretion disk is stopped by the strong magnetic field, and once it's stopped by strong magnet, the matter flows along the magnetic field lines, goes to the polar caps here, and from the polar caps, radiation happens. And because the neutron star is spinning, we see an X-ray pulsation, and this is called an X-ray pulsar. And in India, we are very strong in understanding of X-ray pulsars. And let me go through some of the ideas which have been coming out. First thing is that since you measure an X-ray pulse and we can measure this very accurately, we can measure the derivatives of the pulse. That is, what is the rate of period change of the pulse period very accurately. And this has, I'll come to how what is important in this. But before that, because there is a magnetic field involved, we can measure the cyclotron absorption lines from there. That is, as the emission comes to the cyclotron line, the magnetic field will absorb the thing to the cyclotron process, to the cyclotron absorption process. And this is fairly and very complicated process, especially since magnetic field could be so strong that there are Landau levels. That is, the cyclotron emission absorption lines are quantized, and uh, so and because of the geometry of the system, the way we see these absorption lines are going to be different depending on our viewing angles. So people have to make out models for time averaged cyclotron emission line, and then uh, depending on the way we are watching, that is the phase of the neutron star, that will give us a different measures of thing. So modeling of cyclotron lines and phases world is a very complex thing, and we have been doing in the community. There have been a lot of activity happening on this topic. There is also a lot of activity going on into magnetic dynamic flow onto the polar caps. Now, this is surprisingly and slightly easier way to do than for others. That is, you have a strong magnetic field and matter falls into it. How does the matter interact with the magnetic field? Does it twist it, change it? How does the magnetic field interact with the matter? And that is something which have been extensively studied. Excuse me. So X-ray pulsars are integral part of thing. They involve a lot of physics, and they tell us a lot about thing. The measuring the period derivatives, how the star is spinning down or spinning up, tells a lot about the system that we are trying to understand and evolve. We seem to be there's also but still there a lot of work to be done in that we can measure the pulse profile, but what about the rest of the X-ray? There is also a non-pulse profile on the broadband continuum, and the broad the broad, I mean, even a pulse profile is a broadband continuum apart from the cyclotron line. And where does this broadband continuum come? There's a lot of issues regarding that, and we have to work out a relative process very carefully to understand this kind of system. There is magnetic field evolution, which has been studied, but it is still a very hot debated subject. And modeling the period derivatives as the system spins up and spins down is, so there's a lot of interesting physics and thankfully a lot of available data to do this kind of study. Several neutron stars don't have a large magnetic field, and when they don't, the matter doesn't get stopped and instead goes into a neutron star. The difference between having a neutron star and a black hole is that since the neutron star has a surface, there is another component coming in called a boundary layer, and this boundary layer gives out a lot of radiation, and it gives out radiation, and it can be observed. There's another very important distinguishing factor of a weakly magnetized neutron star compared to a black hole, and that is of a thermonuclear burst. Now, what happens is, as matter falls in, the hydrogen accumulates on the surface of the neutron star. Or actually, it can go all over the surface of the neutron star, and at one point, the hydrogen ignites to form nuclear fusion, and you see a good thermonuclear burst, which lasts for 2-3 seconds. So these are characteristic things which we see, a thermonuclear burst, which we see in for coming from the surface of neutron stars. And uh, what is the most important things out here is to find the occurrence. How often do these bursts occur? What is the frequency of burst? How does it depend upon the accretion rate and the composition of matters going in? I'm happy to say that there are and were a lot of people, a lot of work who has been done on this field. The other great good advantage of these bursts is that they can be modeled as a blackbody emission, and since they can be measured blackbody, you can measure the radius of the star. And but the only problem here is that you have also the, apart from the uh, thermonuclear explosion emission, you also have emission for what was happening to do the accretion and other processes. So you have to remove that the two components to get a good idea of the radius. But if you do get a good idea of the radius, you are going to get close to an important parameter of our understanding of neutron stars, that is uh, the mass radius relationship. And if we know the mass for neutron star and radius of of a neutron star, we can constrain the equation of states. And in fact, this is the most promising method to constrain equations of state, as I've mentioned in here. Uh, the another complication hack occurs is that these as the explosion occurs, the surface moves up a little bit, up and down, and so there is a photospheric expansion of the surface, and that has to be modeled in as a something. So there's absolutely interesting and straightforward physics, but a lot of work has to be done to get that thing out. A very interesting aspect of this burst is that initially the burst is uneven, so you can form a spot in the system where a spot in the neutron star system which is spinning with the neutron star, and this leads to something called a burst oscillation. That is, initially the burst lasts for 2-3 seconds, and in the first 1 second you can see a very high pulse at the frequency of the rate at which neutron star is spinning at maybe 2-3 times a millisecond, and we can see this oscillation, and that gives us a way of finding the spin of neutron star, which is not possible elsewhere. So this is a very important field, and there've been a lot of work in India going on this. In, uh, this is a very encouraging and aspecting field. Now, now I'm going to a more broader topic here now about which I will consider both for all these objects, is that what we do is we generally look at the X-ray spectrum from these sources, and this X-ray spectrum, the first thing we do is we try to characterize the X-ray spectrum in terms of what are the spectral components of the system. For example, you'll have a disk emission, you could have some kind of a hot disk emission, and some reflection, which I'll come to talk about. So the first idea is you get a spectrum, you have to find the different components, and from that components we get vital information about how the system varies or not. So let's go through some of the spectral components here. The most standard spectrum component is the standard cold accretion disk. Now this is more than 50 years old now, and what it says is that the disk would be consisting of a blackberry emission, but it's not uniform. The temperature varies along the radius, and because the temperature varies along the radius, you get a particular multi-temperature or multicolored disk spectrum, and this has been observed and we've noted. And as I said, this has been done for 50 years. However, the real big changes which has happened now is that uh, this kind of spectral modeling has been greatly advanced over the last many years. Uh, we now can incorporate generalistic corrections, including the boundary conditions, and get the actual spectrum expected in generality out, which means that we can use this kind of a technique to measure the mass of the black hole, where the disk has been truncated, and also get to know the spin of the black hole, because the spin will distort the spectrum of this standard cold disk. So, but what this is not as easy as it sounds. It's not just the addition of GR into the whole thing. Uh, what is perhaps more important and not been done extensively is that you have to. This is like a disk, and so it has an atmosphere, just like a stellar atmosphere, and you have to do the radiative transfer corrections to make sure that you're doing the whole spectrum correctly. And while there have been some attempts internationally to do this, uh, generally speaking, we have not been able to. We just add something called a color factor to the disk, and that could be a hampering part of it. But this is a very hot, ongoing field. It's a theoretically driven motivation and motivated field where people are simulating and finding more and more sophisticated codes to do this properly. The second important part of the thing is what we believe is that most of the high energy photon comes from a process called thermal comptonation, where the uh, disk emission, let me go back to this one, where the disk emission from the cold disk emission goes into some kind of a hot region or corona, and these photons get scattered, and you get a high energy X-ray emission from this coronal shape. For thermal compilation, we again have had analytical approximation schemes available from last 30, 40 years, and these schemes have been being improved over times, because first of all, these I would like to emphasize that all schemes here are approximate analytical. Approximate. That is, to do a full-fledged combination, thermal combination, you have to do a full Monte Carlo simulation. And if you do a full Monte Carlo simulation, you cannot fit, and you cannot use that to fit spectrum, because that's uh, computationally too expensive in time. So all of them have approximations to do it, but the level of approximations in these codes and how they implement it are different. And as the for certain cases, we have to start incorporating different, more sophisticated ones. There is uh, now a growing need, and which has been done before, that we have to include non-thermal electrons in this plasma, and that causes a more complexity, and this is a kind of challenging for the uh, theoretical modeling to find a spectrum. You can find a spectrum. It's a question to find a spectrum quick enough so that you can actually go and fit data with it and find errors on the spectrum and all. So the speed of computation is a major element out here. The other element which is going to interesting here is that you need uh, all these things assume that the temperature of this corona is a constant, and there are theoretical arguments to say that why this should be so. But observationally, there are a lot of evidence which saying that this may not be true, and we're not sure. To confirm that, we would, whether it's true or not, that's not important. What is important is to confirm that we would need kind of spectral models where there is a temperature gradient in this kind of a hot flow. How do you incorporate that? We don't know. I mean, which is extremely difficult to do without a Monte Carlo simulation. And as I said, a Monte Carlo simulation is too expensive to spectral filter. In fact, even just for a Monte Carlo simulation to check, sorry, what are the differences for having multi temperatures, things inside a corona, is going to be an interesting and important challenge in the whole thing. However, none of these two things, I mean, the most important and what has captured the imagination of all these people, of all the community in is that of the reflection component. Let me just go back and explain what happens. uh, you have a cold disk, some photons go in, scatter and give you a hard X-ray signal, but some of these high energy X-rays can come back and hit the cold disk and reflect back, and that is called a reflection spectrum. Now reflection spectrum gives you a iron line emission from the disk, and it gives you a reflection bump at some high energies. Um, The main concept of this is that uh, because the disk is so close to the black hole or neutron star, general relativity corrections are important and can be measured fairly accurately in these kind of things. And this has been done extensively. There's a lot of work which has been done to model these spectrums correctly. Uh, it requires knowledge of general relativity, including light bending and how does light in the light bending in curve metric, that is a spinning black hole metric. It's a lot of, but to that general relativistic theories, you have to add the idea that of the ionization state of the disk, that is requires atomic physics that depending on what kind of radiation falling, which of the how ionized is atom, how ionized is, let's say, iron. But to get to know how ionized iron is, you should know how other elements which are also present in disk are ionized. So this is a very complex field, and people have been making headways on this. And the reason is that it is believed, and I think it is true, that this is one of the most promising ways by which we can not only measure the generalistic effects near a black hole, but we can also test generality. In fact, a lot of models have already started incorporating non standard curve metric models to see what happens in the, so this modeling of fishing of sandbank gives information regarding spin and mass of black holes, as well as the truncation radius. In India, in our community, we have been very good, and there've been a lot of very good in incorporating these different spectral components. People have been using the spectral components on fitting the data and interpreting the parameter results. This has been a very, in fact, as I'll come later, we are very strong in this kind of a field. However, I must reflect, which I'll come back again to this topic perhaps, that there's not much activity going on in developing these spectral codes at the level of sophistications which is required in an international state of art. And this is a slight worrisome factor, and we'll have to perhaps do a little bit of catch up on that one. Right. Uh, but spectral modeling is not the only thing. What we need to do is we want to understand how the flow happens. So what is done is you have a hydrodynamic flow. That is, you solve the equations of how the matter will should behave as it goes near the black hole, and the spectral components which we have got from fitting the spectrum gives us a kind of input into what kind of a system we are expected to see from this thing. So let me come to the second one. Like, see, uh, there are many ways by which you can hydrodynamically model the inner flow. For example, the two component accretion flow TCAF is very popular in India, and a lot of people use it. There are this kind of hydrodynamic understanding has enhanced our understanding of how this system should behave and what is the flow. In fact, it gives us a geometry and a kind of a paradigm to for which we can go ahead. There are arguments and counter arguments of which of these models are correct or not. But however, what has been I think more important and more recently is that there are issues regarding boundary conditions and turbulent viscosity which we don't understand, and these issues have to be resolved in some manner before we can uh, take these things to more. But perhaps the more important problem with all this model is the fact that uh, taking into account the magnetic field. It has been completely increasingly understood that magnetic fields are becoming minor to 100 mm. Inclusion of magnetic field in your 100 mm is perhaps very, very important. And a large amount of effort has been now put in, a huge amount, to do minor to hydrodynamic simulation codes are being developed in this. Now, these simulation codes which have been developed in SRA, they're following two different branches, as I think, and I would like to illustrate how these two branches are going. One is that these codes are becoming more and more sophisticated about what are the kind of physics they incorporate. Some of them have been now being able to incorporate geometric effect, such as the lens changing position and body Peters effect. Let me explain what these things are. The lens changing position happens because when you have a spinning black hole, it turns the space time around it, and therefore, if you have a disk, it will precess just like Mercury precess. It'll not like it has the plane of the disk will precess because the black hole is spinning and it has a particular orbit, and that will cause a precession of the. This lens sharing precision can be now simulated in this generalistic models, where they go in and they see that the whole a part of disk is actually precessing around, and then they try and compare it with observation, which I will come to out. They can also do something like the Bodin Peterson effect. That is, suppose you have a black hole whose spin axis is completely different than the axis in which matter is falling into it. Then, because this is a completely generalistic effect, that because space-time is curved around it and space-time is turned around by the curve metric, the matter falling in will align itself along to the black hole and drop in. This aligning is called a Barton-Peterson effect, and this has can also been actually been seen in simulations recently, which is quite amazing that what we do. However, this is just one direction. The primary goal of magnetic hydrodynamics is to solve this necessary problem of viscosity. Accretion disk should not have viscosity. There is no reason for them to have it. There is no reason for them. We believe that this viscosity comes from turbulence. But what is the origin of turbulence? Because rotating objects are very stable. They should not be that turbulent at all. They should not be turbulent at all. And one of the things which was initially proposed by Chandrasekhar long back is that these systems are turbulent because of magnetic rotational instability or MRI. And a long-standing problem has been to solve this in the simulation and show. So the present day simulation can actually resolve this MRI instability, which requires very high dynamic range of your simulations, and they can actually see that how this turbulence is giving out and how the viscosity is happening, and therefore they can understand this flow much better. However, there's still controversies running around that if you go to higher and more precision, will your results still hold or will they change? So that is still a thing, but it's something which has been growing in the last 5-10 years, and it has become extremely complex work, and we don't have much people. I mean, we some is a direction which we need to move in and to see if we can contribute in this exciting field. Now, let me come to timing properties. X-ray binaries are very variable in rapid time scales from second to milliseconds. So the way why is this important? What we do is we look at an X-ray binary and we try to characterize the variability of these sources, and that is by doing a Fourier transform and then finding a power spectrum. And from this power spectrum, we can get to know characteristic frequencies of the system. It's like putting a stethoscope and hearing the importance of listening to the beats of the system. And these frequencies, what we know, are known as quasi-periodic oscillation, QPOs for general, and they can also be characterized by breaks in a continuum. Now, this is extremely important because these frequencies definitely correspond to some characteristic timescales of the system, and these characteristic timescale system must be affected by generality. So the moment we identify these systems to the actual characteristic timescales, we will be able to identify the generalistic nature of these systems. So the way it has been happening over time is that we have been correlating between uh, different observed frequencies to see if we can figure out which is the generalistic effect. But more recently, we are getting better in this, and we are trying to correlate the observed frequency with spectral parameters, such as the energy photon index. But perhaps more importantly, is that what is the where you can correlate the frequency with the radius, the truncated radius of the standard disk, and because that gives a scale of the problem, and with that we can be probably be trying to identify the which frequency corresponds to uh, the relativity part of it. I mean, which generalistic frequency do these QPOs correspond to? And mind you, there are a large number of QPOs and activities in this whole thing. Then there is this whole thing about this energy dependent. So now this kind of a thing has been done for last 30 years using an instrument called RXT, and not the last one, but correlation between we have been observing them for long. But what we can do now with these new instruments, including AstroSat and other ones, is we can look at these timing properties in different as a function of energy, and that is going to be an I think a game changer in this field. Now, what it means, we can check how does a variation, what is the amplitude of this variation, how does it vary as a function of energy. We can also know, and amazingly we can find that out, that if there is a time difference between the arrival of the photons coming from at different energy bands, and from this we can do these with these two information we should be able to find out what is the radiative process which is happening in the system. There are a couple of important steps, which important methods which people use. One is what is called frequency dependent spectral analysis. I wouldn't go into details of that because I don't think I'll have time for that. But uh, this is that at every Fourier frequency you start trying to do a spectrum. This has a lot. This has been tried out in various times, but it has an assumption of no energy dependence, time lags, and all. But this is kind of a thing has been going. The other is phase resolve spectroscopy. That is what we do in pulsars. This is what we traditionally do in pulsars is that at every phase, as the object is as the oscillation is going on, at every phase of the spectrum, we try to measure spectrum. This is difficult because many of these oscillations are not coherent. They are quasi-periodic, so phases of spectroscopy is difficult. However, the general theme for why we are doing all this is that now we are in a position to say that we have made, you go and fit your spectrum, you have understood your spectral components, you have understood that there is an standard accretion disk, there is an inner flow with certain temperatures and all. Then
You have 5 minutes.
sure. So then you see that you have a lot of variation uh, in the light curve. You can connect the two very easily, and you connect it to, and you need some models to say how you can connect to, and this tells you which of these components or how is these components are varying in time. That is an going to be an important part of it. In the last 5 minutes, as Philippe says, I come to the main theme of the paper, that's the jets. Now, the jets are pretty easy to talk about because we don't know anything about them. So, so what I'm going to do is I'm going to talk about jets not in jets context, but in the connection of three things here, which is the. I'm sorry. Let me move this way. It's called state transitions and states, transitions and jets. Let me combine. So when you see an X-ray binary, you see a large variety of states based on spectral and time. So this what happens is, suppose in this typical X-ray nova, the source will go into will evolve over 1 year. It'll over a few days it'll become bright and then it'll dim down. And as it becomes bright and as it dims down, it shows different kind of spectral states, different kinds of, and each of the spectral states is has different spectral and timing properties. I have never understood this because it's very complicated. Because there's some large number of they are called uh, soft state, hard state, or broad ones. Intermediate state, hard intermediate state, SIMS, banana states, atoll states, flaring branches. If you don't understand all these things, that means I'm mixing up states of neutron stars and black holes. But all these have different classification states, and this, but it's a very important thing. Science is first based on classification, so it is important for us to classify and then make an identification. We are broadly starting to understand of the accretion geometry behind why they have these synthesis, but in a very broad sense, not very. What we are less perhaps clear what is how did these states transitions? Is it a when you go from one state from a hard state to a soft state and a soft state to hard state, how frequently do you transition? Can we make some predictions of these transitions? And this is an important aspects of study which has been going on for last many 30, 40 years and all. The thing which I think is going to be different, which we can do and which have not been done before, is that we should look at the flux distribution of these states. That is, if I look at a certain state and ask how does the flux vary within the state, and what we find is sometimes they vary as a Gaussian, sometimes they vary in log normal distribution, and this has connection with a lot of AGN physics also. And there's a fundamental difference that the central limit theorem tells us that if I'm looking at an object and it's varying, the variation will, if I plot a distribution of any variation of this flux, it should be a Gaussian by a central limit. But we get different kind of distributions, and these different kind of distribution tells you when the central limit theorem is not valid and how these systems become uh, non-Gaussian or into specific sometimes the log normal distribution, and that gets back to non-linear behavior. That is, what kind of limit cycles are the limit cycles between the states, transitions, and jets and things like that. So that's a topic of detailed understanding of this system. Coming to jets, uh, we rarely see X-ray binaries which are pointing just towards us. So radio and infrared emissions are indicators of jets. They are so when we look at a radio flare, if it's steady, we call it a steady jet, and then if there are flares, we call it intermittent ejections. But what we now have done very well, and there's a lot of thing that we know that jet behavior is associated with state transitions. That means when there's an excessive flux variation or sometimes a quasi-periodic oscillation disappears and appears, then after a time delay, we can see the radio flare. So we know that the jet was started in those times when there was sun. This is a very prominent thing we have now established quite well. Uh, Theoretically, there's all kinds of question about jet discoupling, the ejection instrument, and what is called a Blandford-Zanzak process, which means that are these jets powered actually by the spin of the black hole, or are they powered by the accretion processes? A fundamental question which we do not understand or not. A new thing which is coming up and which I think is important is that rapid millisecond variability in the optical UV we can now observe from X-ray binaries. For this we need 10-meter class telescopes with very different kind of instruments, but this is not possible. And with this we can now correlate the X-ray variability with the optical UV rapid variability. Optical UV rapid variability was not possible before, but now we can do it. And this difference gives us a direct indicator of jet activities, because then the optical UV cannot come from out of our disk, it has to come from the inside of a jet element. And so that's uh, uh, the new thing which is happening out here. And one would expect that as we I would believe that timing properties of the jet and of the optical UV emission and X-rays will give us now much more better insight into the I come to the end, but I thought I'll put an epilogue. I've never understood why books have epilogue, but then I realized that epilogues are done uh, when authors have written a book and then they miss out the most important part. And this is what I've done. I made it, then I thought I completely missed out the most important part for this for Indian community, and that is of detection of X-ray polarization. In India, we are now being able to detect X-ray polarization thanks to CZTI and what Pollux, which will be launched next year, hopefully. And we really wow, have to now start understanding what does X-ray polarization for X-ray binaries do. We need theoretical understanding. Well, is polarization coming from jets and disk? And the most important thing is for X-ray binaries, it is known that polarization will will require good understanding of general relativity. There's a lot of theoretical catch up to be done which nobody knows about, because people like me completely ignored polarization because we never thought except polarization where we measured. So that is one. And there's one more topic which I think is also interesting, is that the gamma ray emissions from X-ray binaries. These are literally jet physics, interaction with stellar winds and all, and that is going to be the. I'm not nearly over, so I will not summarize, because if I summarize the talk, it'll take me as long as I gave the talk to. But what I'll leave is with my certain impressions, and which I'll try to finish quickly. And uh, I'll just read out because these are my impressions, and so they come with caveats. I think the Indian X-ray is fairly strong in X-ray data analysis. We do fantastically well in spectral and timing analysis. In fact, we have in world standards we are very very good. We also do magneto and hydrodynamical studies, analytical solutions. We have probably have the largest number of people doing analytical studies in the country, in the world. So we are doing very well in both these fields in this subject. However, we need to catch up with certain things. We need to catch up on the state of art MSG simulation. This I don't know, but I think I'm very worried that whether uh, we have the infrastructure and the knowledge and the know-how to catch up with this thing. We also need to produce and sustain a community to develop sophisticated radiative models. Like, as I told you, reflection components, we don't have good people to make the models for us, and also in thermal compilation and other models. Or even when we do, so for example, we have people doing thermonuclear burst modeling, which is good, and also when we are doing this cyclotron line absorption models, which are doing. But there's a certain concern here which I put in, and that is the sustainability of these things. It seems to depend on a PhD student getting up and moving off, and then whether we can develop a community on this basis is a thing. We need to push for more data-oriented theory, which is a summary of what the above statements are. That is, we need to start working more on data. And for the other challenges we are going to do is we have to meet up the challenges of multi-wavelength data analysis. We need to train people on not looking at only at X-ray and not only at optical, but doing detailed X-ray optical studies. Polarization, I'm very worried. Nobody has any much knowledge, and we need to develop a community in polarization quickly, very quickly. And finally, of course, we have to, because of something like Rosetta and so on, big data science is required. And we got a lot of space observatories which are functioning, X-ray space observatories, and we can use the other sites. But however, we still need Astrosat 2 and Astrosat 3, and that is going to be important. So I'll stop it here with my go back to my image. Thank you.
Thanks, Ranjiv. Time for a few questions. I see 3 questions in the chat box already. And the first question is by Abhay Karnataki. And the question is, up to how many Schwarzschild radii distance the GR effects are important? How much is approximate percentage difference if one is not accounting for GR effects in cold disk?
Yeah. So this is a good question. I'll answer your the first question is ambiguous because J effects for all happen. But if you ask about percentage changes of effects, that is, so it also depends on what kind of what are you trying to measure. Are you trying to measure the flux or the, but let me give you, not beating around the bush. Let me give you a rough idea on this. That around 5 or 10 Schwarzschild radius away, your effect is at 10%. So if you're getting closer than that, your effect will going to increase further. So if you are having measurements which are very accurate to 1 or 2%, you better even take GR effects into consideration when you are 20, 30 Schwarzschilds away. But if you are around 5 or 20, 30, 10, 15 Schwarzschilds away and your effect is okay. Hopefully, I answered that question by giving you a broad
I,
number.
uh, I think so. We'll go to the next question from the chat box by Biplab Sarkar.
Mhm.
What are the differences in observational characteristics that we can expect from a constant temperature hot corona versus a variable temperature hot corona?
By which diplo I would assume that what you mean by variable is in space. I mean, when the temperature is varying in space, yes, we can see. Let me take your example. If there are two temperatures, of course, you see two components, right? one from the lower energy temperature and one from the higher one. But if there's a gradient, you should see a more broader gradient spectrum. I think that. But if you by temperature variation, if you mean variability, of course, that depends on the amplitude of variability when you're looking at a time averaged spectrum. But I guess what you meant by variable was what was
So Ranjibai meant the radial variation.
clear. Right. So I'm saying just taking the two extreme things. You have two temperatures separate out, you'll get two spectrum components, very different. But that you can model out. But what about when there is a gradation? How does it model? We don't know. We should do a Monte Carlo simulation to check out how does it vary. How does the spectrum
Uh,
look like?
yeah, thank you, Ranji. Yeah.
Okay, we'll go to the next question in the chat box. That is by Suhas Chaudhary. Does thermal emission depend on the geometry of the accretion disk?
No, I mean the way you see the thermal emission will depend on the geometry of this. I mean, wait, I got to come. The thermal emission itself is the disk itself doesn't know which direction it is being moved. But the way you look at the disk will depend. The kind of spectrum you see will depend upon your angle which you have seen. That is true. Apart from the fact that there is something called limb darkening effect, which has now been taken into account in many of the models. That uh, there is a factor, of course. If you see a disk edge on, you should see nothing. If you see a disk face on, you will see something bright. There are relativistic effects on this which can change that, and also there's something called limb darkening, where because of relative transfer processes, you see different things when you see along the long line. In brief answer, yes, there is a lot of difference in angles.
So Pankaj Kushwa has raised hand. Pankaj, you can unmute and ask questions.
Can you hear me?
Yes, Pankaj.
Yeah, very nice talk. Okay, thanks. So I'm going to a question which is very different. I mean, it's okay. It's on the jet. So at least in binaries, we see at least observational. There is a clue that in some states or some state transition, we see jets, right?
Yes.
So, and one of the biggest problem has been that what is a mechanism which launch jet? Of course, there is a debate. Or rather, much more specific is what condition triggers the jet. So given that these are one of the best system compared to other where there is a persistent jet or something like that, what is the problem that we have not been able to, why we are not able to go much beyond our, what is your view on this one?
It's a very simple question. We don't know what a jet is. See,
Okay.
the basic problem is how is jet powered? You say that you go back to fundamental theory. You say you Danforth Zanzag process.
Yes. Okay.
Right. But what does it really do? Nobody knows. What is its actual prediction? We can't figure out. And it may not be correct because, as you know, young stellar objects have jets.
Yes, agree.
So that may not be the right way to. So we don't have a fundamental understanding of the theory of jets. That is causing the problem. The real problem is that we are not being able to identify the exact accretion process and correlation between accretion process and jets. We have got some uh, IR versus, jet power versus accretion power correlations, but in detail we need to know what is happening out there. Further, I think the biggest breakthrough will happen if any of our simulations we can actually produce a jet.
Yes, that I agree. So that is why I was asking your perspective from the observational point of view, rather.
From yes.
Okay, so let me phrase it more specifically in the sense like, okay, so in this HR diagram or state transition diagram, we have, there is a particular stage where we say that this is when the jet appears or this is when jet disappears and hardness and soft or something like that, which
Yes.
I'm not very much aware of, but as you say, it's too confusing with all those banana and jet all and blah, blah, states.
Yes.
So the thing is, now given that in these particular states, we observe the jets, have we, at least in the binaries community, have people looked at if there is some observable or some observable which looks different compared to other, which probably could give a clue whether this is what is different compared to when there is a jet and when there is not.
Oh yeah, there are plenty of. In fact, there'll be a lot of talks on that one. This is what I was saying, that we have got. We can now identify exactly what is the change in the disk, which leads to the jet. For example, we can check when a quasi-periodic oscillation disappears, does it jet? When there's a flux drop or high, does it jet? We can make this what you call it phenomenological connections very well. But theoretically, we have a little trouble.
Okay, little trouble or lot trouble, because as you say.
Lots
okay.
trouble.
All
Okay.
right, we do not have time for more questions. Let us thank Ranjiv. Ranjiv, you can unshare.
Yes.
And next talk will be by Professor Sandeep Chakraborty on jets, outflows, and spectral states of black hole binaries. The talk will be for 25 minutes and plus 5 minutes for question and answers. I'll give.
Hi, Professor Sudeep. It's S.B. Pandey here.
Yes.
There is some issue with Professor Sandeep Chakraborty. He is reinstalling the Zoom, and he has suggested us to continue the discussions with Ranjiv and other participants for 5 minutes. Meanwhile, we will make it ready. So, if it is convenient, then you please.
Do we go for next talk?
I think it's by Sandeep Chakraborty, but he has some issue with his Zoom. So
no, do we go to the next talk? Do we start the next talk by Moik Pahari if he is ready?
Moik Pahari, if he is available, then yes, why not?
Hi. Yes.
Yes,
can you hear me?
Are you ready?
Yes, I can start.
Okay, I'll announce you. So next talk will be by Dr. Moyuk Pahari on connecting X-ray variability and radio jets in microquasars on a detailed time scale. So it is a 15 minutes talk. So 12 minutes talk plus 3 minutes for question and answer. I'll give a warning 2 minutes before, that is at 10 minutes. Moyuk.
Okay.
You can share your talk.
J capital. Oh, J capital. J capital.
Just 1 second.
Not Gmail, Aries.
And perhaps this is a 15 minutes talk. If Professor Sandeep Chakraborty is ready after that, we'll have this half an hour talk. So tea break will be 15 minutes delayed. So Pankaj, you can.
Can you see my screen?
Yes. It's not full screen, I think.
Okay. Is it now full screen?
Yes.
Yes, somewhat. Yes, I'm not fully sure, but we can follow it. So you can start.
Okay. Okay. Hi everyone. Today I am Mayuk. I am now working at the IIT Hyderabad, and today I'm going to talk about some of my past work and which I have already done, and some of the works we have not able to finish. But I was more interested to have a view on X-ray variability and the radio jet connections, but on a more finite and more detailed timescales. Okay, so the first question is what I like to pose and start with the why these jet connections are important to study in the perspective of studying microquasars. So there are multiple reasons. I am just focusing on few of the reasons. For example, the multi-wavelength emissions. So far there are lots and lots of observations and data analysis have been done. Many papers have been published, but it has been well established that when you have a radio jet, strong radio emissions, then actually in the multi-wavelength, they have a strong and significant contribution to the broadband spectra. So one is shown in the left-hand panel this is by Mirabel, Dhawan and Rodriguez in 1998 using the GRS 1915 data. So the black one is the X-rays, the red one is the infrared, and the blue one is the radio. and this is within the time interval of an hour or so. But it does show that the X-ray, radio, and infrared variability, they are trying to follow each other on long time scale, and they have certain delays which are expected when they are derived from the jet. So now the question is, since we are observing all these multi-wavelength emissions in different bands, how do they impact on the spectra, observed spectra? So Sarah Markov in 2007, he first proposed a jet model to actually model the hard state spectra of a black hole binary. And then his model includes most of the emissions. These are coming from different parts of the jets, and they contribute in the different parts of the electromagnetic wave. So band, that means the entire ACD can be fitted with just the emissions, mostly the emissions from the jet, and slightly other partly from the emissions from the disk. So although this model have been criticized fairly, and then also there are some other evidences that in the low Hart state, when you have a jet dominated source, then you can actually have lots of components are visible in the spectra. So that means the jet actually have a very strong and significant contributions, irrespective of what kind of modeling and how we are doing modeling. It has an impact on the observed spectra and the variability. The second important reason is the harness intensity diagram study. So sometimes we actually associate the jet activities according as per the HID movement or the activity. So some of the, in the left hand panel, we show the harness intensity diagram of one black hole binary, the intensity in the y-axis and the hardness in the x-axis, and the colored dots, they are the radio intensity. So you can see that the radio intensity typically peaks around the hard intermediate state or during that part. But while in the other source, H1743-422, James Millard Jones, he also studied the same way, different spectral state and their relative radio intensity, which is shown in the right hand panel here. So the radio intensity peaks around the soft intermediate state, which is slightly ahead of the hard intermediate state. If you just compare these two diagrams, you can see the peak of the radio intensity comes later in the right hand side diagram, while the peak of the radio intensity comes before in the left hand diagram. So that means I mean, there are some efforts where we are trying to track the radio intensity of the radio activity throughout the HID diagram. But the question is that can we actually use that kind of information to trace the HID, or I mean, can it be reliable? So these are few examples that people have done already, but if you have more and more examples, then we can get better statistics. And also that is the transients we are talking about. Now here we are talking about the GRS 1915, which is a semi-persistent. In the left hand panel, the top panel is the X-ray and the bottom panel is the radio. So you can see when the X-rays are going up, radio almost flat, but during a dip in the X-rays, there is a strong radio ejections, which is called the plateau state, which is marked by the two superluminal radio jets. And this the same thing have been amplified here in the set. You can see there is a depressions in the X-ray flux while they are marked with the two radioluminosity jets. So that means the connections we are actually observing on long time scale, like in days or weeks time scale, they might not be hold true if we actually zoom in to even few days to minutes or hours time scale. So this is one very specific source, a particular source, but typically that the scenario we are holding for the black hole transient may not work universally unless and until we know the system, monitor the system really well. And also there is one important step, like there is a called radio X-ray radio fundamental plane frequencies. So where we can actually see the X-ray fluxes are plotted against the radio flux, and also the X-ray flux in the right hand side plotted against the infrared flux, and they show two parallel tracks. So what is the origin of these two parallel tracks are not well understood, but more importantly, even one black hole transient, they move from one track to another while going up in the high energy diagram and while coming back and the other way around. So that means that there is a kind of hysteresis. If you get lots of data points around the HID, you can find there is a hysteresis in the radio band. So, but the origin of such hysteresis is not really well understood, and we don't know like what exactly the things we need to do to important. So one major reason people have found later that basically we are having a cadence of like 1 day or 2 days or few days, which actually makes things worse in kind of making this kind of diagram. It's better to have a high resolutions in spatial and also in the temporal, like minutes to hours time scale, in order to improve or understand better this kind of fundamental plane correlation. And also Ranjit mentioned one, the Blandford BZ effect or BZ process, where the spin power can be extracted in the form of jet power, and people have tried to prove and disprove the both of the factors. So like in Steiner 2013, he took lots of spin observation measurements and then tried to move a jet power. So here the idea is like the jet power is the proxy of the flat spectrum radio synchrotron luminosity, while the spin angular momentum can be measured by different techniques, spectral measurement techniques, spin measurement techniques like broadband spectral modeling or the reflection spectral modeling. So there are two major works which have been shown here. One is Fender, who shows that even if you measure the spin using different techniques like Dix fitting or the reflection fitting, if you go from IR to radio, it doesn't matter. I mean, there is literally no correlation between these two quantities, while Steiner trying to see that, show that like there might have something in this direction. So there is a kind of ambiguity in establishing the relationship. So the main conclusion might be the simple assumptions that we are trying to interpolate between the jet power, theoretical jet power, and the proxy for the jet power might not work, or it might be that we are measuring very different radio flux or luminosity, which is not maybe the superluminal or the maximum radio jets, and should not be correlated with the spin. So there are lots of open questions regarding this kind of work, so that require understanding the Dix and jet connections, I mean, which are crucial to understanding the Dix jet connections. And also there are a few works by Nandi plus 2013. They have showed that they monitored different sources and their outburst, and they did a real nice study with the ASM radio flux and QPO frequency. So they're trying to understand the X-ray variability properties. How does it change with the radio jet and the X-ray variability, the outburst. So here is an interesting example, like in the middle panel, the radio flux density, which are very low at the beginning when the QPO frequency is really high, and while as it moves on, the radio flux increases while the QPO frequency goes down. So there is some kind of anti-correlation, which although the number of data points are not high, but it seems like that there is some kind of anti-correlation between the QPO frequency and the radio fluxes. And also they have shown the QPOs, position of the QPO during, before and after the radio fluxes. So these kind of works are actually very, very important in order to actually understand what is the long-term behavior of the connections between the X-ray variability and the jets. But the idea is like sometimes many of these kinds of works might be misleading, because the jet and the Dix connections may be very precise, maybe of the order of few hours to minutes time scale. So just interpolating between the days and the weeks might be giving a slightly wrong impression, I'd say. I mean, it might be inconclusive or incomplete for the understanding point of view. So here I started, motivated by his previous work, I work on some source called XTJ1550, which is a black hole transient. And on this panel, I plotted in the blue data the 0.8 gigahertz radio flux density as a function of time, and black data points are the QPOs. So you can see the QPO frequency increases, and it peaks at around sometimes which before the peak of the radio flux density. So the profile follows each other, radio flux density and QPO evolutions, but the QPO evolution is faster or earlier than the radio evolutions. So maybe if they are connected, I mean, this is just like a crude approximations, crude assumptions. If QPO frequency evolutions and jet ejections are connected, then something happens in the disk first, and then that actually propagates towards the giving the strong radio jets. Also, I can computed the time delay as a function of energy, where this 6 to 12 kV is the reference band. And you see there is a certain structure. First, there is a positive lag, so lag increases with energy, and there is a turnover at 6 kV, and then it goes back. While the fractional MS increases monotonically and then becomes a flat, which are very similar. But then I took these 3 data points, particularly 1, 2, and 3. 2 during the peak below, and 1 and 3 at the less, and the 2 at the higher frequencies. So this is 1 and this is 2. So when you are going to from 1 to 2, then there is a time lag become negative completely. There is no turnover and the fractional RMS keep on increasing. And then when I move to 3, then again there I saw a turnover at the similar energy which I saw in the first one. And then the fractional RMS remains same. So that means from going to 1 to 3, the fractional RMS and lag behavior changes and then it regains the similar pattern as it comes back from 2 to 3. So that means some of the X-ray variability properties might have been related to the change in the this jet formations or jet behavior. And also I tried to model the RXTPC and HXT, which is the broadband 3 to 150 kb, and with a simple model. What I found that using a disk and thermal combinations, and using that I found that basically the disk temperature, just like interpretation, the black point are always the QPO frequencies. The blue arrows are the peak position of the peak radio fluxes, and the red data points are the spectral parameters. So in the left hand panel we have disk temperature, which I multiplied by 5 for good comparisons. So you can see like the temperature and the compound amplification fractions, they don't have much relationship or change with the QPO frequency, so they are uncorrelated. While I try to plot the compound electron temperature and the seed proton luminosity, they seems to follow the QPO frequency evolution. So just remember the QPO frequency evolutions I took as a proxy for the radio jet evolutions, since they are similar but they are just like delayed some days, days 1 or 2. Okay. And then when I plot the optical depth and compound Y parameter from the spectral modeling, they seems to be qualitatively looks like a kind of anti-correlations with the QPO frequencies. Okay, so the idea is like the disk parameter seems to be uncorrelated with the change of the evolutions of the source QPO frequencies, while the compound then THCOM or what represents the thermal combinations seems to work well with the correlation or the anti-correlation with these QPO parameters. So that means so forget like what are the numbers represents, but there are some connections which actually represented by the earlier study that might be useful for the evolutions to study the X-ray properties, but on very minute or very fine time scale, so like every day or daily basis. So similar exercise I performed with GRS 1915. Here again the blue data are the radio fluxes and the black are QPO frequencies, and I took so they also follow each other. And then the QPO frequency I took the 3 data point, and these are the time lag as a function of energy, and that lag as a function of fractional RMS as a function of energy. And then 1 2 3, if I go from 1 2 to 3, then you can see it changes in a very different way. So during 1 the pattern is very different, 2 it becomes negative lag, and on 3 again it comes back to the become positive. So maybe the comparison of GRS 1915 and the previous transient may not be very useful, but the one point I want to make here, that the change in the QPO frequency and the change in the jet structure are very coherent with each other. But while the change in the timing properties like the lag or the fractional RMS, they might depend on what frequency QPOs you are using and what is the properties of the local properties of the accretion disk. So so here I try to plot the compound optical depth as a function of QPO frequencies, and there I also found this QPO frequency and the optical depth have a inverse the opposite relationship. Also the QPO frequency and the electron temperature looks like they are opposite or anti-correlated, while the compound flux fraction don't have. So here is a comparison between GRS 1915 and XTG 1550, where I have shown like the QPO frequency and the compound flux fraction, they seems to be anti-correlated in GRS 1915, but they seems do not have no correlations in case of XTG 1550 and 564. So this kind of comparisons might not be effective in interpreting the source behavior, but one thing is sure, that the jet and these properties, they actually follow each other, but the spectroscopy need to be, we have to be more careful, like how much the what spectral state or what are the components exist in that spectrum only. Now, all these works I have presented, they have been monitored the source in X-rays and radio on daily basis. Now, this, as I said, the jet connections or decoupling of the jet from the disk could happen in minutes to seconds time scales. Then we need to do some finite monitoring. For example, here also they are on the daily basis. This is another example, H17432. They continuously monitoring from May 28 to June 6 the ejections of the radio jets, and then they simultaneously monitoring with the RXT power spectra, where they found during the jet ejections they have a strong QPO, but after the jet decoupled from the source, I mean far away, there is a spectral state transitions from the towards the soft state. Okay, so basically, even if I don't talk about the states, it might be a transitions from the strong power load, strong QPO dominated state to the when there is no power exists. So I mean, they are trying to present the scenarios using a cartoon diagram, like when they have a decoupling, then there are not much activity left on the and the disk become getting cooler, and the time scale of the variability they become very longer. So all low frequency, high frequency time variability, they disappear with the decoupling of the jet. So these are, and there is one more example which is even more finite. So using the X-ray and the ultracam, which is the optical here, and the new star, which is the X-ray here, Poshak has done a great job while taking this one source V404 Cygni during its outburst in 29 and 19, and then they try to correlate the simultaneously studied part. So this is epoch 1, and you find no correlations between the X-ray and the optical, while there is a strong correlations. Also, this is also checked by different simulations. This correlation
You
is
have 5 minutes.
Okay, yeah. So you have so strong correlations between the epoch 2, and it shows a delay between the optical and the X-rays. And if we interpret the same in the in this particular diagram, so optical and X-rays, optical, so this delay corresponds to the delay between X-ray and optical, which is 0.1 seconds. And if you interpret in terms of Schwarzschild radius, this is typically 1000 Schwarzschild radius. So this is one kind of very finite, even more detailed time scale evolution is important to understand like what is going on close to the jet base or the close to the structure. So I also personally look at this source called Cygnus X3, which actually monitored very persistent and monitored very frequently. And one important aspect of this source actually repeats the behavior of the radio and the X-ray quite reliably. So once the X-ray goes down very close to the zero count, immediately after that there is a strong radio flare, and it also happens many times. There is no missing, I mean, all the time it is correlated. The major radio flare always preceded by the depression in the decreasement on the flux in the X-rays. So that means this source gives an opportunity to study the multi-wavelength and very finite minute time scale correlation between the X-rays and the radios. So this is one Chandra and the sub-millimeter structure of the area where actually the Cygnus X3 and the other small blobs have been observed, and which is also emitting X-rays. So this area is a bit complicated if we just look through the image in X-rays and the sub-millimeter. And then what we did, we took one observation using AstroSat and the Ratan telescope, and we continuously monitoring for few hours to days, 1 day actually, but continuous monitoring. And this is the light curve of many days, and the red vertical line, they actually represent the observation window which are joined between the Ratan and the AstroSat. And you can see during this window there is a sudden rise in the radio flux and also sudden rise in the X-ray fluxes. So this actually gives us an opportunity to study what happens during this window between the radio and X-rays. So when we study the X-rays and do the background subtraction, we found that the 20 to 60 kV, the hard X-ray flux was not significant for first 60 kilosecond, and then it suddenly rises up to a factor of 550 to 60 in the counts, and then when we do the spectra, when we look at the spectra, we see very different things. So when you take the spectra between the first 40-50 kiloseconds, so the spectra is very much flat, is completely dominated by a soft thermal component, nothing, no hard repairs. But this 20 to 60 keV emission, they appear in the latter part where there is a flat spectra here, and that flat spectra probably due to coming from the ejection, the movement of the ejection of the jet base. So basically they may originate some non-thermal emissions which are very flat here. So when we do the modeling, we found that that typically the index, power law index of that flat part is 1.46. Okay, so this is very flat compared to what we observe in different spectral states, typically 1.89 to up to 4. Okay, so this actually gives us some confidence that actually looking very minutely the positions of the jet ejections is very important to understand the connections between the jet and the disk. So here actually we do what the next, that take this fraction of the spectra and then try to model with a single power law, and then we extrapolate that power law in the radio band. And what we found in the radio band is that this frequency, the extrapolated flux actually matches with what we have found the flux in the radio observations. Okay, so here I come to the summary and conclusions. So basically, although this extra temporal variability, they seems to respond on longer time scale, but basically to understand the even finite connections between these two coupling, so we have to monitor them in minutes to seconds time scale. But on that ground, it's very difficult to pinpoint where to actually start the monitoring and how frequent to do. But Cygnus X3 on the other hand gives a better opportunity to start and monitoring this kind of joint observation to move better understanding this state, because it shows a very regular periodic pattern of disk and jet activity of the flux correlations. So these are the 4 open questions. So I'll just leave it as it is, and thank you for the organizer to invite me for these talks. Okay.
Thanks, Mayuk. We will take questions for Mayuk after the next talk, because Professor Sandeep Chakraborty will give the next talk. We'll have to leave. So the next talk, Mayuk, can you unshare?
Okay.
Next talk will be by Professor Sandeep Chakraborty, who will give a talk on jets, outflows, and spectral states of black hole binaries. It will be a 25 minutes talk plus 5 minutes for question and answer. And I'll give a warning at 20 minutes. Professor Chakraborty.
Hello, can you hear me?
Yes.
Okay, so let me start this talk. Before I start, I want to share with you a small cartoon diagram I just created. The cartoon is very bad, but at least look at it. Maybe a couple of times I will run it. So what we feel that is happening. See, right now, also people have been talking about the observations, but I am interested in exactly what is happening close to a black hole. So we have this low mass X-ray binary companion, and from there matter is streaming into the system towards the primary, and there is a Keplerian disk sitting there. There is a piling up radius. From there, some matter, Keplerian matter is slowly trickling in, and sub-Keplerian matter is trickling in much faster because they have a low angular momentum. Now, the sub-Keplerian flow feels a centrifugal barrier, and that barrier generally oscillates. Whether you like it or not, they generally oscillate. So try to see that the barrier is oscillating, and from this barrier only the jet forms. So if you see the lower part, when the flow is going to soft intermediate state, rising state, you can see that the lower part is very quickly quenches and the entire jet actually disappears. So this jet disappears in the soft state, and of course it disappears, and the Keplerian disk, and you can see that the matter supply also went down. Then as in the declining state of the outburst, as the it is receding back again, then you can see that the jet is coming back, and the Sen ball is started oscillating and producing quasi-periodic oscillation. In fact, type of quasi-periodic oscillation is also written on the top. So a lot of things are going on in this picture. In this below curve, you can see how the rates are changing with time, and you can see that the halo rate is highest before this rate, and that lag is depending on the viscosity in the Keplerian disk. So before the next trigger, this again you can see that this object is symbol is going backward and the QPO frequency is going down, and all the people who have been calculating the lag and lead and anti-correlations and correlations, jets are observed, what to observe with jets, radio jets, etc., can be understood just from this picture alone with 4 parameters. Because there are many observations where you can go very detailed, but then every detail will have some more detail and you may not be able to understand, and you may think that you will be frustrated in the subject. But the point is that basic things have to be understood. Basic things here, the matter is coming in and matter is piling up, and that piled up matter is getting, when the viscosity is high, it triggers the outburst, and this outbursting source, see, you can see that the matter is now the triggering is taking place. Next triggering, you can see that this piling up is going up, and then it triggered started and the next outburst has started. So this is the picture that I want you to keep in mind, and this of course produces type C QPO because the N ball itself is oscillating at a resonance frequency. Now this N ball, this jet, now the question comes, how much of this jet, what is the output, what is the outflow rate of this jet? Is it a very strong jet or weak jet? At what point the jet becomes strong? At what point jet goes away? So that is the part, that is really the discussion of my talk. But the picture is this. Okay, there is nothing else is going on, and this is good enough even for high mass X-ray binaries where there is a lot of winds. Of course, the subkeplerian flow dominates, and low mass X-ray binaries, there are still winds and their size is very small compared to the Roslow of the central object. So ultimately, wind definitely enters. So this is, I want to get out of this, just to show you that this is the picture. You have to keep in mind that the symbol strength of the shock here decides what is the outflow rate. In the soft state, strength of the shock is 1, namely there is no shock, and outflow rate disappears, and the QP also disappears. And you can see that the entire disk becomes Keplerian. In fact, the subkeplerian and Keplerian disk merges into a single A. So this is, I have written here, copyright my name, because this is really something that I believe that captures the whole spirit of the whole subject. Now let me go back to my talk. Okay, I close this and go back to my talk slideshow from the first slide. Now, so jets and disks are really, in my opinion, two sides of the same coin. Now, some workers often pretend to be surprised at their intellectual ability that they have found a relationship between disk and jet. Now, what else that be there? I mean, these jets have to be produced from the disks. Could jets come out of the thin air? Perhaps, but unlikely. Outflows are seen in every system having a boundary layer, and independent of energies involved and independent of the mass of the black hole. So, kinematic luminosity may vary, may depend on the compactness of the object, but the jets are there whenever there is a boundary layer, and so no fancy thing should be invoked to produce jets, and no generic process should be invoked because there is a risk in generic process, like Penrose mechanism or extraction of energy from the card, because then you would see the jet for all these in spectral states. If you say no, jets are produced by transporting the angular momentum to create a Keplerian disk, again you are in trouble, because then you will see a jet all around even when it is a totally soft state and the accretion rate is not superluminous. So this is a situation. It is not a generic process. It's a locally produced, but it can change, and it can change the outflow rate. Now look at the Bondi flow is or any generalization. We always see an accretion solution with a wind. Of course, the flow parameters and the boundary conditions should vary. So this is a Bondi flow, let us say, which is a generalization of the transonic flow that I talk about all the time. This is a wind flow of Parker. Okay, these two are not really time symmetric. It is not that the Parker flow is exactly time t goes to minus t and one solution becomes another. That is not true. In one case, the matter is falling towards gravity. The other case, matter is going against the gravity. In one case, sound speed is low, velocity was low, and when it enters into black hole, sound speed is high, but velocity is even higher, so that it is a supersonic flow. And in this particular case, sound speed is very high, gas is very hot, but matter again starts from very zero, almost zero velocity from the disk and goes to infinity as a jet. So again it is supersonic. So both cases matter is supersonic at the end, but the initial conditions are totally different because the entropies are different, and that's a separate story. I will not go into this. But now the question comes, if this instead of high A, which is required to produce a jet, can you maintain high A? Can you maintain the high sound speed? Can you maintain the high temperature? If you cannot do that, then the jet will not be produced. So that is why the soft intermediate, soft state, for example, jets are quenched. I will come to this. Now, so if I come to the generic picture again, which I presented, I think in the REDCO conference first in Guwahati at Santobroto's meeting, so matter is going in a Keplerian disk, surrounded by subkeplerian. Subkeplerian flow produces the centrifugal barrier, and centrifugal barriers produces the jet, and this short photon from the Keplerian disk goes to the Senball and pre-jet matter, and then reprocessed. And so this is my generic picture, which many of you know. Now keep this in mind, and also the mind of the movie that I showed, because this picture is a dynamic picture. This is just a one picture where all the components are there, but not all the components should be there for all the time. If it's a pure soft state, many of the components are missing. If it's a pure quiescent state, many of the components are missing. Now, we asked the most basic question back in 1997. Can you calculate the outflow rate from an inflow rate? That's a basic question. Okay, don't worry about how it is produced or not. We assume that it is produced from Senball because all our simulations are showing that profuse amount of matter is coming out of Senball. The question is, can we accelerate it? Can we collimate it? Okay, origin is no problem. So what are the most important parameters of the flow on which the outflow would depend? Now this paper I wrote, estimation of the outflow rate, you can see 1997, and again I revised it, but after 2 years it was rejected, while Blanford and Begelman wrote their adios paper. Okay, and after their paper is accepted, published, my paper is rejected, and so I, in the meantime, of course, I understood the tricks of all this thing by now, and I submitted the paper in the meantime. 1997, 98, I have been publishing in different conference journals. This is Geo solution in a Dhaka conference where Indranil also, remember, went there. Global inflow outflow solution 1990. It was published already, because I know that the referee is taking time. 2 years is too much. But anyway, I submitted it again in A&A 1999, and it was immediately published. So what is the basic picture? Basic picture is matter is coming, it is getting compressed, it is a hotter flow, and this flow has to be taken out by thermally driven and this centrifugal. This is the ideal situation on the right hand side. Now, so what are the parameters? Parameter is I have an m dot in with a certain solid angle, and I have m dot out solid angle, and can we correlate them with respect to the parameter of the shock? This is a theoretical problem, and I can guarantee you this is the turning point of the subject in jet formation, because you will see this equation that I derived, that m dot out by m dot in is coming again and again and again in entire understanding the outflow in the soft state to hard intermediate to soft intermediate to soft and vice versa. So all the entire result depends on the solid angle of the theta in, theta out, and the compression ratio of the shock. So if the shock is not there, compression ratio is 1, and you have no outflow. That is the issue. So this is the result that I presented in my 97, 98, 99 paper, and I found that the highest possible jet is coming out not when the shock is strongest, but when the shock has intermediate strength. In fact, this is the place where we have hard intermediate state. This is the place where shock is strongest. This is the place where we have hard state, then hard intermediate, then soft intermediate state where the outflow rate is highest, and then there is soft state is right here where the outflow rate is again almost 0. This was much more detailed calculated by Tapas Das and myself. Again, it has generally the same pattern, and Chattopadhyay, Santobroto Das, we again added the angular momentum, and it has exactly the same pattern. Namely, the ratio of outflow rate by inflow rate has a highest value at some intermediate shock strength, and it turns out this is nothing but the soft intermediate state of an outbursting source. So this theoretical, the power of the theoretical work is that you don't have to defend it anymore. It is there, it is just calculated, and anybody can derive it. Again and again we derived in various ways, it produces the same result. Now let me go back to some of the observations. First, let me show you that the Chakraborty and Manickam already showed that the Sen ball oscillation produces the quasi-periodic oscillation. Okay, and the Sen ball produces, Chakraborty Titachuk already said that the Sen ball produces the componized photon, and therefore the componized photons are taking part in the QPO, and therefore if you go to higher and higher frequency, higher and higher energy, where they are componized photon, you can see 4 to 9 to 13, the RMS value is going up, because it is the componized photon which are participating in the QPO and not the disk photon. Here I have plotted for 0 to 4, either there is no peak. Of course, if you go to very high energy, the peak will go down because not too many photons are participating in it. Okay, now first time we understood that the jets are microcontrolling the spectral state, and jets are microcontrolling the light curve. So this is again the same paper, Chakraborty Manickam. Look at this, one of the count rate as a, so this is the count rate arrow, says there is the count rate, this light curve of GRS 1915. See, I didn't know the name of that class because Belloni's paper was not published yet, saying what class it is. So we just took a light curve and we find that the count rate is going up and down. So these are the called burst on state and these are burst off state. Okay. What we found very excitingly, as you can see that these are the Fourier transform. On this side, QPO frequency can be seen, dotted line is connecting all the QPO frequencies during the couple of hours of data, okay, even 1 hour of data. This is the time. What you can see is that if the object is in the bottom phase, there is a burst off state for a long time, then QPO frequency is very high, very low. And then when it is very small time here, QPO frequency is high. So there is a relationship between, we found out that there is a relationship between how long it is in the off state vis-a-vis what is the QPO frequency. This is very exciting. In other words, matter wants to oscillate, and the frequency is also deciding how long it is going to stay in the off state. These two are completely different things. Now, so this is what our analytical solution for the off state duration in seconds. And you can see that there is a relationship, and this relationship works for GRS all the time. Now, why I am excited? Because this, how long it is going to be in off state and how long will be in on state can be understood from the same formula that I derived just now here. Okay, this formula. Exactly this formula is used to correlate the location of the shock, this even sonic point, and therefore how long time it will take for the sonic radius to fill. And as soon as you feel the sonic radius, you go to the burst on state and start draining the matter. And as soon as you drain the matter, you go to the burst off state. So the burst off state and burst on state depends on how long time it takes to fill the sonic sphere, and therefore it depends on the formula that I just derived. And it was directly, this formula is derived directly from that formula, so we can understand much detailed things. Now, why this is a miracle and in TCAP? The miracle is that there are many things we correlated. One is the infall time with the infall time is correlated with the QPO period, because one is a resonance with respect to the other. Quasi-periodic oscillation period is exactly same as of the infall time period or the cooling time scale during the quantization. Other miracle is that we correlated the time to fill the sonic sphere is the same as the time of the duration of the off state. And so these two can be correlated. In fact, why TCAP is most successful in fitting all the data is that TCAP takes only 4 parameters. I know that the 4 parameter is not enough, but I also know that the other 2, 3, 5 parameters change maybe 2-3% across the spectral state. So that is where the interesting part comes in, that we recycle many parameters. For example, the inner edge of the Kepler-N is the outer edge of the Sen ball, so one parameter is gone. We recycle the QPO frequency with the infall time scale, so the compression ratio and the accretion rates are related with the cooling time scale. So this is how you correlate and you reduce the parameter into 4. Now, I know there are other parameters. Geometry will be a little bit thing, the jet could be produced, but then these parameters may be changing by a few % across the spectral state. So you may as well think those parameters are constant. That is why you don't miss much by assuming a 4 parameters. Otherwise, I could have also used 50 parameters and boast for it, but I am not doing that. I am happy that I can use only 4 parameters. Now, this picture that I already showed, that this is the key of the whole thing, the outflow rate. For the jets are produced. This is from the Orgogi Jana's paper recently published. It basically working on my work on my curve and quantified exactly where what kind of jet. There is no jet when there is no compression ratio is 1, blobby jet and the compact jet, tenuous jet, etc. So these are produced. The blobs are produced when you cool down the jet, base of the jet, and the blobs are separated because it suddenly becomes supersonic when the sound speed goes down. So this is the relationship is there, and I know that all the observations that people are talking about, as soon as I see it, I know that I know the answer. Now let me show you one of the interesting things that a lot of people talk, very proud of drawing this picture, the God's given Q diagram. Of course, it doesn't look like Q for the same object from outwards to outwards, but because Europeans say so, we should call it Q diagram. Now, this diagram also produces a jet line. Okay, it says that jets started coming from here. But what is this place? This is the soft intermediate place, the same place where I already showed you in my card that this is the place where the outflow rate, highest possible outflow by inflow rate is produced. Okay, now then you come back to the next paper which I wrote in 1998. I showed that as soon as jet started producing, is getting produced, the spectral state becomes softened. Okay, can you verify it? Why it is softened? Because I am reducing the number of electrons for the same value of Keplerian photon, and therefore I must be able to cool down this envelope very quickly. So index must go up. So this is the picture. This is the calculation of mine in 1998 and 1990 and 2002 with Nondi and Manikom and Professor Rao. We already showed that exactly how the Barstow and Barstow states should change the spectrum. In one case, the matter is getting lost by the symbol. The other case, matter is returning back to this symbol from the this part, this halo part, so that it can enter. So these two, this recycling between off state and on state, I should be able to see pivoting of the spectral state. Do I see it? The answer is yes. You see, day by day, all the spectra is seen, and you can see that the spectral state, the observation shows that the pivoting is produced at a larger energy because of the hardening of the soft state and softening of the hard state during the mass loss and mass gain. So that was published in Monthly Notices 2002. So they are related. I mean, jets are produced and they have a telltale signature on the spectrum. You should always be able to see from the spectrum, yes, jets are getting produced, and yes, that is the amount of jet that is getting produced. Now, do the numerical simulation. The Gorai and et al. Bose, probably I was also there, and you can see that as the accretion rate of the disk is going up, this is a Monte Carlo simulation. You can see that the accretion rate is going down. Oh, sorry, jet is going down because the jet is getting, base of the jet is getting cooled, and it is no longer be able to drive thermally the jet outward. Okay, here also
you have
the
5
same
minutes.
yeah,
you have 5 minutes.
Same thing. Here you can see that the spectral state is going up, the spectral index is going up. Okay, as you increase the accretion rate. Why? Because symbol is, again, you keep the movie in mind, the movie that I showed you originally. As the accretion rate goes up, the symbol is getting squenched, and it is getting cooler and cooler, and the spectral index is getting higher, QPO frequency is getting higher, and the outflows rate is getting lower. Okay, so all these things are coming out from the numerical simulation. You can see the base of the jet getting quenched totally as you increase the accretion rate of the disk. So this is also on the same paper produced. Now let me tell you that why. Let us say in 1999, here again, interesting paper, Adios. So my paper got delayed by 2 years in the journal, but I published in different conference proceedings. But what was it all about? The Adios paper came out in between. What Adios said is a self-similar solution of ADAP. Okay, this is the solution of Adios. It says that from every radius, matter can go out and with a constant rate, and eventually entire part of the disk can come out of the, and there is nothing is accretion, no accretion is going on. You can see that. So how important is this solution, and whether it is even complementary to my solution or it is a reality? I will tell you why I do not like this solution, because self-similar solutions do not work in a black hole circumstance. Black hole has its own length scale, its own size, horizon size. There is a sonic point, there is a centrifugal barrier size, there is a Keplerian disk could be truncated somewhere. So all the length scales are there, and therefore people should not do self-similar flow. Unfortunately, the ADAPT is self-similar and Narayan is, and following that the Adios is self-similar, and these are not useful. I will show you by doing actual numerical simulation. Let me show you the actual numerical simulation. You go to ADAPT regime, so-called very low accretion rate and very low cooling. What do you see? Yes, matter is going out, but only from region inside the shock. So this is a supersonic flow becoming subsonic, and the subsonic flow is mostly going out. Very similar to ADAPT, so hats off, but matter is getting accreted, and it is not the entire disk that is participating, only the post-shock region. Now come to very cold, high cooling. Look at this. The same other parameters are same. So the shock location is no longer at 30. Shock location has changed to 10, and there is hardly any outflow. So there is no mystery. Why outflow is from things we do not know. How long we do not know, and when we will know is anybody's guess. But now you do the medium amount of cooling, you see all kinds of beautiful things. The shocks are producing, shocks are getting oscillating, it is QPO frequencies produced, there are beautiful turbulences, some jets are coming out, some matter is also getting out. Now I am almost through. That movie I have already shown. Now since the observation facility, I want to show only 2-3 slides just to show you that we also have an observation facility in Sitapur, in Midnapur. This is the main building. There is the dining halls, and the dining hall, the hostel room of 32 people can stay is getting produced, getting created. There are 2 telescopes. One is Orundhuti 24-inch plane wave, Bosistor play 10-inch mid. Both are fully automated, CCD camera and spectrometers. You can see that during and before the lockdown and after the lockdown, how many extra stars can be seen. So sky was really cleared up after lockdown. So this is our picture by CCD camera, and this is also our spectrometer. This is a 0.1 angstrom per pixel, very high resolution spectrometer, fully automated telescope, and so people are invited to come. We had a small conference some time ago. In fact, last year COVID, we did not do anything. Professor Ramsagar came, Ranjan Gupta came, and in fact they even said that this is such a beautiful place, we can have TMT meetings also. We can so this hostel room is getting created, and 32 people can stay. We had these conferences there. So we need a visitor and project scientists, etc. And those who are sincere and want to work here can contact me. We have a small post here for a project scientist kind of thing. Fresh PhD would be welcome. Those who actually have touched a telescope, not like a remote fellows don't know what to do with the telescope, but only the data they can do. But no, we want actually people who wants to touch the telescope. Our students are very good. Students are actually very expert in handling the telescope, and all the softwares are we are doing all right. We are scanning also the entire sky. So thanks everybody. Now I am open to questions.
Thank you, Professor Chakraborty. Now, this is a time for a few questions. We'll first take question for Professor Sandeep Chakraborty, then we'll take a question for Mayuk later. So I see that Santabrato has raised hand. So Santabrato can unmute and ask.
So I had a question to Mayuk.
Okay, we'll take first the question for Sandeep Chakraborty. So is there any question, because he will have to leave. So so Pankaj, I can see you have raised hand. If this is a question for Professor Chakraborty, you can ask.
Yes, I have a very general question. So regarding the cartoon diagram that Professor Chakraborty showed in the beginning. Okay. So I just want to ask, like he said that, okay, when the sandball contract and reach the surface of it, the jet disappears. So I just generally want to know what happens to the magnetic field. Does it diffuse out? Does it vanish? Or what happened to the magnetic field?
No, magnetic field in the case of black holes, you have to be very careful, because in a neutron star, magnetic fields are anchored with the neutron stars. Okay.
Yeah. Okay.
And the magnetic fields are randomly brought by from the companion or from interstellar medium in the case of a black hole binaries. Okay. These magnetic fields can do a lot of things in the collimating the jet, but we have done wonderful numerical simulations to show. I didn't have time to show that it is a wonderful collimator, it is a wonderful accelerator, but it does not magnetic. You can allow magnetic field to take the matter out of the system, but magnetic fields, you cannot have a large range magnetic field sitting there for ages around a black hole, because magnetic fields of random signs are getting advected and they are cancelling each other, because there is no reason why all the magnetic fields will be coming of the same sign. And there is no God sitting there holding the magnetic field at infinity for you, because magnetic field, the divergence of B is 0. Magnetic field must be destroyed. Magnetic field must be closed. So either they are destroyed by reconnection or they have to be closed. So there is no long-term magnetic field which is sitting there. So that field you cannot rely on producing a jet. You can rely on it on collimating a jet by Hooke's stress. You can also rely on it for acceleration by magnetic rubber band effect that Anuj Nandi and we wrote in the 2001, and there are a lot of other good things going on. But I don't think that magnetic field is required very much to feed the data. We have been feeding data for almost all the objects, even from AGNs to intermediate mass black holes to stellar mass, most certainly at least 20 to 30 objects. We did not need any magnetic field to feed the observational data within chi-square 1.2 or 1.1 or something like that. So magnetic field is not very important in determining the spectrum of the disk. It may be important in giving you the collimation and the acceleration.
Okay, so just a quick follow-up. So the simulation that you are talking about, that you did magnetic MHD simulation.
Yes.
So does it hold for any magnetic field value? Like let's say the magnetic field is stronger and the matter is lower compared to what people typically call beta values in.
No, it does not. Magnetic field, this is the beauty of it. All the simulations that are in the literature, they are very sensitive to the magnetic parameter. Now, if I start with a very strong magnetic field, it will immediately get out of the system due to buoyancy. As you know, magnetic fields are highly buoyant. They don't have matter. Stronger the field, lesser the matter inside, and the buoyancy is the Archimedes' law take over. So only these smallest possible filaments can be smuggled into the system because their drag is very low, and therefore they take fastest possible time to go towards the black hole. So there is only a small parameter space. I think if you can look at my paper with Sidney De Silva, 1994, we have extensively answered your question. And then of course the paper was used by Nandi and myself for magnetic rubber band effect, and by Gorai and company. Sudeep Gorai recently published an abject paper with Dinso Balsara, myself, and Kim Jin Ho a couple of years ago. It is absolutely certain, and we do not know very much how much magnetic field does, because magnetic field is very tricky parameter. First of all, nobody knows how to accurately preserve it. You have to go to fifth order accuracy, not like second order, third. All the simulations you get from GUs are wrong, because they are all dissipative. They don't obey Maxwell's divergence of B equal to 0. So if you want to use magnetic field, use it honestly, and so you have to have a very good code. And only few people in the world have fifth order accurate code, and you will be surprised that it is highly sensitive to the magnetic field. My personal view is, do not go into magnetic field very much right now. If you can fit everything without magnetic field, very good. I think that your rest of your life you can be happily fitting data without any trouble.
Okay, thank you.
Any other question for Professor Chakraborty? I cannot see any. If there is no other question for him, we will thank him. And now we will take questions for Moyuk. So Shantabroto, you can unmute and ask.
Hi.
I have a simple question to Moyuk. I mean, she talked about Cygnus X3. I mean, is there any indication that how accurately you can measure the mass of this object?
No, so far we don't have any dynamical confirmations. So, but people usually believe this is hosting a black hole system. So yeah, no confirmation on the mass.
Oh, okay. Thank you.
And I think there are 2 questions on the chat box. Okay. So yeah, Suhas asked like whether there is a signature of hysteresis loop in binary. So the hysteresis loop I was talking.
Moyuk,
Yeah.
please let me read the question first,
Okay,
so that everyone can. So Subhash Chaudhury's question is, if there is a signature of hysteresis loops in the binary system, then what type of histograms one will get? I mean, central limit theorem will not work. Yes.
Suhas, so the hysteresis loop I was talking about in the fundamental plane of X-ray and the radio diagram, but not there are not many data points like when there is a soft state and then it comes back to the intermediate states. We don't have many observations from the radio sites, so the true hysteresis, how it looks like, we don't know much yet. So far what we have observed like a loop kind of pattern, so there is a change in the track and that might again make a loop. So if we in the future, if you add more observations, probably we will have better understanding. But yes, also CLT cannot work because we don't have also much data points to actually apply on that.
Okay, so the next question by Radhika. Thanks for referring to our results. All the QPO changes are seen in hours time scale except a few sources. Problem is cause of lack of continuous observation by RXT.
Yes, so that's the one big problem with RXT, but with AstroSat we have done some better. We have done better than that what we had done under RXT. But I would also appreciate, like, if you think the QPO changes in hours time scale, it's better to go with more frequent, like for example dynamic time scale, so that you can have hourly basis plot. So and that will show how the QPO frequency changes, and on the same plot you can have the radio flux density to see how those are correlated or anti-correlated. Okay.
All right. Are there more questions? Santabrata, you can lower your hand. And yes, there is a question from Jitesh. You can unmute and ask.
Hi, Mayuk.
Hi, Jitesh. Yeah.
Yeah. So I have a question. I mean, like you have showed a picture that there is a jet and then there is a QPO, but the jet is.
Sorry, can you be louder? I'm sorry, my speaker might be not.
Yeah. Okay. So in one of your slide for H1743 or something, so you have showed there is a QPO like when there is a jet, but the jet is like disrupted or disappeared, and then like the QPO goes. So, right. But suppose if you consider like a fast transition, like the QPOs appeared and disappeared very quickly, like for example in a short period of interval. So how do you explain this scenario? Like a transient QPO. So the jet,
yeah, so basically the idea may be QPO, I mean, it's all again goes to the simulation, but the idea is basically if the inner part of the disk, it somehow is represents the connections between the jet origin of the jet base and the QPO, like this type C QPOs, they might coming from the inner part of the disk. So as the inner part goes into the jet mode or the radio jet base, so the oscillations disappear because that is the portion of the disk which goes into the jet. So that is like the connection we are thinking, and we might be exploring more on that direction to find out when exactly the QPO disappears and are there any jet signatures. So the idea is basically the region of the disk that generates the QPO actually goes to the jet part. So that's why it's disappeared from the power spectra.
Okay, thank you.
Are there any other questions for Moyuk? I do not find any. If not, let's thank Moyuk, and we can perhaps take a tea break. I am handing over to Shashi.
Yeah, so I think, yeah, tea break. If I think since we are going to start around 11:45, I think it's still within 10 minutes. I think if we squeeze in place of 15 minutes, if we squeeze just it to 10 minutes, I think still we can start the session in time. So I would propose that let us gather at 11:45 again, so that we can maintain the same time schedule. Professor Sudeep, is that fine?
Yes, that is fine for me.
Yeah, yeah. So see you within 10 minutes.
Hello, Shashi. Should we start? Aru, if you are here, you can perhaps share your screen.
Sure,
Yeah.
I will do that. Thank you.
Should we start?
Yeah, please.
All right. Next talk will be by Aru Berry on fast timing with AstroSat and new light on X-ray binaries using the multi-wavelength approach. It will be a half-an-hour talk, so 25 minutes plus 5 minutes for question and answer. I'll give a warning at 20 minutes. Aru.
Yes. Good morning, everyone. Thank you, organizers and everyone, for giving me this opportunity to present our work in this conference. So as the title of my talk is Fast Timing and New Light on X-ray Binaries Using the Multi-Wavelength Approach. So this is the topic which I've been working on for a while. And this work has been done with a lot of people all over the world. So I would like to thank all my collaborators also for helping me out at different aspects. So outline of the talk will be, first I'll give you a very brief glimpse to the class of objects, thanks to the previous talks that we know now. We are familiar with the geometry and the picture of X-ray binaries, and specifically low mass X-ray binaries, which are the focus of this talk. First part of the talk will be focused on a particular source, 1636, which has been observed with AstroSat frequently, and several thermonuclear experiments have been observed with this particular source. Second part of the talk will be focused on another class of low mass X-ray binaries known as accreting millisecond X-ray pulsars. Finally, I will give you some new results obtained from the multi-wavelength study of the peculiar black hole candidate X-ray transient 1357.2 minus 0933. So we all are familiar with this picture now, which is an X-ray binary, low mass X-ray binary, where the object, which compact object sitting at the center of this accretion disk is accreting from the low mass companion star, and there are several exotic phenomena happening by this accretion process. There are accretion and ejection processes both taking place in these kind of objects. Like outflows in the form of jets or winds, or there can be a X-ray emission which is from the inner part of the accretion disk. However, we also have the multi-wavelength image of this X-ray binary in terms of like different parts of this image illuminates in different wavelengths. Like for example, in the morning talk, we heard from Ranjiv that outer part of the accretion disk illuminates in optical. We have radio jets, and then the inner part, which is hot, illuminates in X-rays and so on. So to understand the complete picture of the systems, we need to understand it in a multi-wavelength band, which is now the state of the art research problem. Sorry. So coming to the first class of the part of my talk, which is focused on thermonuclear X-ray burst from accreting low magnetic field neutron stars. So if you recall from Ranjiv's talk in the morning, he mentioned about thermonuclear X-ray bursts, which are because of the matter onto the falling onto the neutron star, and at certain right ignition depth, and when particular ignition depth and temperature is attained, it undergoes a runaway flash, which is in the form of X-ray flash observed in the X-ray light curve, which is shown here on the top panel, which shows large increase in the X-ray intensity and an exponential decay. And these are very abrupt and very transient in nature, so we cannot predict beforehand when you will be observing a next thermonuclear X-ray burst. But since they are these occur from the surface of the neutron star, they are an excellent transient features which are important to understand the equation of state of the neutron star, and hence we have been hunting for these kind of bursts to understand the behavior during this of X-ray emission during these bursts. Observationally speaking, when we try to fit this X-ray burst spectra in small segments, they are well fitted within a thermal blackbody spectrum. And as you know, from the thermal blackbody spectrum, we can obtain the radius of the neutron star, which is given by the Stephen Boltzmann law, which is given here. We measure the flux here, and the temperature measurements which are taken during the spectroscopy study during these thermonuclear X-ray bursts can give us an idea about the radius. And this is one of the very few ways by which one can measure the radius of the neutron star and from the temperature measurements. So this is also important for carrying out experiments which cannot be taken place on the Earth because of the extreme conditions which are present in the neutron star compared to LHC or any other experiments which are taking place at high temperature compared to the temperatures which we obtain on the surface of the neutron star. So again, as I mentioned, that these have been a particular interest of the community to understand how these thermonuclear bursts behave. There have been several missions, right from the discovery of thermonuclear X-ray bursts, which have been focused on studying these bursts. Specifically talking about RX-3, which was the excellent timing instrument, which was available to us until 2012. Which is shown here in this blue color or cyan color curve, this particular plots compare the effective area versus energy. And if you observe this effective areas, you see that effective area of RX-3 PCA was way larger and hence very suitable for, because as I mentioned, they are very abrupt, and also they last for only fraction of seconds. And we are also interested in performing time result study with these kind of bursts, which means in the fraction of seconds, how the accretion geometry and how the temperatures, etc., are varying in these bursts are of interest. So we need excellent timing plus large effective area combination to understand or to study these kind of bursts. So RX-3, which had 5 proportional counters on board, was one of the most successful mission in this direction, which led to several discoveries, like discovery of thermonuclear X-ray burst oscillations, getting peculiar profiles in the thermonuclear X-ray burst, and so on, which was discoveries led by RX-3. After RX-3 was no longer operative, in 2015 we had LAX-PC, which was another X-ray timing instrument dedicated to study this class of objects specifically and to understand the equation of state. So now if we compare the effective area of LAX-PC with respect to RX-3 PC, we observe that above or around 20 keV, when the RX-3 PC effective area falls rapidly, there is a still a large effective area, or the collecting efficiency achievable with LAX-PC. Hence, it is a very excellent instrument to study this class of objects. So we carried out this study during the PV phase data of 1636, just after the launch of AstroSat. So this observation was taken sometime in March 2016, if I remember correctly. So this was an important discovery which was made during this observation, which was observation of a triple X-ray burst. And if you look at the time scales of these or the time gap between two bursts, it is of the order of 5 minutes. And to our surprise, we obtained the wait time of around 5.5 minutes between the second and the third second and third X-ray burst. So as a continuously monitoring this particular source, specifically 1636, if you look at the RX-3 PC archive, there are more than 1,000 observations available. So it's a kind of a very well-known source and well-studied source with RX-3 PCA because of several peculiar features which was observed in this particular source, different types of QPOs, different types of bursts, and so on. So we look at the MinBar, which is another catalog available for all the burst sources, and which is maintained by Galloway, who has been observing or looking at the all burst sources available, studied by different instruments. So what we found was the triplets which were observed for different sources are classified in this particular table, which is shown that only few triplet of X-ray bursts, when there are several thousands of X-ray bursts been observed since date, but only few of triplets. So hence it is a rarest triplet. And that too, if you look at the wait times which were observed during these bursts, you see that there is 8.4 minutes, and for these are the wait times for this particular source, which is 1636, and hence it is the shortest wait time which we observed for this with this particular X-ray observation. So to understand this short recurrence burst, there are several possibilities being discussed in literature. And one of them is which is a waiting point in the thermonuclear chain reaction. So as I mentioned, these are thermonuclear runaway processes, not the gravitational energy release processes. Hence, people have done nuclear reaction networks, and from that they have found there can be a waiting point in the reaction network, which can lead to this kind of multi-burst or multiplets in the X-ray light curve. However, there was a recent work which was based on one-dimensional, single zone simulation based upon transportation by convection, and this convection is driven by the ignition depth. So what Keek and Hager et al. Believe that there can be leftover material. So if the ignition has taken place at particular right depth of temperature and ignition depth, so there can be some leftovers available on the surface of the neutron star, which can reignite after some fraction of time. And this heat is transported by convection, and this convection is driven by the ignition depth between different layers on the neutron star surface. So based on the simulation, they simulated the profile of a triplet. And if you observe this triplet profile, which is a simulated one, you see between the triplet, first and the second burst, there is also a secondary peak, which is generated by these simulations. And similarly, there's a small kink here also, which is being seen with these simulations. However, if you compare these profiles with what has been observed with AstroSat or previously with other instruments like integral, this is a profile which was seen for Equalus X1. The profile of the triplet which was observed is similar to what we observed for 1636, and there is no presence of this kind of bump or a kink or a second flare or some flaring event in between the two bursts. So clearly this model, or the model based on this single zone convection, is not completely giving us the understanding about the behavior of the triplets observed in 1636. There are other models which are like spreading layer of accreted matter on the surface of the neutron stars, which are also believed to generate these kind of multiplets in the X-ray light curves. But there are certain shortcomings to this as well. I will discuss that shortcoming in a while. Meanwhile, we also looked at some other distinct feature which is observed in the hard X-ray band. So as you can see from the effective area curve, with the large effective area available with LAC-SPC, we can also go for studying these bursts at very hard X-ray emissions. So we looked at the profile in energies beyond 30 keV. This is on the top panel, right? We have energy resolved burst profiles, and from these profiles we can see the burst was detected up to 30 keV in this particular source, 1636. We looked at the profile in a higher energy band, which is 30 to 80 keV band, and we observed there is some kind of dip observed here. But this dip was observed only before the dead time correction was performed. As soon as we performed the dead time correction, we find that this dip was no longer available, seen in the burst profile. And in the previous studies made with integral and also with RXT-PCA, there have been reports which have reported a dip in the hard X-rays, and this is a example profile from Kazawa et al. In 2017, where they have found a dip in the burst profile, and this dip was obtained after stacking of 123 X-ray burst. However, this is the profile which we are getting only with single burst. So they explain this dip based upon the Compton upscattering or the electron cooling effect. So we believe that higher energy X-ray emission in or hard X-ray burst or X-ray burst in higher energies are observed because of the Compton upscattering of the soft X-ray photons. And if this electron cooling effect is still taking place during the X-ray burst, what it is doing is there is some change in the hard X-ray flux during the X-ray burst, and which is getting transported to the soft X-ray flux. And this is how they explain the dip in this hard X-ray profiles of the burst. And these authors also propose that if this is the scenario, then it is difficult to constrain constrain equation of state or measure mass and radius from the X-ray burst, where specifically the discussion about hard X-ray burst observed during hard X-ray spectral state, where you see such kind of accretion flow where the Compton upscattering is dominant process. So, but in comparison to results which is obtained with better instruments like AstroSat, we did not observe such behavior. So such theories have to be confirmed again with more dedicated and more effective instruments like LAX-PC in the future. So coming to the time resolved spectroscopy during these bursts, as I mentioned, from the time resolved spectroscopy, we can observe or measure the radius of the neutron star. So this is what we observe. There were several bursts observed with 1636. So I'm showing here only a couple of them. And if you look at the on the top panel, it is a count rate profile. On the second panel, you see the temperature profile, and the radius is measured in the is plotted in the third panel. So you see this is a special class of X-ray burst which was observed during these observations, which are also known as photospheric radius expansion burst. So these photospheric radius expansion bursts are also again important class to study the radius of the radius of the neutron star or measure the radius of the neutron star. And during these bursts, basically it is believed that the local Eddington luminosity exceeds, and hence your the envelope above the neutron star moves above the neutron star surface, and hence you see the increase in the radius. And as soon as it fall back onto the surface of the neutron star, your temperature again increases, and while your radius began to decrease. Although all this process takes place at almost the constant flux values. So the shaded region in this time resolved spectral profile is are the regions where we observe the thermonuclear X-ray burst oscillations. So to search for thermonuclear X-ray burst oscillations, we again require a micro instruments with microseconds of sensitivity in time, and also large number of counts or photons available to us to obtain or search for these burst oscillations. This is just an example profile where we just compared.
You have 5 minutes. 5 minutes.
Okay, so I'll skip on this. So we looked at the burst oscillations, and we did detected burst oscillations here, and there's a peak which is observed around 581 Hertz, which is the spin frequency of this neutron star. We looked at different profiles, different behavior, like how the fractional amplitude varies as a function of energy and so on. So as you can see in this profile, your frequency is evolving with time, and we compared all our results with the models available. Luckily, all our results are consistent with the models which have been proposed to understand these oscillations or burst oscillations. So I'm not conclude for the first part of the talk, which says that first of all, the spreading layer model, which can explain some part of the triplet observed, but there is some important component which is missing, which believes which discards or which does not incorporate the radial velocity component, which is an important factor unless the viscosity plays a role. So this component has to be incorporated in this spreading layer model to completely understand the triplets or the multiplets observed. And our burst oscillation results were in good agreement. However, for the phase lag study, we require to combine or have a simultaneous observation with lower energy, high time resolution instruments like NICEL. So these are similar results on another subclass, which is accreting millisecond exapulsars, where we found pulsations around 442 hertz, and this was the first source observed with AstroSat. Again, we performed the spectroscopic studies, and where we found the reflection component, we fitted with the reflection models or relativistic models available to us, and we found the high reflection component factor which is available, or a large ionization parameter which is obtained for this particular observation, which is 3.5 for this particular source. And we obtained the upper limit to the magnetic field by using the flux values and so on, and using this equation. And the upper limit to the magnetic field was of the order of 10⁹ Gauss. Again, we are continuing this study with another source which we proposed with AstroSat, and pulsations have been again found at 401. So this is the last part of the talk, where we are focusing on the SwiftJ 1357. This is a peculiar source because it shows very prominent optical dips during its outburst. And these optical dips are observed, but there are no dips observed in X-rays, and it is believed to be high inclination system. And if it's a high inclination system, then we expect to observe X-ray dips as well. And this was first studied in 2013 by Coral Centena, which was a science paper. And in this paper, they proposed there is a existence of an obscuring torus in the inner part of the accretion disk, which is responsible for this kind of optical dips. And these obscuring structures move outwards as the outburst progress or outburst decays, and hence your duration of the optical dips also increase, which is seen in the simulation here. So we performed this multi-wavelength study with the observations with NuSTAR and Swift, and we observed the entire outburst of during 2017 outburst, and we see this profile where you can see that power law index is showing an evolution going from hard to the soft state, and this is quite typical of low mass X binaries observed. And then this is a correlation plot in UV and optical magnitudes. And if you look at this plot here, the gray plots shows neutron star, and black is for black hole data points. And for black hole, it obeys the black hole. So from this, although they are not confirmed dynamical mass measurements, but they do data points do match the black hole system. So that's why it is believed as black hole candidate. We looked at the power density spectrum. We did not find any QPO which was similar to observed in the optical band. So if you look at the Q value here, it's quite low. We looked at the power density spectrum. So the motivation here was, if there is an obscuring structure in the accretion disk, then it should pop up as a reflection features in the X-ray spectrum beyond 10 kV. So with our proposed NuSTAR observation, we did not find any reflection features. However, it was a flat spectrum with a power law index of 1.7 in both the NuSTAR observations obtained. We looked at the source with ultracam, and then we see the large optical dips here. However, the lack of dips in X-rays. This is the optical spectrum obtained with the ultracam observation. You can see the sharp feature here in millihertz range. So we proposed the geometry of this particular system with the multi-wavelength study, and we also had the radio observations available for this particular source, where we see this data point at 10⁻⁴ Jansky. And based on this, we believe that the system has obscuring structures in the inner part of the accretion disk, which is similar to proposed by Coral Centena, but there is a jet base which is responsible for the red optical emission, and the viscosity in the inner part of the accretion disk is responsible for the bluer dips. And also there is an extended corona which may be responsible for the hard X-ray emission which we observe in X-rays. Now in 2019, although the first outburst was observed in 2011, after 7 years, the second outburst happened. But in 2019, we were lucky to have the third outburst in this particular source. And again, the multi-wavelength campaign began for this particular source. And this was source was frequently observed with nicer, and we see the optical dips, X-ray dips, not X-ray dips, but sometimes some kind of variability in the X-ray light curves, and which is energy dependent and dominant at lower energies. And we also see a feature here, which is a QPO like feature, or a QPO rather. This is evolution which is similar to the previous outburst. Very important result was the sharp peak or the cube at the same frequency which was observed at optical in the optical band. And if you compare this frequency with the optical evolution, which is shown in black and red during the previous outburst, the blue are the nicer data points, we see the similar millihertz variability, although they are not following the monotonic trend which was observed in optical band. So we believe that although this optical X-ray dips are, or some kind of X-ray variability is seen, but there can be a the mechanism which is responsible for these dips may be different. We studied some another part with UV data, which is to understand the X-ray UV correlation. And with this, we wanted to understand what could be the mechanism responsible for the emission in the optical and UV. So we find that the viscosity model well fits our data points in all in optical and UV band. So finally, I will conclude. If you want to understand the complete geometry of the system, we need to tackle the entire multi-wavelength band, and that too simultaneously, to understand these accretion and ejection processes in these systems. And with this, thanks, and I'm sorry for exceeding time.
Thanks, Aru. Questions first, Indranil, you can unmute and ask.
Hi, can you hear me?
Yes, yes.
Okay, I have a very simple question. You see, you measured, I mean, you gave an estimation of the magnetic field. It's around 10⁹ or something, right?
Yes, yes.
Yeah, it's low, but it's not too low. So,
yes.
what should be the geometry of the corona that you're considering?
So this is purely from the I mean flux values. We are not assuming any geometry here. So as you can see here, the simple magnetic moment, which is I mean based upon some assumptions, also has been taken into account. So there is no corona or any geometry which we are taking into account for, and this is an upper limit to the magnetic field. There is a more detailed paper by Mukherjee et al. Where they have estimated the magnetic fields of these systems for all the accreting millisecond X-ray pulsars. So this equation was taken from that paper.
Okay. Okay.
Okay, we'll take 2 questions from the chat box, and we won't take any more questions because we don't have time. So Kewal Anand says that I have read your paper Berry et al. 2018. There you did not study the energy spectrum of persistent emission of the source 4U1636. Can you please what causes the persistent emission, and which model can be used to study the persistent emission spectrum of the source?
So when you talk about persistent emission on these particular class of objects, there is no one single model which we can recommend, or any model we can. So as you see that there is evolution in the spectral states, and which is by evolution I mean the accretion disk move inwards and outwards depending upon the spectral state. If it's a high accretion rate, high accretion state of the system, then the accretion disk might be closer to the compact object, and hence you might have different components which may be a boundary layer and a surface emission, neutron star surface emission, which can be taken care by the black body or disk BB like components. They can be emission from the disk also. Plus, if you have a hard X-ray emission, hard X-ray state, then you can have a corona also, which can be in this case the disk is receding away from the neutron star. So there you can play around with COMP-TT models and nth comp, and also now if you want to really understand the reflection features, there are relativistic state-of-the-art models also available. So you have to play around with all these models to figure out what is the best suited or best explain your data. So this is what I can suggest at the moment. And we didn't study persistent emission in that paper because that was not the motivation to report. So the persistent emission is a separate aspect. We were focused on thermonuclear X-ray burst in that study.
The last question is from Biplav Sarkar. What mechanism will give rise to the vertical perturbation of inner disk causing the optical dips?
So what perturbation? Okay, so the perturbation here are the obscuring torus, which was believed for that particular source, Swift 1357. So this was a peculiar source because the optical dips which were observed from the simulations, they believe there is a thick region or thick absorbing material. And if you look at the multi-band optical dips also, the normal absorption could not explain the optical dips. By normal absorption, I mean, if you assume that it's a regular kind of absorption of the absorbing material around the neutrons, compact object, then you expect that the short wavelength band should be more absorbed, but that was not observed in our observations. It was the reverse what we observed, that the red component or the red band of optical emission was more obscured compared to your blue band observations. So that is why we believe that this is present in this particular or peculiar source, which is obscuring torus, rather than a normal absorption due to the material in the inner accretion disk.
All right, let's thank Karu.
Okay, thank you.
You can unshare. And the next talk will be by Indranil Chattopadhyay on jets around X-ray binaries. It is a 25 minutes talk plus 5 minutes question and answer. I'll give a warning at 20 minutes. Indranil.
All right. Just a minute. Is it full screen now?
Yes.
Okay. All right. All right. I firstly thank the organizers to give me this opportunity to talk in this conference. And my student Raj is also part of this work that we are going to present here. So quasar AGN is an active accretion jet system around a supermassive black hole. While a microquasar, I mean the micro word is basically small, and therefore it's a small quasar, is actually an accretion jet system around stellar mass black hole or around a neutron star. However, we just concentrate on jets from black hole microquasars. The main difference in microquasars and quasars are three. Okay, the outer boundary condition. For example, the quasar is fed by stars, dust, etc., from the galaxy, something like this, a cartoon diagram of an AGN or a quasar. And a microquasar is fed by a secondary star. Okay, so if this is the black hole or the central object, and this is the secondary star, so that matter is fed primarily from the secondary star. Okay. And the second is that microquasars being small, they evolve faster, so we see state changes. And the third is that microquasar disks emits mainly in X-rays, while a quasar disk emits from radio to gamma rays. Okay, so these are the basic differences. In other words, apart from some details, quasars and microquasar jets can be treated in equal footing. Okay, so although the title of my talk is around jets around microquasars, it doesn't matter. Okay, you can just take it as jets around quasars as well, or AGNs. So now there is from microquasars, of course, there is enough indirect evidence that the large-scale jet is matter dominated. Okay, and that the jet states are also correlated with the accretion states, which previous speakers have already stressed on. And there are certain things called the QPOs, or the quasiperiodic oscillations. These are the oscillations of high energy X-rays, and they seem to follow a Q diagram, which was made famous by Fender and Belloni. and which shows that as with states, the jets also change with states. Similarly, the QPOs also change with states. Okay, so that it appears, that implies that accreting matter launches the jet. Now, moreover, jets appears to be launched from a region close to the central black hole. This is famous M87, and I mean, these results are with us for the last more than 20 years. Okay, so, and jets are ubiquitous. Okay, I mean, you can have, these are FR1 jet, this is FR2 jet, these are YSO jets, and you can see that the morphology of the jets are of a supermassive black hole and a jet from a young stellar objects are similar. Okay, and these are the microquasar GRO jet. Okay, so jets around black holes is potentially relativistic. Not always it's relativistic, but it's potentially relativistic. And terminal speeds are, some of the jets are inferred to be relativistic. For microquasars, this of course changes with this, with the spectral state. And jets are collimated. Again, there is a variation. There's a whole zoo of that, few less than the others. And the things that are not known about jets, how jets are formed and composition of the jet. I mean, the most famous is the Blandford-Znaick mechanism, but then you can also have jets around neutron stars, and some of them jets are very fast. I mean, some of the few Lorentz factor. So on those jets, the Blandford-Znaick mechanism definitely will not work. So it's probably a plasma effect, and of course the composition of the jet. Okay, these are the things that are not known. In addition, the low frequency QP is also correlated with the jet states. That's what we said just before. And the HD simulations we did previously show the general agreement, broad agreement with the observations mentioned above. However, this talk, we only focus on driving mechanism of jets. Okay. The important point to note is that the jets, so this is some little bit of background. The jets are launched from accretion disk, and close to the central object, the accretion disks are very hot. Okay, the electron temperatures can go beyond 10 to the power 9, and proton temperatures can be around 10 to the 12 or something. And the plasma around the compact, so therefore, the plasma around the compact object has to be fully ionized, and they are also thermally relativistic. I mean, if it is more than 10 to the power 9, then the electrons are definitely, then the thermal energy of the electrons are of the order of their rest mass, or if the proton temperatures are around 10 to the power 12 or thereabout, then again, it is the thermal energy is close to its rest mass. So if the gas is described by not only relativistic speeds, I mean bulk speeds, they are also described by internal speeds. These zigzag motions, the random motion of the gas particles, they are also, if it is relativistic temperature, they are also moving very close to the speed of light. And therefore, taking a Newtonian equation of state is not justified. You have to take a relativistic equation of state. Okay. What do we mean by that? We mean by that is that what is an equation of state? Equation of state is the average energy of the energy density of the gas, local average energy density of the gas. And for non-relativistic gases, what it is assumed to be Maxwell-Boltzmann, and the energy is non-relativistic. That is q squared by 2m, q being the momentum of each particle of the gas. But if we take the relativistic distribution and you integrate, I mean, take an average of all the energy, and then the integration will give rise to something like this. Okay, so this E is the energy density, rho is the mass density, theta is a temperature measure, and these K's are modified Bessel's function. Okay, and it was famously computed by Chandrasekhar long time back, and it was again regenerated by Singe and Cox and Giuli and so on. The problem with this RP stands for this Chandrasekhar equation of state. RP means relativistically perfect. It is expensive to implement in numerical simulation codes. If the simplest of hydrodynamic codes, the computation cost increases by 50%. Okay? And if you want to put more physics, I mean, it will get very slow, and therefore it's not very fashionable to use this RP equation of state in simulations. A lot of people have worked on this, and we also put our bit, and we proposed an equation of state, which is very good fit of RP, but it is algebraic in nature, and therefore it is easy to handle, and it doesn't, impose any computational cost to the numerical simulation codes. But we have used this for also analytical calculations as well. So this is the, if you, with that equation of state, if you calculate the adiabatic index, you will see it varies with temperature. The temperature here is around 10 to the 7, and here is 10 to the 13. And you can see that the adiabatic index goes from 5/3 to 4/3. Not only that, not only on temperature, it also depends on what kind of gas we have. If it is an electron-proton gas, then the variation is different. And if it is an electron-positron gas, the variation is different. Okay. So for electron-positron, it becomes 4/3 after it crosses the electron rest mass energy. And if for electron-proton, it achieves gamma 4/3 around 10 to the 13, or when it's above the proton rest mass energy, and so on. Okay, in this particular case, you will see this plateau here. That's because the electrons have become, in this temperature, electrons have become, in an electron-proton gas, electrons have become relativistic, but the protons are still not relativistic. So therefore, it is trying to be, flatten up, but then again, as we raise the temperature, proton starts to become relativistic. Anyway, we implement that. All right. Now, we are trying to discuss acceleration mechanisms. Now, the jet, when the powerful jets come in the Q diagram, if you look carefully, then the accretion disk is in the outbursting state, and it is basically the intermediate hard to soft, that region. So the luminosity is high, and and a lot of high energy radiations are coming out. So these intense radiations, can they drive this matter that is coming out, outflowing matter that is coming out as relativistic jets? The problem is, however, that if the matter is also hot there, so if the thermal energy is very high, then radiation driving is not very important. Additionally, optical thin jets are also subject to radiation drag. What is radiation drag? Radiation drag means that in optically thin jets, the radiation from the disk or the external radiation field will penetrate the jet, and the radiation field will also exist in front. So as the matter, the normal matter is trying to move in that radiation field, then the pressure, the radiation pressure and the radiation energy density will try to hold it back. Something like, if you throw a stone in air, then the air drag sort of holds it back, okay, because the air is in front and so on. Okay, and what about collimation? Okay, if you have radiation actually spreads, okay, but can radiation collimate? Okay, so because relativistic jets are also collimated. Magnetic field, on the other hand, ticks almost all the boxes for the jets, right? Like, they can accelerate, they can collimate, and so on and so forth. However, the MHD calculations shows the temperature at the jet base are really unreasonably high. Okay, that's a problem with MHD calculation. And also, it is intriguing that what should be the magnetic field configuration around a black hole, because black hole itself doesn't have a magnetic field of itself. And how to put that magnetic field inside a black hole, because the div B have to be 0. And again, with the spectral change, assuming that there is a magnetic field configuration, there is a magnetosphere outside the black hole horizon, how does that change? Okay, how does that magnetic configuration change with the disk spectral state? Okay, so we did something with relativistic MHD, powering of outflows of relativistic jets with magnetic fields. And we took the Koenig methodology of splitting it up into self-similar streamlines. Okay, so these are self-similar streamlines There are self-similar field lines. R means radial, and there are theta self-similar field lines, and all sorts of things are there. We took the R self-similar field line configuration. That means that along R it doesn't change. Okay, so if you can find one field line, then it's if we can find one field line, the other field lines will be self-similar. It will just scale up according to the scaling laws. Okay, and along that magnetic field lines, we solve the relativistic emission equations. Without gravity, it's only in special relativity. And then we impose our equation of state that we just described just now. And the problem with this is good in the sense that we can discuss how the jet is behaving far away from the black hole, where the gravitational interaction is not important. However, when we solve these equations without gravity, the problem is that the base velocities are also pretty high. So there is, I mean, if you don't have gravity, then you don't form the slow magnetosonic points, which will bring down the jet, the velocity to much lower values and will satisfy the accretion disk boundary conditions. But what was important is that first we can achieve very high speeds, okay, very high speeds. And okay, so these are the streamlines that we obtained. So here the B phi is changing, it flips, the azimuthal velocity flips. So if it is here, it is moving in this, rotating in this direction in anti-clockwise, and here you can see it is rotating in the clockwise direction. Okay, after it crosses the Alban point. Okay, and this is a top view of the same. All right. So, but what was important in that work is which we did not find in our hydrodynamic calculations, is the fact that why we should use this relativistic equation of state. Okay, this is a solution where the energy density, the magnetization, the current distribution, everything is exactly the same, except we have changed the equation of state of the gas. We have used our equation of state assuming an electron proton gas, and then we have solved these equations assuming the fixed gamma equation of state that is generally used, and we have used a gamma 5/3 and a gamma 4/3. The green is the gamma 4/3 and the red is the gamma 5/3, and we solved it. Okay, look at the temperature here. Okay, the temperature distribution. What we see here is that the green, which is gamma 4/3, has a lower temperature at certain region, and red, which is gamma 5/3, has a higher temperature. Okay, that should not be the case. If you look at so you see here for lower temperatures, the adiabatic index is 5/3, and for higher temperatures, the adiabatic index is 4/3, and others in between. So for everything same, gamma 5/3 should produce a lower temperature, and gamma 4/3 should produce higher temperature. It does not. Okay, so I mean, it basically, this is what the referee wanted to put. I mean, he or she wanted to us to compare with the fixed gamma equation of state, and once we submitted that in the paper, and the referee was excited. I said, "Oh, this is important." So anyway. So then, of course, we also checked radiatively driven jets. This is in GR, and this is with Comptonization and so on. So not just Thomson scattering cross section, but it's a Compton scattering cross section. Here, so if you do that, apart from that, we're producing very high speeds at large distances. What is also solved is that the temperatures at the base of the jet is fairly low. It's 10 to the power 8, 10 to the power 7. It can be 10 to the power 9, of course. But what the point is that these temperatures will match with the accretion disk conditions at those ranges, those regions. So so the point is that we did it, and it ticks not all the boxes, but fairly it is good. Problem, however, is this is steady state calculations. Okay, what happens if it is not steady state, if the radiation field is changing? Okay, so this is what we have done. We are doing it recently. It's still in the process of completion. It's not completed as yet.
You have 5 minutes.
Yeah, okay, I'm just done. Okay, so here you see this is a cartoon diagram of the accretion disk and the jet. Here we do not consider the accretion disk at all. Okay, it is just an auxiliary in the sense that it just gives the radiation. Okay, radiation field, and in that radiation field the jet expands. Okay, all right. So these are the equations of motions. This is steady state equation of motion I've put. I'm not the time dependent equation of state, but the point is that you can see here this is a radiation contribution. R1 is the flux of radiation flux, R0 is the radiation energy density, and R2 is the pressure, radiation pressure. The radiation density and the radiation pressure, they come with the minus sign, and it is and it's also multiplied with the flow velocity. These are the three velocity. So this is the radiation drag term that we have been talking about. Okay, all right. So here what we have done, we have taken an accretion disk. So this is the corona which is producing the high energy radiation, and this produces the low energy radiation. Okay, so now the corona has a median position. Okay, it can be a shock, it can be something else, there is centrifugal barrier or something else. Okay, so it has a median position. Now it is oscillating with this oscillation amplitude and this time period. Okay, and the corona height has a fixed ratio. Okay, and if you do that, then the radiation field is also changing. But the problem is that if the disk is at some position, okay, the outer edge of the corona is some position, then it takes time for the light to go and tell the jet that whether the disk has moved or not. So at a given snapshot of time, different part of the jet will see different part of the accretion disk. Okay, so this delayed effect we have put, and we show that if you implement that this is started with a steady state, and then we started to oscillate, and you can see this steady state jet did not have any shock, but here you can see that it is forming a shock at this certain time. Okay, the time is measured there. Okay, and so these are the various snapshots at various time, and you can see that how it is changing in time. So and the bottom panel shows the energy density, the pressure, and the flux, radiation flux, and how it is changing. When the radiation, the jet is very slow at these regions, you see the energy density has really piled up. Okay, so that sort of slows down the jet. All right, here is another parameter. I'm just finishing it up, and you can see there are multiple shock-like structures that they are traveling. Okay, and if we can make them collide, it's going to open up something else as well, colliding jets and so on. So this is very exciting, and so I'll just stop here. Thank you.
Thank you, Indranil. Time for some questions. If you have a question, you can raise your hand.
I guess not.
Yes, there are some questions. Pratik, you can unmute and ask.
Yeah, thanks. So when you talk about how the high energy radiation, so up to high energies, what high energies do you actually see this radiation going up?
Here it doesn't matter. Okay, we have just dumped radiation, but from accretion disks, what we have seen that it can go to MeVs.
Okay.
And if you take larger and larger black holes, it can go further and further up.
Okay, I see. Okay, thanks.
Yes, next question is by Ranjit, you can ask.
Indranil, a quick question. I think you mentioned that when you're taking on magnetic fields, you can get very high velocities.
Yeah.
What is the velocity in gamma, and why doesn't radiation drag affect in that case?
No, the MHD is when we did MHD, we did not take radiation. So it's a two separate studies.
But then radiation drag should still occur, right?
Yes, radiation drag. But the point is, if you look at the MHD, so somewhere here it is approaching speed of light, right? Here.
Yeah, but what is gamma?
Gamma is the Lorentz factor, should be.
I mean, what is the value?
So it's around 40, 50, it can go up to 100, we have checked.
Yeah. But the radiation drag should affect this also, right?
Yeah, but the point is what it will all depend on the intensity of radiation there. If the intensity of radiation is not very high, it won't affect. Of course, we did not study the radiation MHD. I mean, radiation hydrodynamics plus magnetohydrodynamics. We did not do that. But around this region, I believe it will slow down. I mean, so the radiation intensity will fall a lot.
Okay.
Next question by Samik.
Hello. Am I audible?
You can ask.
Okay, sir. So, what is the effect on temperature by the magnetic field?
Effect of temperature on the magnetic field?
I mean, what is the effect of magnetic field on the temperature?
As such, nothing. But the point is, if you take magnetic fields, MHD simulation, so you have to bring that magnetic field down. I mean, if you are going closer and closer to the central object, you are bringing that magnetic field, right? And the gas will be confined in a smaller and smaller region, and that might be larger than, I shouldn't use the word larger, but it will be steeper than R-squared dependence. You understand what I'm saying? So for example, if it's a spherical flow, so the area would go like R-squared, right? It will increase like R-squared. Okay.
Right.
And then the density, of course, it will depend on velocity and everything. It will be like divided by R-squared. Okay. Now, if you have a magnetic field, okay, it has to be some sort of a dipolar or quadrupolar. But anyway, whatever it is, close to the central object, the cross section can decrease faster than R-squared dependence, and that shoots up. I mean, so you're confining the gas in a smaller and smaller region. Okay, so it's secondary effect, but it can increase the temperature a lot. That's what most of the MHD calculations shows. That okay, this is okay. Don't look at this because it is STR, means it is far away from the central object. But if it is 10 to the power 10 far away, you can imagine how high it can go up as you go closer and closer to the central object. Most of these MHD solutions don't mention this. They try to avoid this question. This is a big question. So probably some radiation hydrodynamics, as Ranjiv was trying to, radiation hydrodynamics will be very important at the base of the jet to reduce the temperature a little bit.
And just a small question about, you said that in the base of the jet, the temperature will be lower, right?
Lower than what we get in calculation, not lower.
Okay, compared to it is lower in the base part than the collimated portion. Like the jet is emitted.
Yeah, that will depend, right? That will depend where you are sort of pumping maximum energy. If you are really pumping a lot of energy away from the jet base, the temperature will go up. Okay, for example, if you look at this solution here, there is componentization here. So, so not only momentum, also energy is being transferred. And you can see at the base of the jet, the temperature is around 10 to the power 8, but it goes to 10 to the power 11, few Schwarzschild radius above. And again, then after that, it sort of decays. But now if you say I have a cloud here at say 10 to the power 4, okay, a dense cloud, and it hits the cloud, and the temperature can again go up. So it will depend on what kind of dynamics you are putting. These are the things we are studying at the moment, but as of yet, it's not, reportable. The results are still not reported.
Okay, thank you.
Okay, we do not have time for more questions. So let's thank Inonil. And next speaker will be Shilpa Sarkar. She will talk on 2 temperature advective accretion disks around black holes. So it's a 15 minutes talks, 12 minutes talk plus 3 minutes for question and answer. I'll give a warning at 10 minutes. Shilpa.
Yeah, thank you. So you can see my screen?
Yes.
Yeah, hello everyone. So I'm Shilpa and I'm from Aries. The topic I am going to discuss is about 2 temperature advective accretion disks around black holes. So black holes are a type of astrophysical objects which are generally called as compact objects. So they are named such because of their extreme small size, which is quantified using a ratio called the compactness ratio, which is the mass of the star to the radius of the star. So because of their extreme small size, they exhibit a phenomena called accretion, which is the accumulation of matter from the surrounding medium because of the strong gravitational potential energy. So this accretion is the best known mechanism till now, which can explain the high luminosities of AGNs and X-ray binaries. So these accretion models have been developed from time to time and have been improvised to match with the observations from the new generation telescopes. But few basic elements that has to be kept in mind are that the black hole accretion is necessarily transonic in nature. So we should consider transonic flows. And to capture the effects of strong gravity, we should work in the GR regime. And the third point is that to study these transrelativistic accretion flows, we need a relativistic equation of state. So to explain this further, generally matter is said to be thermally relativistic when the thermal energy is greater than the rest mass energy, or kT by mc square is greater than 1. So not only the temperature but also the mass of the species is important. So in 2009, Chattopadhyay and Ryu gave an equation of state for multi-species flow along with variable adiabatic index. So this is the expression of the equation of state, where E is the energy density and summation is the summation over the ith species. So apart from that, advection dominated flows should be considered because it induces stability in the system. Also, these all elements should be kept in mind, and the equations of motion should be solved self-consistently. But the question now comes that what are the types of species that should be present in the flow, because it will determine the thermodynamics of the system. So there could be protons and electrons present inside the flow, because hydrogen is the most abundant element in the universe, and an ionized plasma should consist of protons and electrons. And as we know, their masses are very much different. So the question is, what should be their temperatures then? So in most of the astrophysical cases, it has been found that these accretion flows are of 2 temperatures. So reasons why a flow should be of 2 temperature is basically because of their different masses. Secondly, it has been found that in most of the astrophysical cases, the Coulomb coupling timescales are greater than the infall timescales. That is, the timescale in which the electrons and protons, they talk with each other and settle down into a single temperature distribution. So before that, it falls towards the black hole. So in other words, it means that the electrons and protons are thermally decoupled, and we have 2 different temperatures in the system. Apart from that, electrons are the main radiators, so the temperature of the electrons will deviate more from the protons. So these types of flows are actually generic in nature, and since we have information of the electron temperature, it helps us in computing the spectrum. So spectral analysis of the 2 temperature flows is popularly done. So these types of flows are actually realistic in nature. So apart from the spectral analysis, these 2 temperature flows predict electron temperatures, which is greater than the rest mass energy of the electron. So production and annihilation of electron-positron pairs, they play an important role in the accretion physics of the system. Apart from that, the accretion disks are the bases which drive the jets. So the outflows can also be composed of these types of species. But before going on to these types of things, special attention is needed. So most of the works in accretion flows, they consider one temperature, that is the proton and electron, they settle down into a single temperature distribution. So they have one particular theta, which represents the temperature. So in one temperature flows, they have a unique sonic point and hence a unique transonic solution. But in case of two temperature flows, we now have a additional temperature. But unfortunately, we do not have any principle which is dictated by plasma physics, which can constrain the relation between these two temperatures. Or in other words, we do not have any extra equation which can couple these two temperatures. So the equation set is incomplete, and we can see that the system is degenerate, which in other words means that for the same set of constants of motion, we have infinite solutions. So this hint of degeneracy has been given a lot of times in literature. So it was in 1980 when few authors, they parameterized the proton and electron temperature to obtain a single solution for a given set of constants of motion. So not only in 1980s, many works still now, they parameterize this proton and electron temperature to obtain a solution. Similarly, some arbitrary values of either proton or electron temperature is assumed at any boundary of the flow. Even some specific relations were introduced in order to constrain the relation between a proton and electron temperature. So this heating of the electron is equal to the cooling. But in other way, it actually means that the electron advection is ignored in the system. So these choices and assumptions are actually arbitrary, and a solution obtained from these assumptions will actually give us a wrong information of the system. So we, for the first time, attended and solved the problem of degeneracy and proposed a methodology to remove this degeneracy. So from the first principles, we obtain a measure of entropy, which we call the entropy accretion rate form. So this is the first law of thermodynamics in the right-hand side, where first is the energy equation for the proton and the second is for the energy equation of the electron. But as we can see that there are heating and cooling terms and a Coulomb coupling term actually coupling these two equations. But remembering the fact that near the horizon gravity overpowers any other interaction, we can actually assume that the infall timescales are very much shorter than the cooling timescales or any heating timescales. And the infall timescales are also shorter than the Coulomb coupling timescale. So the Coulomb coupling can be assumed to 0. So these two equations then be integrated to obtain an entropy accretion rate form for two temperature flows, which is strictly valid near the horizon. So validating then obtaining all the entropies of all the degenerate solutions from the second law of thermodynamics, we saw that nature prefers a solution with maximum entropy, and hence we constrain the degeneracy. So we validated this entropy accretion rate form first onto spherical flows around black holes. So this is a typical Mach number versus radius plot, where the solid line is the accretion solution and the dotted is the excretion solution. So we are not considering this is only a mathematical solution. The star is the sonic point. So near the horizon, so we identify this solution using a proton temperature or electron temperature also. So now changing the proton temperature to 5 into 10 to the power 11, we get another measure of entropy. Again, changing, we get another measure of entropy. Not only other solutions exist, but we can see that the entropy maximizes at a certain solution. So by we select this solution to be the unique two temperature solution for the given set of constants of motion. Now extending,
you have 2 more minutes. 2 more minutes.
Okay, so extending our work to more rotating flows around black holes, we can see that these are the constants of motion, and for the given constants of motion, we have a host of solutions, some passing through outer, some passing through inner, some even occurring shocks, and this is the spectrum. So the spectrum also changes, but so there is a need to constrain the degeneracy. So from the entropy accretion rate formula which we gave, we saw that the entropy maximizes at a certain solution, and this is the correct spectrum, and this is the correct solution for the given constants of motion. So now coming on to the contribution of different regions of the black hole disk to the total observable spectrum, we can see that we have shaded the regions, and corresponding to the shaded regions, we have plotted the spectrum. So we can see as we move far away, the luminosity decreases, but very near the horizon, the luminosity is smaller than the corresponding radius. This is mainly because of the strong gravity of black holes, which actually captures most of the photons, reducing its luminosity. And tabulating all these luminosities, we see that 90% of the total luminosity actually comes from a region less than 10 Schwarzschild radius. Now, as we change the black hole mass with the accretion rate, so we plot the luminosity versus accretion rate. So for a given accretion rate, these are the sizes of the circles is actually represent the different black hole masses. So for a given accretion rate, we change the black hole mass, we can see that the spectral bandwidth increases, but the shape of the spectrum doesn't change much. So this for a higher black hole mass, we have enough amount of emission in the radio fluxes, which is the basis of probing higher mass black holes by the EHT. So this spectral index is represented by alpha, and this doesn't change much if we change the black hole mass. Whereas for a given black hole mass, if we change the accretion rate, we can see the bandwidth remains the same, but the spectral index changes a lot because of the a large amount of inverse quantization. Now, if we plot the efficiency, which is represented by this L by m dot c square, we can see that with the increase in accretion rate, the efficiency increases, tapering off at 10%. But with the change in black hole mass, it doesn't change much. So the efficiency for all, it actually means that if we change the black hole mass, we change the system quantitatively, but qualitatively the system remains the same. So we proposed actually a general method, a novel methodology to constrain the degeneracy, because it is necessary to get an exact picture of the system. And these temperatures are actually conducive for the production of pairs, and pairs actually play an important role in shaping the spectrum and in the accretion physics also. And it is believed that the shocks in accretion disks mainly give rise to the outflows and jets. So there is an increased probability in the outflow because of this shock front. So we want to study these things also in the two temperature flows. So thank you.
Thanks, Shilpa. Time for a question. Yes, Ranjit.
Shilpa, yes, nice, but I got a little confused in one of the approximations which you're doing.
Yeah.
Is that the Coulomb timescale is long for both the protons and electrons. My understanding is that the Coulomb timescale for two temperature disk will be different for the protons and electrons.
Yeah.
And for protons, I can understand because they're so high temperature, the timescale should be very long compared to the radioactive timescale. But the electron timescale would be a factor of 1,000 less or something because of a difference in temperature.
Yeah, the timescales of this, you mean this Coulomb coupling, right? This assumption, you mean?
Yes. So you have a time. So in your closed to black hole, you neglect those terms of Coulomb interaction.
Yeah.
Cooling term.
Yeah.
And that is the timescale argument. That is when the Coulomb timescale will be longer compared to the advection timescale.
Yeah, because mainly, as you said, the electron-electron collision timescale are shorter, so they will settle down into a single temperature first, which the electrons will collide and they will settle down. But the Coulomb collision means that the electron and proton, they interact and settle down. So that timescale is larger.
No, that timescale I'm saying is different for the electrons and protons.
But Coulomb coupling timescale is the interaction timescale between electron and proton.
No, it's the energy of the proton divided by the cooling rate.
Mm,
And when you have electron divided by cooling rate, same cooling rate, so there should be factor of 1,000 different between them.
No, Ranji, it's an energy exchange term between electrons and protons.
Correct. So the time scale is defined by the.
Yeah, if you calculate, all of them are much larger than infall time scale near the horizon.
Yeah, this is a plot like if the black one means the red one is the infall time scale and the Coulomb coupling time scale is represented by a blue line. We actually can see that the Coulomb.
This is for a proton.
No, Coulomb coupling time scale is the time scale of interaction between electrons and protons, not a particular electron or proton.
We'll discuss this online, but offline then.
Yeah.
Okay.
Yes, we do not have time, but Santabrata, if you have a very quick question, you can ask. We cannot hear from Santabrata, so since there is no more time, let's.
Am I audible now?
Okay. Ask, please ask.
So first of all, this is a very nice talk. I must appreciate. I mean, this is really.
Thank you.
Just one question. So your entropy maximum plot that you showed, did you check how spectral behavior changes when you are looking at the different entropy distribution?
Yeah, this is the spectrum. In the right hand side, you can see these are for the given constants of motion. These are the spectral change. So we have a low luminosity system and some.
No. What I'm saying here, your temperature is changing. What I'm saying is, when you said that you identified a maximum entropy solution just to find out a maximum entropy solution and you resolve the degeneracy.
Yeah.
Did you check the spectral behavior, including the degeneracy, how it is changes?
Spectral behavior, you mean the spectral state?
I mean, so for every accretion solution, you can calculate a spectra, right? So if you include all degeneracy allowed, and you see how the spectral behavior changes between a degenerate solution and the maximum entropy solution, what is the difference?
I guess if I understand your question correctly, so this
can
is.
Can you go to the slide? I can explain you where you identified the.
Well, we are already 4 minutes past, so very quickly in 1 minute, if you can do.
Less than 1 minute. So here you see the distribution of entropies. So for okay. I think your temperatures are different, so that you cannot do. So even if you calculate the spectral behavior for all cases, so the solutions that you showed me, it is the case, right?
Yeah.
Okay. Got it. Okay, thank you.
Hello, Sudhir.
Deepak, can you share your slides?
Okay.
I'm sorry I announced it, but perhaps I was muted.
Okay.
So it will be talked by Deepak Devnath. So 15 minutes.
Could you see my full screen?
Yes.
Okay. I will be talking about. Hi. First of all, I want to thank the organizer for giving me opportunity to for the presentation. I'll be talking about the accretion ejection properties of short orbital pure transient black hole. Transient black hole are very much interesting object as these sources stay most of their lifetime in quiescence phase. Sometimes they become active and show the activity. And so during that phase, they passes through different spectral state and they show QPO. Some in some state they don't show QPO. They show the outflows and all the things are related to the different spectral state. The short orbital period also carries some special characteristics I will be talking about, that we generally see the X-ray from the accretion disks, also from the jet. More precisely, if we tell that we see jet from the base, base of the jet. We see X-ray from the base of the jet. As you know, as jet moves away due to the adiabatic expansion, we see other low energy band of the radiations. And the jets are mostly active in the AGNs, but the stellar massive black hole also show the jet. Jet may be velocity may change from up to the speed of, it may move up to the speed of superluminous speed 0.99 c, and sorry. Oh, recently we started. We tried to fit spectrum, the black hole spectrum with the two component model after inclusion in an aggregate table model in space, and we have nicely fitted the spectra as in the morning lecture Professor Chakraborty said, and for the fitting spectra we need only four basic flow parameter: the Kepler and Dix rate, circular Hero rate, location of the shock, and compression ratio. And if mass is not known, then you can make free of the mass as a free parameter, and model normalization needed. The normalization of this model is not like other model normalization, as the normalization depends on the source indigenous parameter like the mass of the source, distance, and the disk inclination angle. So we found that this model normalization should not vary on a daily basis. Why this model normalization should not vary? Because that as during the outburst that flux changes, but we don't require to change the normalization on a daily basis. We generally see normalization varies in a narrow range or in a constant range, constant narrow near about a constant value, because that flow parameter changes accordingly to match the not only the shape of the spectrum but also that intensity of the spectrum. Recently, the Corbel et al. Tried to find the universal correlation between the radio and X-ray luminosities, and they found the beautiful the relation of the radio and X-ray, the luminosities, and which is around the 0.7, 0.6 to 7, and they termed as universal correlation index. But there are some sources which does not show this follow the universal correlation index. Those they termed as outliner, and interestingly we have noticed that these outliner sources are short orbital pure object mainly. So these short orbital pure sources also have another characteristic, that they do not show all the spectral state, canonical spectral state during the outburst, like the hard intermediate, soft intermediate, and soft. So they in this spectrum, in outburst of this short orbital period, we generally do not see soft spectral state, and we may see that sometimes soft intermediate spectral are also missing. So we made a harder spectral state or intermediate spectral state during the object. So these objects are very much interesting. So what we have tried to, we have studied some of these objects, like on the Maxi J1659 minus 152, Maxi J1836 minus 194, on the Swift J1753. All are short orbitals. We just look around, and on the only exceptional, these also the GRS 1716 last one on 249 is also short orbital period, but little bit higher than other object. This is the one spectra fitted with the TCAP model of the XRT, GSC, and BAT combined spectra. So this picture probably you have seen morning, that according to TCAP two component additive flow model, TCAP model, the base of the jet or symbol act as a base of the jet. So we see that jet from this the symbol. and up to the sonic surface, the density is higher, temperature higher. So we see the X-ray radiation from the base of the jet. And recently, it is well known that when we study the outflow rate ratio between the outflow and inflow rate RM dot, with the compression ratio, it has been observed that maximum outflow rate observed in the intermediate state, and more precisely in the hard intermediate spectral state. And nature of the jet are different in different spectral state. In the soft state there is no jet. As the compression ratio increases, we see that the jet appears, and in the hard state maximum compression ratio is there. We see compact jet, and in the intermediate state we may see that the blobby jet or discrete jet. And these jets are also correlated with different spectral state, that in the hard state as I told, and in the soft state there is no jet, and origin of the jet are different of these in different spectral state or different nature of the discrete or compact jets. And in this so we have observed that that model normalization, when we fitted all the data of 2005 outburst of sweep J1753.5-0127, we observed that the model normalization is found to be higher. We require higher normalization to fit the spectra in some observation, around 5 observation in the initial rising phase of the outburst. Otherwise, it was roughly constant. So then we compared the normalization, the variation with the radio flux. We found that the radio flux also was higher during this phase. So in this model, the TCAP present model, we have not included that the contribution of the jet in the model. So this higher normalization could be due to the effect of the jet. As you told, that jet also emits X-ray. So extra to compensate the contribution of extra X-ray flux from the jet, one may require higher normalization. So what we have done, we have selected the minimum normalization from our fitted, and we found that on the minimum normalization, the red point, the radio flux also lower. So we assume that on this day the jet contribution minimum or negligible. So we refitted all the refitted or not refitted. We have frozen that normalization at that lowest value, and we just calculated the flux from the base period spectra, and that flux actually give us the inflow contribution or disk contribution. And after here is the flow chart. How we calculate that, separate the jet flux from the total observed X-ray flux. And first we fitted the spectra with the free normalization. This gives the total X-ray flux, which contains both jet and X-ray, jet X-ray and accretion disk X-ray flux. And then we observed on the lowest n value, normalization value, and we freeze that normalization value and to calculate the disk component X-ray flux, and this disk component X-ray flux if I inflow is subtracted from the total observed X-ray flux, these X-ray flux, the fitting with free normalization, and we obtain the outflow X-ray flux. This is the one.
You have 2 more minutes. 2 minutes.
Okay. Another one method we recently done, we have fitted the spectra with TCAP and another additional the power law model. This additional power law model gives the contribution. In the earlier method we have not fitted. We just put we have to put the lowest normalization and freeze that value and calculated from the base fitted spectra. And in this model we have added one additional normal power law model. This power law model gives us the contribution of the, assume that jet X-ray looks like power law, and this gives a contribution of the jet X-ray, and TCAP gives the disk X-ray. So combining this gives us the disk plus power law separately with the 2 component of the model, the TCAP and power law. And interestingly, we found that in this method, the TCAP model parameter has not been changed significantly. The change is negligible. So we studied the different objects. Just I'm going to quickly. We have separated the this component, X component, and we compared with that, and we have separated, and we studied comparative study of those X-ray, and we found that the percentage of the jet contribution in the in total X-ray, and we also studied that correlation between the this X-ray and this X-ray, outflow X-ray, and total X-ray with the radio flux, and from there we try to find the properties or the nature of the jet is compact or blobby. And for example, for this also that we found the tight the correlation in the hard state, and whereas the intermediate state the correlation was weak. So we concluded that in the hard intermediate state for this source that jet was blobby in nature, and in the hard state the jet was compact. Another source, I'm going quickly. Another source, MaxCJ, also we have studied, and we have separated both Dix and X-ray flux, and we found that we have calculated the contribution of the jet component X-ray flux with the total observed X-ray flux, and we also tried to find the correlation for this source in the both Dix and hard and intermediate state. We found that the jet was compact. I'm going skipping this. And this is another source where during entire outburst, hard state was observed, and this source of two outbursts we have studied both the outbursts, and we found that during these sources in both the jet was compact in nature. There is another source. My student in the next talk that Kaushik will talk about the details. I'm not going into details. I just going to the conclusion, a summary that the two we try to find the separate that the jet component X-ray flux and jet component X-ray flux from the total observed X-ray flux with the constant normalization method. The two methods we have used, and we found that the jet that after the separation, the accretion Dix and jet X-ray and total X-ray flux, the contribution was that total X-ray flux are well correlated with that radio component X-ray flux, and from there we have studied the nature of the jet, or compact or discrete, and this short orbital period. Interestingly, we observed that during the short orbital period, although these sources show steeper correlation, and when correlated with radio flux with the total X-ray part, but when correlated with that outflow or jet component of X-ray flux, we found that these objects also falls in the universal correlation relation that correlate with 0.6 to 0.7 when correlated the outflow flux with the radio flux. That's all right. Thank you.
Thanks, Deepak. We can take one question because there is not much time. There is a question. Okay, if there is no question, let's thank Deepak.
Okay. Thanks, sir.
And the next talk will be by Kaushik Chatterjee on X-ray properties of black hole candidate XT J1752-223 during its 2009-10 outburst. This will be a 12-minute talk plus 3 minutes question and answers. I'll give a warning at 10 minutes. Kaushik.
Okay, can you hear me?
Yes.
Can you see my presentation?
Yes.
Okay. So, good afternoon. I'm Kaushik Chatterjee. I'm working as a research fellow in Indian Center for Space Physics under the supervision of Dr. Deepak Devnath and Professor Sandeep Kumar Chakraborty. In this presentation, I'm going to talk about the X-ray properties of the black hole candidate XT1752-223 during its 2019 outburst. So these are my two outlines. I'm first going to discuss about the spectral and temporal properties, and then I will go to its jet properties. So the source was discovered in 2009 by RXT, and there was various works that have been done on this source. Hapoznikov et al. Reported that this source has an M-type donor star and its mass was 8 to 11 solar mass, and the binary has an orbital period of 6.8 hours. However, they also reported about the spectral nature of the source, and they showed that the source has gone through all the defined spectral state of a black hole candidate. In 2013, Brockshop et al. They showed that there was persistent radio and jet emission from throughout the outburst. Now, this motivated us to spectrally analyze this source again, because we know that in soft state there is not presence of jet, and they reported about the presence of jet. So we using RxT-PCR data, we analyze this source. First, we show the temporal properties. Here I show the light curve variation from MaxiGSC and with that archival daily average light curve. And in panel B, I show the hardness ratio. From the variation of this hardness ratio, we can see see that the throughout the outburst, the source has gone through soft, all the defined spectral states of a black hole candidate, including the softer state. We also show the hardness intensity diagram or Q diagram, where the points A, B, C, D, E, F, they represent the transition dates between various spectral states. Now, we also estimated the dynamic photon index of throughout this outburst using RxT ASM data. This theta or photon index, this gives the hardness of the spectrum, and it is given by this formula where C and B is the number of counts in the 5 to 12 and 3.5 to 5 keV energy bands in ASM data, and ECEV are the average energy in those bands. So according to Ghosh and Chakraborty 2019, if theta goes below -1, then we can say that the source has made a transition towards softer states. So for this outburst, from the figure in panel A, we see that in the middle phase, the source has gone below, the dynamic photon index has gone below -1. And this is where we think that the source has gone to softer states, and this is also supported by the hardness ratio variation. But to be more precise, we have to do spectral analysis. However, we also try to find the quasi-periodic oscillations from the source, and out of all the observations, we have found QPOs on 6 days, and some of them shows harmonics, and the frequency of those QPOs showed monotonic increase in frequency. Now, the spectral analysis is done mainly using the phenomenological disk blackbody plus power law and the physical two-component advective flow or TCAP model. Now, here are the disk power law results, and we see that at the start of the outburst, the power law flux is dominant over the disk blackbody flux, and the photon index was also low. This tells us that the source was in hard state at the start of the outburst, and as the outburst progressed in the middle phase, the soft flux or disk blackbody flux became dominant over the power law flux, and the source gradually made a transition towards the intermediate and then towards the softer states. And at the back end of the outburst, it again went to the opposite sequence, and again went back to hard state in the declining phase. Now, we have also done TCAP with TCAP analysis. Now, this has been broadly explained by Professor Chakraborty in the morning. So there are two components. One is the subkeplerian flow, and other is the Keplerian flow. The subkeplerian flow, being less viscous, comes to the black hole much quicker than the Keplerian component, and it forms shock, and the boundary is known as the Senbal or centrifugal pressure supported boundary layer. Now, in TCAP model, there are mainly 4 parameters: two rates and 2 shock properties, and also we can estimate the mass of the black hole using this model. However, there is also one parameter, normalization, which mainly depends on the source's mass, distance, and inclination angle. So during an outburst, when these properties of the source does not change, the normalization tend to stay in a very narrow range, very narrow range or close to constant. So however, if there is phenomena like jet or disk precision where these are not taken into consideration in the current TCAP fields file, it can vary in a broad range. For this outburst, it has varied from 0.51 to 3.10 because there was presence of jets throughout the entire outburst. And here we show the TCAP results, and I will show the normalization variation later. Here from the to accretion rates and the shock properties, we can see that the source was in hard state at the initial phase, and then went to intermediate state, and then in the middle phase of the outburst it went to softer states, and then it went back in the opposite direction. We also estimated mass of this source. The most probable mass has been estimated to be 10 plus minus 1.9 solar mass. We also show the accretion rate ratio intensity diagram. This also looks like a Q diagram, which designates the transition day between various spectral states. However, here the point B is missing because in the PCA data, there was a gap of 2 months data due to sun constraint. So we could not spectrally analyze the source using this archival data. So the first transition day from hard state to hard intermediate is purely done based on the temporal properties. Now, these are some comparative results where we show that the total PCU rate and the total disk blackbody plus power law flux and the total accretion rate from the TCAP model varied analogously. Now, come to the jet properties. We know that Shen ball being from Shen ball, the Shen ball acts as the base of the jet in TCAP model, and thermal pressure makes matter ejects matter in the vertical direction to the disk. And in the global inflow outflow solution, Professor Chakraborty established a relation where he related the outflow and inflow rate as a function or as a parameter as a function of the compression ratio. And in the left figure we see that as the source stay in soft state, there is no jet. Now as it goes to the intermediate states, the value of R goes to an intermediate value, and there the outflow becomes maximum. And this is also the case for jet, where in hard state the jet is compact, and as it goes to the intermediate states where the rates increase, we see more jet emission from the source. So we have estimated some radio X-ray fluxes using our analysis using these two methods, where in the first method we only freeze the normalization of the TCAP model and then estimate the inflow flux. As Dr. Devnath has already discussed that on the day where the normalization n is minimum, there is negligible contribution from the jet, and it can be taken as only the inflow flux. So freezing the normalization to its minimum value, we get the inflow flux, and when the normalization was free, we get the total X-ray flux, and subtracting we get the outflow flux. And in method 2, we have added an additional power law with the normalization, where we freeze the normalization.
You have 2 more minutes.
Okay.
2 minutes.
Okay. We freeze the normalization to its minimum value, and we add an additional power law and fit the spectra. Now this fitting, due to an additional power law, this takes care for the change for the jet components, and we see negligible change in the parameters also. Now from both these methods we estimated these fluxes, and from method 1 we see that the outflow flux varies. Outflow flux from this jet varies similar to the variation of the normalization and the radio flux. However, using method 2, where we have added an additional power law, we see that the outflow flux, the variation of the outflow flux is more analogous to the normalization and the radio flux than the method 1. We have also tried to estimate a correlation between this outflow flux from X-ray and the radio, and we found that from both these methods in panel A for both these figures, the correlation coefficient has been close to 0.6 and in second method to 0.7, and this stays in the standard correlation of 0.6 to 0.7, and we have also established correlations of other X-ray fluxes from the total X-ray flux, the inflow with this radio. So now I come to the conclusion is that during the whole outburst, this black hole candidate has gone through all the spectral state, all the defined spectral state of a black hole candidate, and this source has a mass of 10 plus minus 1.9 solar mass. And since the motivation of our work was to find if the presence of substrate was there, we have also tried to explain the jet emission mechanism in substrate. We think that in softer states, the disk was magnetically dominated, and when matter from the companion comes, it brings in a lot amount of stochastic magnetic field, and being due to azimuthal velocity, they forms uh, flux tubes, and when more amount of matter comes, this flux tubes collapses and ejects matter, which is the result of the flares as seen for this outburst in the softer states. So these are my conclusions. So thank you.
Thanks, Kaushik. Are there questions? If you have a question, you can raise hand or ask the question. Okay, Sheshadri Mojumdar, you can ask. Please unmute and ask. We cannot hear you.
No, I can't hear you.
Yes.
Hello.
Yes.
Yes. So, what is the confidence level of your mass estimation?
It's 90% confidence level.
Okay. Okay, fine.
Okay, all right. If there are no more questions, let's thank all the speakers of this session, and I'm handing over to Shashi.
Thanks, Sudip, for your contribution to chairing this session, and thanks to all the speakers of this first session for their nice presentations and discussions. And now it's a lunch break, and for the second session, we will again gather here at 2:30. So let's meet at 2:30. Bye.
Hello.
Good afternoon, Sachi.
Yeah, good afternoon. How are you?
It's doing fine. Maybe I can share my slide. Okay.
You can try, yeah.
You cannot start screen share while the other participants is sharing. Don't know who is sharing.
Okay. This is the host.
Yeah, something like that.
Yeah, they have put this.
Actually, this Zoom presentation, no, I mean, I'm having a lot of difficulties. I think whenever I tried to present, you remember this last JPC meeting. So everywhere I find the same.
Yes. Yeah. Hey, what happened to? Did you hear anything from them?
Oh, no. I got some unofficial message. They said that it should not be the part of JPC. It should be part of something like SSPO or something like that. Okay. So
it should go to science office, right?
I think they have recommended it, but I didn't find any official letter. Our coordinator informally told me, and I met him last week in a tea stall. So he said that this is the kind of news he got.
Okay. Actually, I heard from somewhere that you have another project on the same line.
Yes. It is going on.
Okay. So
See, I'll tell you the story. So this project I submitted, I think, almost 3 years ago. And it routed to many places and reviewed, and then again asked for revision. These things continued up to 2019 May or something. And then I again submitted, and meanwhile I submitted another project to directly SSPO, and that was selected. So
actually, there are other.
Sorry.
Other people here. Okay.
No, I didn't hear you.
There are several others like this already.
Okay.
There are several other people here, no?
Okay. Anyway, we'll talk offline.
Yes. Okay, so you can talk to Nandita.
Yeah. Actually, I'm waiting for official letter. Let me see.
Okay.
By the way, you are not the host, right? So host should be from Aries.
Yes.
By the way, how things are going on at your place? Yes.
On what? COVID?
Now only one issue, no COVID.
Do you know, can you guess one thing? I am at the moment COVID patient.
Sorry?
I am a COVID patient now.
You are infected now?
Yes.
Oh my God. But it looks like you are very, very stable.
So I am getting recovered. This is my 9th day.
So it looks like nobody will get away. I mean, everybody will be infected at some point of time.
So in my family, 3 people are infected. So the other 2 people, they have recovered. So I am in the process of recovery.
So did you travel anywhere in these days, or maybe?
No.
So it is internal, right?
No, actually, my wife works in IMD. Okay. So in her office, there are 4-5 cases that time.
Okay. I got the point. In our campus, many people are affected because they went for holidays in different places. Once they return, their infection is detected. And few students are also detected as positive, but it's not alarming still now.
Here the cases are very large and increasing every day. Even in our office, lot of cases. Every day 3-4 cases are coming.
Oh, that is a bit alarming.
Yeah.
But overall, suddenly the numbers increased.
Yeah. Actually, here the cricket match was there, and these political rallies are going on.
Politically, I mean, see the way everything is conducted, in Assam, in West Bengal. I mean, it's difficult to see. I mean, nobody understood, and in fact, nobody is understanding the gravity of the problem.
Yes. The people, like in the government, they are allowing all this thing.
Somehow, definitely, it is there. No, otherwise, how it is possible?
Yeah.
So already around our regions, all hospitals are completely full. So if someone is infected, it's very difficult to find a place for him in the hospital.
Actually, in my case, I had a high fever. Supposed to get admitted in hospital. But because of lack of beds, so I had to stay back at home. Okay.
So this is somehow, I mean, it's God grace that you didn't have any serious issue. I mean, if somebody is having some issues and requires some kind of medical support, it's really pathetic.
Yeah.
It's very, very difficult.
So nobody yet from Aries.
I saw one. I saw the mouse was roaming around, so that means somebody is definitely there.
Okay. No, I don't know.
No, I just saw in the screen. Possibly this host has to give permission.
No. I mean, it's all okay. Sachin and Santabrata, we are listening your conversations.
No. We could not check our slide sharing because the host is not allowing.
No. Okay. I see. Stop share. Yeah. Now, is that fine now?
Yeah, Santabrata can try sharing.
I think it is possible.
Yes. We can see.
Yeah.
Can you see?
Yes. Very much.
I'm absolutely tense because I changed my presentation to another machine because my original machine is not working. Zoom is not working for some reason. I don't know. So I'm not very sure everything will come appropriately or not.
You can check the slides.
So we have just click if your slides are moving.
Yes, that's true. Yeah, it's moving.
Yes, very much.
Yeah, the animations are also working fine.
Yeah, very good. So we have just a minute to go.
Yeah.
So still only 19 people total, including host.
After lunch, it is really difficult. No, people have to come and join. No?
Yeah, so good afternoon, everybody. Good afternoon, everyone. I welcome you all here again in the afternoon session of the third day of this workshop dedicated for microquasars and microblazars. And now I invite Dr. Sachin Nayak to chair the session and proceed ahead. Dr. Sachin Nayak, please.
So thank you, Sachi. So good afternoon, everybody. Welcome to the post-camp session on extra-binaries in the conference. So in this session, we have several talks, 2 of which are of 30 minutes each, and the rest of them are of 15 minutes. So in the beginning, we'll start with half-an-hour presentation by Santabrata Das from IIT Guwahati, and he is going to speak on role of pseudo potential in storing black hole and extra-binaries. Santabrata, this is half-an-hour talk, so 25 plus 5 minutes. I give you warning after 20 minutes. Okay.
Okay. Thank you, Sachi. I'm extremely happy that the organizer invited me to present my work in this 5 days long meeting. So I decided to present one of our recent developments about the pseudo potentials that we are working on. So this work is done with my collaborators. So he is the main person, my PhD student, former PhD student. Now he is a postdoc in IIT Indore. He is the lead person to work out everything. And Professor Debaprasad Maiti, Professor Sayan Chakraborty is my colleague at IIT Guwahati. And probably most of you know about Anuj working at URSC SRO, and Somir Mondol and IIST. So they are my collaborator. And the brief introduction of my talk goes like this, but I'm thankful to my previous speakers. Most of them have introduced the subject by and large in an elegant way. So I just here want to mention one specific point, that the sole motivation of all these things that we are working on is to understand a black hole. And the black hole is essentially characterized with only two parameters. One is mass and speed. So the ultimate goal to explore the black hole sources is in terms of their mass and spin. So with this, we proceed. So I find some places to be discussed from the historical point of view, the way the subject is developed. So one of the things that I will start from the energy budget of the accretion process, and what is its importance altogether when accreting matter falls onto a black hole. Something about 10 to 14% of its rest mass energy can be extracted depending on the spin of the black holes. So essentially, if you send some amount of matter, its potential energy will be acquired, which can be estimated something like this, and that will be converted to kinetic energy. Essentially, it will go to the thermal energy, and finally, we can see it in the form of electromagnetic radiation. So the bottom line here is, if you bring the matter close to the compact object, you can have a lot of energy in your pocket, which can come out in the form of hard radiation. So the thumb rule is, closer to the compact object, flow will be hotter and it will produce high energy radiation. So that is the primary motivation to study the accretion physics. And with this motivation, things started long back in the era of 1972-73 with the standard disk model. These two pioneers, they started the standard disk model with the configuration something like this. So the configuration is something like that. The disk is a collection of ring of matter, matter within the ring are orbiting in Keplerian velocities. The disk is essentially very cold. They move very slowly, and therefore they have enough time to radiate its binding energy. And also the disk contains a significant amount of viscosity. It has two roles. One of the role is it drives matter to the black hole so that the accretion is possible, and at the same time it heats up the matter. So with this, with this configuration of the disk structure, the electromagnetic radiation that we see, it comes in the form of a black body spectrum. So if you look at the accretion disk, Keplerian accretion disk is essentially composed of several rings of matter with increasing temperature as you go inside. So you can see the distribution of temperature is a monotemperature disk. And if you calculate the emergent radiation from the disk, it will produce a soft bump in this form. Now, one important issue here is this Keplerian disk is designed in such a way that it cannot cross the length scale within the 3 Rg radius. So that means the in principle, the Keplerian matter cannot fall into the black hole. And by definition, in fact, today morning also we have heard many times that the black hole solutions, if the matter needs to fall into the black hole, it has to be supersonic in nature. So in principle, the Keplerian flow cannot fall into the black hole. So this is a very important information we need to keep in mind. Now, even with this restriction, the Keplerian disk has an enormous success in explaining the quasar luminosity. But at the same time, it also gets criticism in various forms. One of the important criticism it receives that it cannot explain the spectra of stellar mass black holes. For example, the spectra of the Cygnus X1 could not be explained, particularly the high energy part. Sachi, am I audible?
Yes, Santam.
Yes.
I'm sorry. It's very difficult. It's a communication is so. It's a one-way process. Sometimes I feel I'm not audible. I'm sorry.
No, don't worry. Go ahead.
Okay. So this high energy part, it's very difficult. It is not possible to explain with the Keplerian standard the disk model. So then there was the obvious question came in minds, people's mind, that how to produce these hard X-rays, particularly from the stellar mass black hole sources. So Theta 2 came into the picture in 1980, and he along with Rashid Shunaev, proposed an idea that if some hot electrons is surrounded around the compact objects, particularly black hole or so, some amount of photons, soft photons can be Compton scattered, and once it is Compton scattered, it can produce a high energy photons. The idea is something like that. If a hot electron is present here, so low energy photons is coming, it is being reprocessed and produce hard X-rays. Now the next question comes, where does this Compton scattering occur? So you need some amount of matter which is very hot. So it should harbor some hot electrons, and not only that, so this particular regions has to be optically thin, so that the hard radiations, once it is produced because of the reprocess through the inverse Compton process, it should immediately come out so that we can see it. If it is got absorbed, we cannot see. So from that, many people started with phenomenological study describing the presence of hot electron regions. Typically, people are calling it the coronal regions. But here, we would like to point out that this coronal structure can be obtained from the solution of hydrodynamical equations or macrodynamical equations. So the advective accretion process here works in this following way. It's basically the competition between the gravitational and centrifugal force. Essentially, the presence of centrifugal force stabilizes the disk at some point of time. So if you see the force profile of these two class of forces, one is the gravitational force, another is the centrifugal force. The gravitational force goes like this way, and centrifugal force goes like this way. Now, if you fix certain angular momentum, particularly if you keep on tuning the angular momentum, then you can see that the force profile can be obtained like this. And very close to the black hole of the order of, let's say, few rg, and very far away from the black hole, the gravity always wins over the centrifugal force. But at the intermediate region, you can see these two forces are comparable. Now, the level of comparison, it strictly depends on the angular momentum. So this is a very crucial point here. So if you supply matter with the appropriate angular momentum, then what can happen? The flow at the intermediate regions, let's say few social radius, the flow will be slowed down and density will pile up, and this structure of the disk will look like something like this. So this is the disk structure. Flow is moving from this regions, and at this region flow fills the centrifugal barrier, and because of the centrifugal barrier, flow slows down and makes a torus-like structure, essentially we call as the post-shock corona. And this is the byproduct of the governing equations. So the slowed down matter, as I said, it produces the effective boundary layer, basically behaves like the boundary of the black hole. Now this slowing down process cannot be indefinite. At some point this process has to stop, and once the Rankine-Hughes shock condition satisfied, this discontinuous transition results in shock transitions, and these shock solutions are preferable when as the second law of thermodynamics supports it. Now, if this scenario is possible, what can happen? The low energy photon from the outer edge of the disk, these photons can intercept with the electrons, which are very hot in this region, and this is the ideal place of the inverse quantum process that we have already described, and it produces the hard X-rays. Now, this is the Keplerian accretion disk structure that I already described. Now, this advective disk dark structure with the post-shock corona, it looks like this. The matter is falling like this from the outer edge, and this is the torus-like structure. The effectiveness of this model is it produces a two-temperature disk profile. The outside is something similar to the Keplerian profile, and inside is the two-temperature profile. And it not only produces the soft bump, it also maintains a strong hard tail. So this model has a potential to take care the several observational features, and these shock scenarios in astrophysical context is seen in many occasions. For example, in supernova explosions, bow shocks out of the moving stars, and bow shocks in the jets. So this shock idea is not really a uncommon phenomena. So it's possible to see in the accretion disk physics as well. Now, if we look at the observational point of view, in many black holes X-ray binaries, they keep on showing the spectral state transitions in few days of time. For example, this source, it shows the spectral state transition in only few days time, and some sources they show the very sharp peak in the power density spectra, in the frequency power density spectra space, and with some harmonics. Now, these are the observational features, and these observational features, can be taken care of by the numerical simulation of the kind of model that we are describing. If you see that the simulation result, which I display in the right hand side, you see here the spherical geometry is used, and the matter is injected from the outer edge with certain set of input parameters. And you can see that it's nicely produces the coronal structure here, and from the coronal structure, some amount of matter is ejected away from the surroundings of the compact object, and also the coronal structure is not a steady structure; it is a dynamical structure. So these dynamical features possibly responsible to cater the spectral state transitions for black hole sources, as well as the QPO features. Okay, so now meanwhile, it is already discussed in the literature that the black holes inherently they are rotating in principle, because in universe nothing can be static. Some amount of angular momentum must be associated with all objects, and some of the black holes should be some of the black holes are reported as rapidly rotating. So a general relativistic treatment is definitely required to understand those black holes, particularly when we are talking about their spin and mass values. So what we did, we would like to study the hydrodynamics of these plasma in a stationary axisymmetric space-time, and this is the very standard equation set of equations. And if you look at these equations contains a viscous stress terms. We are not talking about any radiative process yet here, but still, believe me, this solution of these equations in K space-time is really challenging. It's a mathematically challenging task. Okay, so the alternative way is the pseudo-Newtonian approach. The pseudo-Newtonian potentials are believed to be a very important tool for the study of relativistic astrophysics, and it has been done since long. Since the Patinsky's time, since 1980. So these are the governing equations. I would ask you to pay attention only the first equation. The rest three equations are the standard equations, nothing special here. If you look at this term appears as the gravity force, and this phi, it's essentially is called the pseudo potential. Now, the Patinsky in 1980 proposed the potential in a very simplified form, which is what he proposed is something like this, with a singularity at r equal to 2. And these, once you write this potential in G equal to mdh equal to c equal to 1 unit, it looks like this. And obviously, this potential gives a very, very satisfactory result. People are very happy. And in fact, we also worked with in many occasions. For example, I show here one solution, accretion solutions, which is passing through the outer critical point, and then it is supposed to go to the black hole without any problem. But suddenly it finds a place for shock transition. It jumps into the subsonic branch, crosses the inner critical point, and goes into the black hole. Now, what is interesting here, you see, the branch which is plotted with a solid curve is containing the high entropy content. This morning, Shilpa is also talking about the entropy issues. So this is a very important concept that we must understand. Nature supports the high entropy solutions, so the accretion solutions is really preferred, and these calculations we have done using the pseudo-Newtonian potential proposed by Patinsky and Witta. And in the right-hand side, I show you, if you tune the flow parameters, for example, the accretion rate and the level of and the strength of the magnetic field, you can see the inner structure of the disk changes. So by tuning the flow parameters, you can control the geometry of the post-shock corona. And since post-shock corona is responsible, according to our model, to produce the high energy radiation, so the emergent radiations and its various properties can be examined just by tuning the accretion flow parameters, for example, accretion rate and the magnetic field, particularly in this case. But with the tremendous success of the Patinsky with the potential, many people proposed the pseudo potential, various pseudo potentials for rotating black holes. For example, the Artimova et al. They proposed one potentials. Then Bani Broto Mukhopadhyay, he also proposed one potential in 2002. And also Sandeep Chakraborty and his student Soman Mondal also proposed one pseudo potentials. But all these potentials, they have their own limitations. Particularly, you can see that this potential, when they propose, they categorically mention this potential is valid only for black hole spin less than equal to 0.8. That means these potentials are not suitable to take care of the maximally rotating black hole systems. And you know that as the space spin parameter increases, the space-time geometry becomes more and more non-linear, and many more gravitating effect becomes completely different in nature when black hole spin increases. Different in nature means its effect becomes very, very different, very, very intense rather. So keeping these things in mind, what we did, we make a comparative study of all three potentials. Basically, what we did, we solved the accretion solutions, taking all three black hole potentials for rotating black hole, and we keep the black hole spin same, and we compare the accretion solution for all three potentials, keeping all the flow parameters same. And you see that in the left hand side, all solutions are giving different results. Now, from here, it is very difficult to pick one. which one is giving the best one. So all three are equal probable, and all three are having certain limitations.
5 minutes.
Okay, I'm almost. I'll try to wrap it up within 5 minutes. Yeah, and we calculate the critical viscosity parameters for all these potentials, and we find that not a single potential can address shock solution beyond certain spin values. So this is a serious limitations of these potentials. Once we realize these deficiency, we worked out to identify a more generic effective potentials for rotating black holes. So we found a black hole potential, effective potential for a very general space-time. And for K black hole, there's potential reduced to this form. It looks like somewhat big and messy, but if you see this potential in the equatorial plane, it becomes really very simple potential. So in the equatorial plane, it looks like this. And one interesting feature that we realized is, if we expand this potential for a Schwarzschild limit, and we find a series expansion, and the first leading term we identified as the same potential that Paczynski and with the proposed. So our potential carries all the higher order corrections for at least Schwarzschild limit, and obviously in other non-zero spin values, the potential will give a decent result, more accurate result. So obviously we try this potential to study the two temperature solutions. I'm really thankful that Shilpa saved a lot of my time because I don't need to introduce what is two temperature flow, because she gave a nice introduction about this problem. So I will directly go into my results sections. So only thing that I would like to do is that our model assumptions is that we consider the steady flow, the axisymmetric viscous two temperature advective flow, and obviously we included magnetic field as well. And as I said, because of the mathematical difficulties, we did not carry out this problem in pure general relativistic framework. So we use DTMC potential. And we also use the relativistic equation of state proposed by Indroda and Professor Ryu. And the energy beta is very straightforward. We use the viscosity to heat up the ions, and the coolings of ions is because of the Coulomb coupling and the inverse Bremsstrahlung process. The electrons are heated just by the Coulomb coupling, and the electrons are cooled by the relevant cooling processes like Bremsstrahlung process, synchronous synchron process, condensation process. And the magnetic field we approximated following the work of Machida and Oda. They did some numerical simulations and pointed out that the toroidal component of the magnetic field is most relevant and most dominant in the accretion disk for certain scenarios. So we adopted their magnetic field structure, and we obtained the additive accretion solutions for extremely rotating black holes. So in the top left panel is showing the Mach number profile and all other associated profile. For example, this one is the velocity profile. This one is the polytropic index profile for electron and ion. You can see that the ions remain almost non-relativistic throughout the length scale. Apart it is going towards the relativistic regime very close to the black hole, but the electrons is by and large maintaining the relativistic profile. And you can see that the temperature profiles of the electrons and ions. And we also calculated the total emission spectra for these solutions, and you can see that various contributions of radiative processes. And the black card is showing the total emission spectra. We calculated the photon index of this spectra, and we found it as gamma 2.11. And later, we also tried to explore the effect of accretion rate on the disk spectrum, and you can see that the disk spectrum, how it is modified with the increase of accretion rate. And also we got the photon index different for different accretion rates. And we try to see the variations of the photon index as well with the accretion rate for various magnetic field cases. and this is the profile. We see that as the magnetic accretion rate increases, the photon index decreases as a whole. So this is my last slide, and I will conclude it here. I think I am within the time. Okay, thank you.
Okay, thank you so much. Time. So I see one hand raised by Indranil. So Indranil, can you unmute yourself and ask the question? Indranil. Hello.
Hello, Santo.
Yes.
Yeah. Sorry, I spoke a lot without unmuting myself.
I also did this morning.
Anyway, you commented that you compared these three pseudopotentials, right?
Yes,
one by Artimova, one the other with Chakraborty, the other with by Bani. The Artimova never claims that they cannot go up to 0.9 or something, beyond 0.9 spin parameter, while they don't have a coupling term, the angular momentum and flow angular momentum and spin angular momentum coupling term. While the same problem exists for Bani's case as well. While Chakraborty claims that he cannot go much closer to 1, I mean, extremely spinning black hole, but he has the coupling term. So, do you in your potential have a coupling term?
No,
the black hole spin and the
So among these three potentials, only Chakraborty Mondal potential has a coupling term.
Yes.
Now,
I'm talking about your potential.
No, our potential is, so these are the potentials. These potentials are not derived from the hydrodynamics point of view. These are the potential was proposed. Obviously, they have some physical intuition behind it, but the potential I'm talking about, this is the potential. It is a derived potential. Derived means, I'll explain you.
I know what you have done. Basically, you have you wrote the two equations of motions and you matched. I mean the relevant terms.
Yes.
I'm not talking about that. What I'm trying to say is, for example, what I mean to say is, so if you have a coupling term, then if you are say you are shooting prograde particles, okay?
Oh, okay. Oh, Indra, I think I got your question.
Yes.
Just I will explain you what I think. What you are saying. Oh my God, I am going back. I'm sorry. Yeah, if you look at maybe the simple one, if you look at this, so this is the form of the effective potential. Okay. Now this is the spin. AK is the spin, and this is the lambda.
Term. Okay.
So we didn't manipulate anything. It came automatically, and we found that this coupling and everything is already inherently present.
Okay.
And the most important potential is, see, if you look at the first one, you take any kind of black hole space time, you put the appropriate value of the metric component, you will get the potential.
Okay. Yeah, it's fine. I'm good.
Hello. Is there any more questions? I don't see any. Okay. So if there is no more question on this, thanks to Santa. And let's move to next lecture of this session, study of microquasars with relaxed criteria of astrophysical observatory by Professor J. Yadav from IIT Kanpur. Dr. Yadav, this is 30 minutes.
Can I share my
please,
screen now?
Yes. So 25
Can you see my screen or no?
Yeah.
Not yet.
Visible. But
Can you see?
Not your presentation. Your screen visible.
No,
yes.
screen is no screen. Screen was visible.
It is coming. Yeah, it's coming now.
Yes, your screen is visible. You have to go for full screen mode.
Yes.
No, but can you see the first page? Associate
Yes.
species. Yeah. Okay.
Yes,
Fine.
it's visible.
All right.
So after 20 minutes, I will give a warning. Just 25 for presentation and 5 minutes for discussion. Okay.
This is 25, right? 30 minutes, right?
30 minutes, 25 presentation plus 5 minutes discussion.
Fine.
So after
So I
20 minutes,
thanks organizer to invite me for this talk, and there has been good talks in the morning and now this session from Ranjeev, Sandeep, and Mayuk and other people. So of course that is just introduction. I will be talking about more on observation part. So what I will focus, the major progress in the study of microquasars happens after 1995, of course, during RXT-PCA era. I will discuss some of the results. Then associated LXPC has some better points to study these radio and disconnection. I will highlight that. And I will present at least few examples, simultaneous observation, and some of the results of associated LXPC. In the morning session, there was discussion like state transition mechanism, which launches the jet and those things. And of course, when this appears and not appears, we don't understand. So I will try to touch those points a little bit and let us see what we get out of it. So first, coming to the associate thing, of course, we all know associate. Of course, associate provide wider range to study the X-ray property, almost from say 0.5 or lower to hundreds of keV. So that is one part, and especially LXPC. It provides much better efficiency, about 20 keV, and that is very, very important for the jet in the sense it is supposed that there are soft dips. So how soft dips? Okay, I will show you what is the difference between say RXT observation and associated LXPC observation. If you see the efficiency wise, of course, you can see that above 20 keV, there is a big difference in efficiency. And here, there is one class, theta class in GRS 1915 plus 105, which is observed by RXT and LXPC. And I just want to point to this HR2. This is nothing but non-thermal to thermal emission ratio. And you can see it is around 4% here. This is what is the soft dips where radio jets are supposed to be ejected. So they measure at this level, 0.04. And in LXPC, the same theta class we observed, and it is about 12%. So that is the accuracy. That is coming from the efficiency, and it has been now known from the observed QPO, variation in QPO and the spectrum, that this is very, very important for spectral analysis. Now to show that you believe what I'm saying, this, if you say HR1, it is similar in both. That is this here, this part, okay? It is quite similar, okay? And profile you can see here. So this is what I wanted to stress, that in fact I will show you also some results how it is different from RXT PCA. Now I'm coming to some basic. Of course, this was seen by this was shown in the morning by Mayuk. So just to show you the time scales, okay, for microquasar and quasars. So in that category, microquasar is much better. What you can study in say half an hour. That is what I will talk about. We will talk about how many types of radio emission we have from microquasars. So the phenomena of half an hour will be say hundreds of years. That is really not so easy to study, and here you can study. So this is the point I want to stress upon, and of course it comes major emission agent X-ray. That is one part. Now coming to the as I said, that major progress in microquasar, especially black hole binary, it came in RXT-PC era, and this is some of the sources. This is some of the sources, and which are shown here, and not all we know the orbital parameter, but now we know much more, something like almost 40 sources. Out of that, Fender et al., I have not written here, Fender et al. In 2019, no, 2009, in 11 sources out of 14 outbursts, he concluded that peak radio emission comes at state transition from hard to soft. So that, of course, it was not simultaneous. It was some sorts of hour difference in observation, but that was important observation. Now I'm coming to this is the most active source, GRS 1915. It is very active in X-ray and very active. This is X-ray from ASM counter, and this is in radio. You can see the activity, various activity. I will come to how to divide into. I will discuss in a minute, but I want to stress here the importance of all sky monitors here. If we have all sky monitor, that helps in a big way in the study of microquasars, because that can provide simultaneous X-ray data. So in future mission, I think we should have that. Of course, the major progress started in RXT-PCA era. That was in 97 FLIR activities. That was also in IXC, Indian satellite. And say within few months, there was such FLIR activity which showed the radio emission, and that is called beta class, X-ray class. Here, what I wanted to mention here, this is what is black is the X-ray curve here, and this is hard dip. You can see from hard, as I mentioned in the RXT, around say 12%, and this is what is the soft, and where ejection of matter is there. That is what the conclusion. So infrared, of course, has no delay time, but radio emission has a delay time. If I take here, mass is ejected from the disk, then radio peak comes here. Of course, it is particular wavelength, okay? Because for different radio wavelength, it will vary. I will come to that point also. I will discuss a little bit. So this was for beta class. That is a radio class. Now it is, we agree to this point. And there is also a theta class, which I showed you in the beginning, theta class X-ray light curve and hardness ratio. And here also we see something like around 40 milligensky type of radio flares. Now, if I take the, for example, this length of the hard dip, and if I correlate with the radio luminosity, then this is some sorts of, plot. So this at all, there is some correlation here. Of course, there is no physical reason for this, but one can say this is what the stored energy that comes in radio. And this is the light curve for beta class and theta class. Santosh has done this, and he put this in their soft dips, which is very clear. For hard, it is hard component disappears. That is what he wants to show here from the ratio. So it was some sorts of, we agree to this, that theta in beta class, that is a radio class, and we almost agree that at what time the matter is ejected, and it is where the soft dips are produced, whether it is in the theta class, this is beta class, or in theta class. Now, same thing, of course, is possible in AGNs, and this is the picture of 3C120. But as I said, time is a big issue. This is almost by 4 years. So in 4 years, they can see that there are dips, and what they claim, this is soft dips with the 4 radio jets coming out. So of course it doesn't match completely, but that is what the errors in the measurement. But this is what, of course, consistent with the AGNs. But such measurements in AGNs will be very, very difficult. This viewer also you have seen in the morning. I just want to repeat in this that this is the hardness of X-ray, and here the intensity of X-ray, and this is Q diagram. These people assume, and they say this here are the jets. Most of the jets comes here. So this is what they call, in fact, jet line they call like this, but most of the jets are seen only in high luminosity. So far I don't know any jet is seen in the lower luminosity. Most of the jets are seen here only. Now persistent emission, of course, has been seen here along this, okay, here, and in here not very clear. If it is mostly radio quiet state here. So the same picture Santosh has put in a way that when he says this is persistent emission, of course this is connected, coupled with the radio, and you can see continuous one. I will come to first classification of this one with more properties, and then this is discrete jets, like every hour, like in theta or beta classes. And if there is a matter, there is a shock, and then you have large jets. With this picture, of course, if we classify what type of radio jets we get in black hole binaries or in microquasars, the first is persistent emission. It is up to 10 to 100 millijansky. It has been seen in many of the sources in AGNs, and it is very correlated with the X-ray flux. Mayuk in the morning, he presented graph. Of course, it shows 2 tracks, and these 2 tracks is because we don't understand really accretion disks so well. Okay, like in GRS 1915 plus 105, there is hard states, okay, or there is SPL state, but there is also plateau state, and both are hard state. But then radio emission will be different. So I believe this is coming from these 2 tracks, or more scatter there is coming from what we understand the different X-ray states. So then I will go to directly third one, transient. This is what I talked about with theta class and beta class. It is the intensity of radio jet is 20 to 200 millijansky every half an hour or so time scales. Compact object is less than 300 AU for GRS 1915, only observed in GRS 1915 plus 105. And this is quite simultaneous observation is there. Superluminous radio jets, as I said, this is up to 1 millijansky, but say, this is I am talking about GRS 1915 plus 105, but say in Cygnus X3 it goes up to 20 jansky. And it times the length scale 400 to 5000 length scales. And here, of course, I will be talking about at least simultaneous observation for GRS 1915 plus 105 plus Cygnus X3. Now, one point I have to really make it clear. In case of persistent emission, disk and radio jets are coupled. But in case of superluminous radio jets and transient IR and radio jets, the jets decoupled from the accretion disk. So if you want to connect the radio flux with the accretion jet property, you have to connect it with the accretion disk before it decouples. And that is what really produces a lot more problem. So from this, then of course I will be talking about this GRS 1915 plus 105 in Cygnus X3. As GRS 1915 plus 105 is very active, and Cygnus X3 has the strongest radio jet in our galaxy. Of course, we have studied from GMRT, and when bubble eject from the accretion disk, we can talk about adiabatic expansion, and we can talk about delay in different the emission of radio in different wavelengths, and we can reproduce the delay time. That much we can do. Now, if we talk about very large radio jets in GRS 1915, 105, here there is two such radio flares in October 1997, January 1992, at a gap of almost 2 years. You can see similar behavior, and here it is produced, large radio jets. So we have to study the property of accretion disk here in this region and couple with this radio here, because here once this whatever disk portion or disk part is ejected, it is decoupled from the accretion disk. And here it gives really strong correlation. If you say that this property here, X-ray energy or timing of the X-ray energy, or even the absorption column density for this, it gives very strong correlation with the radio here. I'm talking about this large radio relativistic jets. Here is the correlation with the total X-ray before it decoupled, and this is the radio. It shows for total 8 large radio jets. Good correlation. And here, of course, timing property of the radio and timing property QPOs in disk, they are also well correlated here. But surprisingly, if you talk about the absorption column density, okay, with the peak of radio flux, okay, that is also well correlated. So now I'm coming to the Cygnus X3. This particular black hole binary is buried under a lot more mass, okay, from the companion. It is very close, 4.8 hours orbit period, and really we don't know about much, okay. Even X-ray should be coming reprocessed one, okay. So in this case, to find out when new jet comes, okay, it is very, very difficult. And this is what is the picture of 2nd April 2017, very large jets, almost of say 20 Jansky. And with LexPC also said, we planned in advance this particular observation. And some result, I think Mayuk presented some of the results here. This was the time, at this time, what we are observing. Okay, this was the time starting on the 1st April and going up to this. And we clearly say where radio intensity increases and when it decoupled, we can see this. Interesting part of this, here we discovered a new X-ray class that is very high state, which had a hard component with gamma 1.5, very hard. And if we extrapolate this to radio, we can explain the power of the radio. So that was really first simultaneous observation in X-ray and radio. Of course, it was by chance because it is very, very difficult to plan. But there are certain things, of course, one can understand, like these soft dips which are produced here. Or you can see here, okay, soft dips, okay. That is one signal that a large radio jet may be coming, but not always. Like in this case, it was not here, okay. There was something here, okay. Like in previous case also you can see here, there was not that. So it's not always, but usually it is the case. Now I'm coming to the other observation from Astro XPC, and this is the theta class I presented. Here it is much better than what we were getting from RXT-PCA. If you say this is what is the soft class, soft dips, where mass is ejected, you can clearly see the non-thermal emission is dropped by a large factor. But in the hard part, you can say it is only the hard component, non-thermal emission, that is dominating. So that really clearly supports the picture what we had for a long time.
5 minutes.
So how much time I have?
5 minutes. 5.
All right. Okay. So I will do before than that. Okay. So this is what I'm. So what I think is that next week.
I think you should plug in the charger.
Pardon?
Your battery is drained out. You should plug in the charger, otherwise it will turn it. It will turn.
Okay. Just a minute. Yes. You can see that, right? Okay. Great. Thanks. Yeah. So this was the point to say. So I am putting my conclusion here. Okay. Also said XPC instrument is well suited for the study of microquasars, as it can provide wide band spectroscopy and fine tuning, especially the higher efficiency at above 20 keV, because that is important when you want to quantify the soft dips which are supposed to be associated with jet emission in microquasars. Now the hard part is this X-ray and radio connection for superluminous jets, or even for other jets. Okay, you need to have simultaneous observation, and I think we have radio observatory, and now with associate we have X-ray observatory, and so we should plan and do this, because that can really bring very important things which is lacking, that how jets are produced. Okay, so with this, of course, I stop here. Thank you.
Okay, thank you very much. So any questions on this presentation? Please raise your hands, or I can start. So now I don't say anything, but I have a small question, but rather query.
Yes.
Can say. So
Yeah.
You have well summarized the existing knowledge on GRS computing system side, the radio, infrared, and also the lead, and different classes, everything. Whatever you know, you have well summarized. So the title of your presentation is like a study of microquasars with like PC. So I don't know whether any coding related kind of observations during particular type of exercises have been planned, or are you planning to have, so that you want to address something which has not been addressed yet with RHT or other earlier observations? Any such a program coming up, or can you comment on this?
Yeah, that is Sachin, that is right thing. Yeah, we are, of course, we would like to have that. But you know that GRS 1915 plus 105 now has, or it is going to quotient state. Okay. And during last almost 2 years, although it was many times in SPL state or very high hard states, but never went into plateau state. Because that was the time one can really plan. You know that when you expect large radio jets, of course we would like to do if source comes to life, But I think we should also concentrate, I will say, Sachin, we should also concentrate not only this GRS 1915, we know something now with other sources, okay? If they come to radio and we know they may come in radio jets, we should do it simultaneously. Yes, we definitely plan for other sources, yes.
Thank you. Yeah. So, any questions on this? Okay, so actually I'm happy to see so many results on GRS 105 and X-ray. Basically, they're using extra-galactic nuclei. Congratulations, that. So thank you very much, and for your group also. So nice results.
Thank you, thank you, thank you.
Thank you very much.
Thank you,
Now we'll move to next speaker. The talk will be for 15 minutes, and it will be on the long-term X-ray flux distribution of stimulus X1 using RST and MAX-T observation by Kavita Dekar from State University. This is a 15-minute class, so 12 plus 3 minutes, 12 minutes for presentation, 10 minutes for discussion, and I'll give you a warning after 10 minutes. Kavita, it's for you.
Okay, sir. Thank you.
You can start.
Okay, sir. So is my screen is visible?
Yes, yes.
Hello?
Yeah, it's visible.
And am I audible properly?
Yes, everything is fine. Yeah.
Okay, sir. So I can go ahead.
Yes, please.
Okay. A very good afternoon, everyone. I am Kavita Dekar from Tejpur University. So I would like to begin the talk by thanking the organizing committee for giving me this opportunity to present our work. And today I'll be talking about our work of long-term X-ray flux distribution of black hole X-ray binary Cygnus X1 using RXT, ASM, and MAXI observation. So this work has been carried out under the guidance of Dr. Jahir Shah and Professor Ranjit Mishra and Dr. Ghazi Amin Ahmed. So as all of us already know that Cygnus X1 is one of the most powerful and persistent galactic black hole binary system. It has been a prime target of most of the X-ray observation from the time of its discovery. And recently, Miller et al. Had re-estimated the mass of this black hole, which is about 21.2 solar masses. So this source Cygnus X1 shows variability at different time scales from milliseconds to years at X-ray energies. So the X-ray emission of Cygnus X1 falls into distinct spectral states. One is the hard state with low luminosity and hard X-ray emission. And this hard state is dominated by a non-thermal component, which can be modeled by a power law of index less than 2.0 and an exponential cutoff at high energy of 50 to 150 kV. And the another state is the high soft state with high luminosity and soft X-ray emission. And this soft state is characterized by a thermal dominated X-ray spectrum and is power law emission with a photon index of greater than 2.5. And the terminology low hard and high soft state is based on the long-term monitoring of the source Cygnus X1 in the energy range 1 to 10 keV. So above 10 keV, the state get reversed. That is, the higher flux values correspond to the hard state and the lower flux value correspond to the soft state. So one of the interesting features of this source is that it often undergoes transition, that is from hard to soft state or soft to hard state, and at the time of this transition, the source is found to be in an intermediate state with X-ray spectral properties lies between the hard and soft state, and this transition makes Cygnus X1 a suitable source to study the intermediate state. So the motivation of our work is to find out the different probability distribution correspond to the different spectral state, that is hard, soft and intermediate state, and to examine the nature of the intermediate state to find out whether it is a distinct state or just an extreme version of hard or soft state. So to understand the flux distribution of Cygnus X1, we have used the publicly available light curve from RXT ASM and from MAXI. So the light curves from RXT, we have used the RXT one-day average light curves, which were obtained during this time period, and the MAXI light curve were obtained during this period. So the light curves from both these instruments are available in 3 energy bands, A, B, and C. But for our work, we have considered only B and C band. B and C band, since A band can be there may be some variable absorption in A band. So since Cygnus X1 is known to have at least 2 distinct spectral states, and its flux distribution would also require more than one component to describe it, and in order to characterize the probability distribution of the source, we have created a normalized histograms of these light curves, and to reproduce the shape of these light curves, we have defined 2 probability distribution. One is the Gaussian distribution and another one is the log normal distribution. So this log normal distribution is nothing else where this variable x is replaced by a logarithm of x variable is replaced by logarithm of x. So we have defined 2 probability distribution function, and for the double probability distribution function we have chosen 3 combinations. So they are like log normal plus Gaussian 1, log normal plus log normal 1, and the Gaussian plus Gaussian 1. So this is the normalized histogram which we obtained from RXT ASM one-day average light curve. So the histogram binning was chosen such that each bin contained equal number of flux points, and since the source is simultaneously observed in B and C band, and the fraction of time it spent in hard and soft state is same for both the bands, therefore we have carried out simultaneous fitting of B and C band with double probability distribution function to ensure similar contribution of respective components from B and C bands. So here we can see this is the red solid curve and this black test curve represent the best fitted probability distribution function. So as I have already mentioned, we have used 3 combination of this double probability distribution function, but out of these 3 combination, this log normal plus Gaussian 1 had given us a better fit with a reduced chi-square of 1.20. So here I have shown only the best one, and again, I would like to mention this is the best fit, the log normal plus Gaussian fit, and this dotted curve, the black dotted and this pink dotted curves represent the individual log normal and Gaussian component to fit the histogram. Similarly, this is the normalized histogram for MAXI light curve. So here also we have used these 3 combinations, and out of which this log normal plus log normal 1 had given us a better reduced chi-square, a better fit with a reduced chi-square of 1.06. So here also this red solid curve and this black dashed curve represent the best fit, and again the black dotted curve represent the individual log normal component. So from this two histograms, we can see the lower flux values of B and C band in case of RXD, and the lower flux values for RXD, for maxi B band correspond to the hard state. And in the maxi C band, the higher flux value correspond to the hard state. This is because the energy range of maxi C band is is above 10 keV, which is 10 to 20 keV. So for further study, we have also used the state definition of RXD, ASM, and MAXI given by Greenberg et al. So these are the state definition. So by using this state definition, we have separated the light curves into the hard state, hard, intermediate, and soft state. So in this table, we can see the number of points and the number of points per state and the corresponding percentage. So in the RXD era, the source stayed in the hard state for most of the time, and in maxi era, the source stayed in the soft state for most of the time. So this implies a behavioral changes of the source in the time scales of a decade. So after separating the light curves into hard, soft, and intermediate state, we have graphically we have plotted this one. So in this correlation plot, this top and this right panel again represent the best fitted histogram for RXD B band and RXD C band. And in the central panel, we have plotted the data corresponding to the different state in different colors. So this one for hard state, this for intermediate state, and this green one represents the soft state. So after separating this data into this different state, what we have done, we have included the data corresponding to the intermediate state to hard state and the soft state, and calculate the average of fluxes. So here we have plotted the average of fluxes for the hard state by this red point, and the average of the soft state with this yellow point, and the average of fluxes for soft plus intermediate with this blue points. So from this plot, we can see the and again this horizontal and vertical bands represent the centroid values of the components which we use to fit this histogram. So from here we can see the average of the flux values for the hard state coincides with the best fit centroid values. And similarly, the average of the soft plus intermediate state is much closer to the best fitted centroid values as compared to the average of fluxes of soft state. Similarly, this one is for the maxi data. So here also this top and right panel represent the histograms with the best fitted probability distribution function, and the central panel we have plotted the hard state, intermediate state, and the soft state with different colors. Again, this represent the average of fluxes for hard state, and the average of fluxes for soft plus intermediate, and then for soft state. So here also and this horizontal and vertical bands represent the centroid values which we have used to fit the histogram. So from this plot also we can see the best fitted centroid values for the hard state coincides with this average of fluxes of the hard state, and the average of fluxes for soft state is much closer in case of maxi than the average of fluxes of soft plus intermediate state. So from these histograms and this correlation plot, it can be seen that the hard state of thickness x1 is better fitted with a log normal distribution for both MAXI and RXT data. But for RXT ASM data, the soft state is better fitted with a Gaussian one. And for the MAXI data, the soft state is again better fitted with a log normal distribution. So the log normal distribution in the hard state may indicate the variability of the source seems to be determined by a multiplicative process, but the discrepancy in case of the soft state may be because of this presence of the larger fraction of intermediate state in case of RXTE as compared to the MAXI data. So we have also tried to fit this histogram using a 3-component model, but which again suggests which didn't give us any good result. So this further suggests that this intermediate observation may not be a separate spectral state, rather it represents a transition between these two states. Or it can also be, it can be summarized by as this way, that the flux, maybe the flux distribution of intermediate state may not correspond to a Gaussian or a log normal, and instead it could be some arbitrary function, which again may depends for how long the source stays in this transitional state. So with this, I would like to conclude my talk. Thank you all for listening.
Thank you. So any questions? Any questions? Yeah, there is one question from yes, Marga. Yes, can you please unmute yourself and ask your question?
Hi. I was wondering, like, what could be the reason behind like discrepancy in the duration of intermediate state between RXT and MAXI observations? And also, there was a common interval for RXT and MAXI when both were on. So, do you see any like similarity in the percentage of intermediate states in the common duration?
Okay, so I think I don't exactly know what is the reason behind this discrepancy in this intermediate state. And can you repeat the second part of your question?
So was there any overlap between ASM and MAXI so that if it is there, we can compare like if there are.
I think so. The data which we have considered in our study for RXT, it's up to 2009, and for MAXI, it's just started from 2009 to 2018. So there's no overlapping.
No, but
in this
ASM
data
was active till 2012, if I'm not.
Yeah, because but after 2009, the data was deteriorated, so we didn't consider that part. Yeah.
Okay, like if you get some time, then you can maybe check if it has something, if it can
yes.
Tell something about this, because it will be very interesting to see if the source has overall reduced its time in the intermediate state since that epoch, or it's just some systematic feature which you like which is not being modeled correctly. Like if that discrepancy could be removed, then that will be great, I guess.
Okay, that's a very good suggestion. We'll try to do that. But from literature, it has been advised to not to use those data for RxDSM after 2009. So I don't know. Maybe we'll discuss about it.
Okay, thanks.
Okay, thank you.
So this shift back monitoring data is not useful in this kind of analysis.
Sorry, sir. Can you repeat it?
Shift back, actually, the 50 kV monitoring data. That's not suitable for this kind of analysis.
I'm so sorry, sir. I couldn't hear you properly. I'm so sorry.
So my point is, in your analysis, why did you use shift back data also, along with MAXI and RxDSM?
Okay, so can you repeat it? Actually, I find it very difficult to understand what you are saying. It's
like RxDSM or
I think Kachi is saying that what about Swift bad data?
Sorry. What about?
Swift back data.
Also, okay. We haven't considered that data in this study, but yeah, the Greenberg et al. They have considered by studying this sweep path. So I can't comment anything about that. I'm so sorry. We haven't considered the sweep data. So, sir, are you suggesting us to consider that data? Is that your question?
I think that's not my point. Whether it is advantageous or disadvantageous, I don't know. You might have thought about it. That's what I wanted to know. Okay, that's okay. Right. So, any more questions from you? Okay, so since no, so thank you, Kavita, for this presentation. We'll move to next presentation of the session. Yeah. So next will be by Sneha. Sorry, you can. Yeah. Sneha Modani from Christ University. The title of the presentation is Comprehensive X-ray Study of 4U 1957 plus 115 using AstroSat, Swift, and NewStar. So again, it will be 15 minutes talk, 12 plus 3. So after 10 minutes, I'll give one. Okay, Sneha? Yes.
Good afternoon, all. Is my screen visible? Am I audible?
Yes, everything is fine. Go on.
My name is Sneha Prakash Mudambi from Christ Deemed to be University. Today, I'm going to present a talk titled Comprehensive X-ray Study on 4U 1957 plus 115 using 3 instruments, AstroSat, Swift, and NewStar. This work I have carried under the supervision of Professor Shivappa Gudanava from Christ and Professor Ranjiv Mishra from Ayuka, Pune. This is the outline of my talk. Moving on, first I will tell you what are these black hole X-ray binaries. Black hole X-ray binaries are closed binary system which hosts a black hole and a companion star orbiting around the common center of mass. This companion star could be of a high mass or low mass main sequence star. In extreme cases, it could be a white dwarf system also, but here in this case, we are considering a high mass or a low mass main sequence star. It predominantly emits in X-rays and sometimes in radio in the form of jets. The X-rays are emitted due to the extraction of gravitational potential energy of the infalling matter. The luminosity of these systems are of the order of 10 to the power of 36 to 10 to the power of 38 ergs per second. So the two figures, what you see on your screen, the first one, the top right, is the artist impression of a black hole, which is accreting matter from a companion star. The grayscale of the picture is, which you see in the bottom right, is more relevant, which shows which part of the accretion disk emits what part of the electromagnetic spectrum, something Professor Mishra was talking to us today morning. Moving on, the source 4U 1957 plus 115 is a black hole candidate that has been in outburst since its discovery in 1964. Its optical counterpart V1408 Aquila was discovered 4 years later. Till date, no radio jets have been detected. The binary period from optical studies have been found to be 9.3 hours. Bales et al., he said the disk is axisymmetric, thin and uneclipsing. Because of this nature of the accretion disk, it leads to wide range of mass, distance and inclination estimates. The system is believed to host a rapidly spinning black hole. Novak et al. Considered 48 RXTE observations, and in his study, he said the spin of the black hole is varying from 0.8 to 1. And like I said, he considered the mass to range from 3 solar masses to 16 solar masses and distance 10 kiloparsecs to 20 kiloparsecs. In 2014, Maitra et al. Using Swift data reported an inclination of 77.6 degree with 90% confidence using Monte Carlo simulation. Further, Gomez et al. In 2015, using optical studies, they put the upper limit of the mass of the system to be 6.4 solar masses and inclination to be 12.45 degrees. So from this, we can see the kind of contradiction we have with X-ray measurements and optical measurements. Gomez et al. Also estimated the distance to be 20 to 40 kiloparsec. Coming to data and methodology, AstroSat has observed this source on 8 different occasions, and all this data is now publicly available. The figure what you see on your right on your screen, it is the maxi light curve plotted in the energy range 2 to 20 keV, and each of these vertical green lines, orange and red shows the observations of AstroSat, Swift as well as NuStar. NuStar is black, Swift is orange, and green ones are AstroSat. SXT observations were used for studying the soft X-rays. LAC-SPC observations were used for hard X-rays. We followed the standard operating procedure to extract SXT and LAC-SPC spectra, background, RMF, and ARF files. The latest background files for SXT were used. Spectral analysis we have done in multiple segments. First, we modeled the X-ray continuum with disk BB in the energy range 0.3 to 20 keV. Along with disk BB, the X-ray continuum was fitted with RELZIL, T-BAP. So what we found was the inner disk temperature was found to be around 1.67, whereas the disk normalization was found to be very small, the value, and also constant within errors. Then we studied the variation of asymptotic power law index, gamma, and inner disk temperature. The systematic error included for this analysis was 3%, and the model seems to be fitting the spectra well, as we found the reduced chi-square to be around 1.2 for all epochs. Also, the asymptotic power law index was found to be around 2.4. So what the two plots which you see on your figure on your screen are the one on your left, that is the asymptotic power law index versus the total flux for all the 7 epochs. You see that the asymptotic power law index reported a high value, the highest value of 2.82, whereas the lowest was 2.1. Similarly, KTIN, that is the inner disk temperature, recorded a lowest of 1.35 and the highest of 1.65. There seems to be some correlation also observed between the two parameters. Now, the second part was modeling the X-ray continuum with GRBs model. The combined spectra was once again modeled in 0.3 to 20 keV. Now, what we did was we fixed the distance and inclination to 22 kiloparsec, which we obtained from Novak et al., and 77.6 degrees, which we 0.6 degree, which we obtained from Maitra et al. Then what we fitted the spectra with different black hole masses. The reason was with GRBs, we were making an attempt to measure the spin of the black hole. As you may know, the spin is determined by 3 parameters: once the distance, the disk inclination, and the mass, mainly by these 3 parameters. So as I spoke to you as I discussed during the introduction, the distance to the source is still not well established. There is a wide range of masses that are available. Only the inclination seems to be reported fairly well. Therefore, considering different black hole masses, that is 3 solar masses, 5 solar masses, 10 solar masses, and 15 solar masses, we studied the spin, variation of the spin as a function of chi-square. So the figure what you see on your screen, the bottom figure, starting from left to right, it is 3, 5, 10, 15, the variation of the spin as a function of chi-square. We noticed that irrespective of the mass that was chosen, the chi-square versus spin plots seem to follow a similar trend. Also, for spin values around 0.99. So spin is in the decreasing direction, that is maximum, it's decreasing. This is 0.99, 0.95, 99858, and the chi-square is increasing. So at 0.99, the chi-square was found to be minimum. Therefore, what we did was, for further analysis, we fixed the spin of the black hole to be 0.99 and mass, we took it as 10 solar masses. The reason being, with 10 solar masses, it's easy to compare with other systems like LMC-X1. The rate of accretion was found to be around 0.215 times 10 to the power of gram per second. And with this model combination, we found the reduced chi-square to be around 1.4 for all the epochs. Now, coming to AstroSat and SWIFT observations. So when we were looking at the SWIFT catalog, we found that on 14th July 2017, both AstroSat and SWIFT had observed the source on the same day. So,
2 minutes.
Motivated by this, we plan to carry out simultaneous observations. And in this case, once again, we considered the energy range 0.3 to 20 keV. Same set of spectral models were used for disk and GRBs. Modeling the disk revealed the presence of a hot disk very close to the black hole. The power law index was found to be 2.61, and rate of accretion, once again, 0.201 times 10 to the power of 22 grams per second. Important thing is, similar trend was observed in the chi-square versus mass study. Sorry, chi-square versus spin. It's not mass, chi-square versus spin for different masses. Moving on, SWIFT and New Star. We also found one simultaneous observation of SWIFT and New Star on 20th October. In this case, with New Star, we were able to go further in the hard X-rays. We went all the way up till 50 keV. The same set of spectral models were used for the sake of uniformity. We found similar results. But in this case, when we were considering SWIFT and New Star, no systematics were considered. Whereas for AstroSat and SWIFT, we use 3% error. So this is the best fit spectra. On the top left, you see the best fit spectra of SXT, SWIFT and LAX-PC, whereas on the bottom right, you see New Star and you see SWIFT and New Star. So the black color here on the top right is for SWIFT, red is for SXT, green is for LAX-PC. Similarly, black here is for SWIFT, green is for New Star Telescope 1, and red is for New Star Telescope 2. What I've shown here is modeling the continuum with GRBs. Now, coming to the conclusions, the combined SXT and LAX-PC spectra were fit with disk BB along with other model combination to study the radiative properties of the black hole. The source was found to be in the high soft state throughout its course of observations by AstroSat, SWIFT, and New Star. The disk contribution was found to be 60 to 70% of the total flux. An accretion disk with inner disk temperature approximately 1.67 keV was found to be present very close to the black hole, which agrees with the previous results reported by Novak et al. A correlation similar to what we found of inner disk temperature and total flux was reported by Viginards et al. We made an attempt to constrain the black hole spin via continuum fitting technique as discussed in Mudambi et al. Spectrum was modeled using GRBs, like I said, with distance inclination fixed to 22 kpc and 77.6 degree respectively. We found the rate of accretion to vary between 0.164 times 10 power 22 grams per second and 0.240 times 10 power 22 grams per second, indicating that the accretor is constantly accreting matter. For a range of masses chosen, the spin recorded a minimum value at 0.99, probably indicating a rapidly rotating accretor. For a fixed inclination, mass and spin, source distance was found to be 17.55 kiloparsec. Further studies using simultaneous data from AstroSat and NICER may help in confirming the results presented here. These are the list of references which I have added in my talk. Thank you for your time and patience.
Yeah. So thank you. So questions. Actually, there is one in chat box by Radhika. So she wants to know, just before your results slide, if you possibly show whether there is a ratio or delta chi-square, moderate or especially fixed.
It is.
Can you go back to? Can you go back to the slide before, just before your results and discussion? Right?
Is this the one?
No, go back again. Then one more. Yes. Is this the one? Adita? No.
Sachi, can you hear me?
Yeah.
No, you have.
You, ma'am.
Yeah, Sneha, can you come down? Just one before the results. That is where you have shown the broadband fitting. S60 axis. Yeah, this one. So what is there in the y-axis of the bottom plot? But you are not mentioned. What is it?
That is actually normalized count. In both cases, normalized count. The bottom one is the reduced chi-square.
Reduced chi-square.
Chi-square.
The square. That's why the other is negative. So that's what.
Sorry, the chi-square.
Okay.
Okay, fine.
Okay, so there's another question from Jitesh. What is the Eddington limit here for the assumed mass? Eddington luminosity, or what is that? Eddington mass action rate. Which limit you are asking, Jitesh?
If I heard correctly, the question was, what is the Eddington limit?
Yes, what is the Eddington? See, for example, you use 3 or 4 mass, right? What is the Eddington for each case?
Sorry, Jitesh, I'm so sorry, your voice is not very clear.
The question is, what is the Eddington limit here for the assumed mass?
Okay, so the Eddington limit, we found it to be varying from 0.12 to 0.14. It's very low. It's not accreting closer to the Eddington limit. It's not even as bright as LMCX1. The fluxes are very low.
Okay. Okay. So there is one from Santa. Santa, can you please unmute and ask?
Yeah, I mean, these questions may be a very novice question. So I just want to know why your chi-square versus spin variation is almost independent of black hole mass.
This is something we found actually.
That I understood, but can you give some physical understanding? I mean, is it expected, or usually you see that you are measuring the black hole spin, and as far as my understanding, so these two parameters, mass and spin, they're connected. I mean, if you cannot fix one accurately, it is difficult to fix another one.
Exactly.
And the method that you are saying, that you take the minimum chi-square value, and that one is almost independent of black hole mass, although I could not read out the numbers because someone, maybe my screen is not good. But I mean, I just try to understand that, I mean, why it is almost mass independent, truly speaking.
Actually, that's right. The spin depends heavily on the mass, inclination, and the distance. So when we were doing this, we were also surprised to see such kind of a trend. So what the value there is 650. That is where it is more or less the minimum it is recording. This is not expected. This is what we got. I, at this point of time, do not have an exact explanation why this has happened. I would love to hear any experts listening to the talk. If they can throw some light, I'll be very happy to take this as a learning opportunity.
Okay.
Honestly, I don't know why that was the case.
Okay, so if anybody has any suggestions, can write personally. to speaker and start conduct the presentation. Anyway, so I don't see any more questions on this part. So if there is no more questions, let's thank Sneha for this presentation. Now over to Shashi. Shashi, are you present?
Thank you for this opportunity. I'll stop sharing my screen.
Yes, yes, please. Shashi? I think he's not present. So we can have a break for tea and also crystal viewing. That's long break, 45 minutes. So we'll assemble again at 16:45 hours. Okay, till then. So please go through the posters presented in the link and see how are they. And then come back. Okay, then. I'll see you at 16:45.
ನನಗೆ ಗೊತ್ತಿರಲಿಲ್ಲ ನಾನು ತುಂಬಾ ಸ್ಲೋ ಅಲ್ಲ ನಂದು ಅಷ್ಟು ಆಗೋದಿಲ್ಲ ಬೇಗ
Neha, you have to mute.
Yes.
No, Sneha was unmuted, so I was just telling her. She was talking something in Kannada.
Hello. So, it's time. So can we start?
Yes, Sachin. Yeah.
Okay. So welcome to the evening session of this conference. So here we have three or four 15-minute talks. We'll start with S. Mallo from Osmania University. So he'll be speaking about inner region of accretion and jet in one jet source and atom source. That's a GX7+2 and 4U 1705 minus 44. So can you please share the slide and start presentation?
Yeah. Hello, sir.
Yeah, sorry. Okay.
Am I audible?
Yes, sir. Can you share a slide?
Yes, I'll be. Yeah, I'm sharing. Is my screen visible right now, sir?
Yes, yes. So go ahead.
Hello.
So because this is a 15-minute talk, so 12 plus 3. So I will warn you up to 10 minutes. Okay.
Yeah.
Yeah.
Sure, sir.
Go ahead.
Right. Thank you, sir. Yeah, thank you. Good evening, everyone. I'm Malu from the Department of Astronomy, Osmania University, Hyderabad. Firstly, I would like to thank the organizers for giving me this opportunity to present my work here today. I'll be talking about understanding the inner region of the accretion disk and jet in the Z source GX17+2 and atoll source 4U1705-44. Mentioned here are my collaborators. I'll begin by briefly giving an introduction into the broad classification of neutron star low mass X-ray binaries that are Z and atoll sources. Z sources trace out a Z-shaped track in the hardness intensity diagram or the color diagram. They are highly X-ray luminous, while atoll sources trace out a C-shaped track in the hardness intensity diagram, and they have a much lower luminosity compared to Z sources. Primarily show three branches: horizontal branch, normal branch, and flaring branch, while atoll sources show two prominent branches called island and banana branch. They have characteristic QPOs associated with each of these branches. The inner disk radius of these sources across luminosities have been found to be within 6 to 20 Rg, approximately 1 to 3 square. This is based on the study by Cackett et al. 2010 and Ludlam et al. 2017, based on reflection spectrum modeling. I'll begin with GX17+2. This is an SCO-X1-like Z source. Properties are as mentioned here. The soft part of the spectrum, which is less than 3 keV, for the source remains less explored. So we achieved that here with the SXT data from AstroSat. Suzaku observations of GX17+2 has been studied by Cackett et al. 2010, and they constrained the inner disk radius to be approximately 1.2 to 1.3 SCO, while new star observations were studied by Ludlam et al. 2017, and they found the inner disk radius ISCO. Interestingly, Pennings et al. 1988 observed that when the source was in HP and in B, there was radio emission associated with the source. And Migler et al. 2007, they performed simultaneous X-ray and radio observation for RXT data, and they found similar results. And they also strongly suggested that NB oscillation could be possibly connected to the presence of a jet. Now, we observed GX17+2 using AstroSat in AO cycle 3 from August 22nd, 2017 to August 24, 2017 for an effective exposure time of 32 kiloseconds. This work was published in MNRAs last year. So given here is the SXT image of the source on the top, and on the right, based on the hardness intensity diagram of the source was found to be in the normal branch. So we divided the normal branch into three portions: the upper A, middle B, and lower C portion, in order to study the evolution of the source along the track. So we performed simultaneous SXT and LAX-PC joint spectral fitting in the energy range 0.8 to 50 keV. The best fit model that was used is mentioned here. So we use the reflection framework. Based on the convolution RD-Blur model, we found Rn to be 7.51 to 8.06 Rg, that is approximately 1.25 to 1.34 ISCO. This value is consistent with that obtained from previous studies, and this BB normalization is also proportional to inner disk radius. Hence, using this BB normalization, we found the effective inner disk radius after using the color correction factor to 11 to 16 kilometers. These values are consistent with that obtained from the reflection framework as well. We found that the inner disk radius is almost stationary along the branch starting from A to C. And power law index was found to be varying from 2.31 to 2.44, indicating that even though the disk is non-variant, it could be the corona or the hard component which is varying, which could be leading to the source traversing along the NB. As was shown previously, the source inner disk radius is found to be close to the ISCO, and because of that, there could be, and the source is emitting close to the Eddington luminosity. Hence, there could be puffing up of the inner disk region. Hence, we determine the radius of this quasi-spherical region using an equation given by Ding et al. 2011, where it is the region radius is proportional to mass accretion rate. Hence, and this radius was found to be 36 to 43 kilometers. Popham and Sunyu 2001 proposed a model wherein the radius of the boundary layer is proportional to mass accretion rate. And we use this equation to estimate the radius of the boundary layer. And for this, the mass accretion rate that was used was obtained from the equation given by Klusniak 1987, as given here. Here, beta is the neutron star angular velocity in Keplerian units. So what they mention is that the boundary layer luminosity is proportional to the disk luminosity. So we plugged in the hot BB component luminosity obtained from the spectral fit, because Barrett et al. 2000 and Popham and Sunyu 2001 suggest that the boundary layer could be responsible for the hot BB component around 7 to 20 kV. So we estimated mass accretion rate and used this to estimate the boundary layer radius, which came out to be 30 to 54 kilometers. Again, by using the hot BB component luminosity, we estimated the height of the boundary layer or the ionizing source above the disk using the equation given by Cackett et al. 2010. And we found this value to be varying from 19 to 23 kilometers. It was interesting to note that all these estimations, all these values, all these radii came out to be approximately in the same range. We also performed energy-dependent CCF study of the source using AstroSat, SXT, and LaxPC data. We first initially performed LaxPC soft versus LaxPC hard light curve CCF study. LaxPC 3 to 5 kV soft light curve and LaxPC 16 to 20 kV, 20 to 40 kV, and 20 to 50 kV hard light curves. And we also performed simultaneous SXT and LaxPC light curve CCF study, soft 0.8 to 2 kV SXT light curve versus LaxPC 10 to 20 kV, 16 to 20 kV, 20 to 40 kV, and 20 to 50 kV. In 3 different sections, we found significant lags. We found 2 anti-correlated hard lags and 1 anti-correlated soft lag. On the bottom, 20 kV LaxPC light curves with the correlated hard lag. While SXT 0.8 to 2 kV and LaxPC 10 to 20 kV light curve is shown in the next panel with the corresponding CCF, which is an anti-correlated soft lag. Here, by hard lag, I mean the hard photons are lagging the soft photons and vice versa for soft lags. Similar studies were performed on the RXT and NewStar satellite data of GX17+2. This work was published in 2019 in RG Supplementary. Interestingly, there was a radio emission associated with the one of the observations in RXT. This work was published by Miglieri et al. In 2007, as shown in the first figure here. We performed corresponding CCF study for this observation ID, and we found that there is an correlated hard lag and an anti-correlated soft lag in the first and last portion of the light curve. Miglieri et al. 2007 and DeSalvo et al. 2002 proposed that the horizontal branch and normal branch are associated with a hard tail and a jet. And we note that CCF lags were detected only in the horizontal branch and normal branch, which could mean that there is a possible association between the detected lags and the presence of a jet. So we obtained few hundred second lags as is shown here near the figure. We also performed a CCF study for new star data. For the first time, we note a hard anti-correlated lag in the new star light curve, 3 to 5 kV versus 16 to 30 kV. We found a lag of 113 seconds for this in this study. Propose that the obtained delays could be a combination of the readjustment timescale of the disk as well as the coronal structure. And based on that, we arrived at an equation for the coronal height, wherein coronal height is proportional to the mass accretion rate as well as a beta factor, where, where beta is the ratio between the coronal readjustment velocity and the disk readjustment velocity. Beta was taken to be 0.1 to 0.5 based on MHD simulations by Manmoto et al. 1997, Penn et al. 2003, and McKinney et al. 2012. So for the lags obtained in AstroSat, LAGS-PC, and SXT data, coronal height was thus estimated to be 27 to 46 km for beta equal to 0.1. And similarly, for RXT and NewStar data, coronal height was constrained to be 20 to 35 km. We also, yes. We also assume that the coronal height could be, if it is equal to the truncated disk radius, then the readjustment velocity of the corona should be zero. Similar work was performed on 4U1705-44. For the first time, using a simultaneous AstroSat SXT and LAGS-PC data, energy-dependent CCF studies were performed. Shown here is the SXT image of the source and the LAGS-PC and SXT light curves. Apart from using our AO cycle 3 observations, we also used LAGS-PC archival data obtained from guarantee time phase observations from March 2 to 5, 2017, which is dataset 2 here. On top panel, we have the light curve from dataset 1, LAGS-PC, and on the bottom panel, we have dataset 2 light curve from LAGS-PC. Based on the hardness intensity diagram, we found that the under review in APNSS. For this, we estimated the coronal height for each segment of the light curve, and we found that for 10 different segments, we are finding lags varying from 64 seconds to 573 seconds. And similar to the previous study, we estimated the coronal height, which came out to be 7 to 77 kilometers approximately. And it was interesting to note that this is in the same range as that which was estimated for the Z source GX17+2. Shown here is a representative CCF with an anti-correlated hard lag. We also performed dynamical CCF study between 3 to 5 kV and 15 to 30 kV LAGS-PC energy bands. And we found that few tens of seconds of lag is noted here as well, which could mean that the corona is readjusting at shorter timescales as well. And apart from that, we also performed LAGS-PC 10 to 20 kV versus SXT 0.8 to 3 kV light curve CCFs. From this study, we found that there is an anti-correlated hard lag of 259 seconds and a correlated soft lag of 38 seconds in two segments. And this resulted in a coronal height of 0.6 to 20 kilometers for beta equal to 0.1. This value is similar to that which was estimated for the boundary layer. Hence, we cannot rule out the possible lags. This work is currently submitted to MNRS. We also performed a spectral study. And based on reflection model, we found that the inner disk radius is at around 14 RG, which is well in agreement with the previous studies by these authors mentioned here. And it is also noted that the inner disk radius is found to be stationary along the branch from A to C. And we also note a hard tail about 25 kV. And DeSalvo et al. 2000 proposed a model wherein this hard tail could be produced by the condensation of seed photons in a relativistic jet. This temperature is found to be similar along the branch, while the hot blackbody component temperature was found to vary from 2.21 kV to 2.04 kV along the branch. And we note that the power law index is, power law flux has increased from the branch from A to C, and varying hot component fluxes and power law indices indicate towards a varying corona or a coronal or a subcapillary flow. And we also note that using the luminosity and mass accretion rate obtained from the spectral field, the boundary radius was constrained to be 14 to 18 kilometers, which is similar, like I mentioned, to the coronal height that was estimated. Now, the source was found to be in the banana state, which would mean that there could be a compact corona present, and the inner disk radius was found to be stationary along the branch, hence it could mean there is a constant influx of disk photons. CCFs show, despite of the CCF show lag, so variations could be occurring only in the corona or the base of the jet. Light curves show decrease in hard flux when hard lag was detected. So this could mean that during the hard lag, the corona is decreasing in size, and vice versa for soft lags. So in a nutshell, the height of the coronal structure estimated from Z and et al. Sources are within the same range, and hence would lead to an understanding that the structural configuration in the inner region of the accretion disk and around the neutron star could not be drastically different for et al. And Z sources. The radius of the boundary layer and coronal structure estimated are within the same range, hence it is also probable that this varying structure causing the lags could be the boundary layer. I would like to conclude by saying that a similar study on various other et al. And Z sources may help in resolving some of the ambiguities concerning the differences between them, and may also help us in understanding the accretion disk coronal geometry. We thank the AstroSat S60 and LAXPC team for providing us with the necessary software and for releasing data via SSDC. I would also like to thank DST Inspire for the financial support. Thank you.
Okay, so you have already exceeded your time, so don't see any questions, and also we don't have time. So we'll move to next lecture by Sriram. Can you please answer your slide? And Sriram, can you please share your slide?
Yeah, Sachin. Thank you, Sachin.
So, Madhu, can you please answer your slide?
Sir? Yeah, sir. Yeah, sure, sir, sure.
Sriram, so you can share your slide.
Yeah.
So as you know, this is 15 minutes talk, 12+3. So after 10 minutes, I'll give you a warning. So please try to be within time. Okay.
Good evening, everybody. I hope you can see my PPT.
Sorry?
I hope you are all audible.
Yes, sir.
I mean, you can hear my voice. Yeah.
Hello. Yeah. Hello. Sriram, we can't hear you.
Yeah, no, we can hear you very clearly, Sriram. Please go ahead.
No, he is not Sriram.
Sriram?
We can't hear you.
Sriram,
we cannot hear you.
Okay. Sachin?
Yeah.
Fine at your end?
No.
No, I can't hear Sriram at all.
You can't hear?
No.
Okay. So I think there is some issue.
Yeah, now I think you can hear me.
Yeah.
Hello, can you hear me now?
Yes, very much.
Hello.
Yes, very much. Please go ahead.
Yes. Okay. So let me quickly start. So I'll be discussing few of my recent works and other works. So I'll be talking about the very rapid transitions which are occurring at the scale of 10 seconds to 100 seconds. The type B and type B or type A QPS are mostly associated with these sudden transition events with varying fluxes in the light curves. Jet phenomena are often found to be associated with the type B QPS, Fender et al. 2004, 2009, Belloni et al. Russell 2019. Rapid flip-flops, first rapid flip-flops in X-ray light curves was captured by Jinga, which was observed in this black hole binary GX339-4, Miyamoto, Mota et al. And Nespoli et al. 2003, and few other black holes. And such transitions, we also studied such transitions in these black holes, XTJ 1859 plus 226, XTJ 1550 minus 564. And generally it has been observed that such transitions are observed at the peak of the outburst. Yeah, so this is Nespoli's work. You can see Nespoli 2003. You can see this is the light curve. Initially there was no QPU or very weak QPO. This is the dynamical PDS. And suddenly there is an appearance of type C QPO. So they told that there is a transition of type B to type C QPO. And radio flux was in the range of 10 to 40 millijansky, Gallo et al. 2004. There was no radio observation exactly not on this date, but there were radio flux detected just plus or minus 2 days around this X-ray emission, around this transition. Yeah, this is one of my work in 2012. This is the source XTJ 1817-330. You can see that there is a steady light curve and suddenly there is a dips in the light curve. And when we extracted the spectra and the power density spectrum in the dip and non-dip section, we can clearly see that there is a change from the type B to type A transition occurred during this time. And this is the location where during the outburst, around the peak of the outburst, notably what we found was that in the dip region, the gamma was very hard, 2.29. And in the non-dip, in the steady region, it was 2.46, slightly softer than the dip part. Similarly, we did this similar studies in XTEJ 1859 plus 226. You can clearly see these are different light curves. In the Q means detection of QPO, NQ means non-detection of QPOs or very broad QPOs. You can see here. Similarly, in this second light curve also, in the last light curve, you can say there is a transition which is of the order of 100 seconds, and you can see very broad feature here. You can't say that it is a QPO, but there is a radio association for the first observation. It was detected around 140 millijansky. For these second two, there was no radio detection. I mean, nobody might have observed, or there is no radio detection. And in the last observation, just 1 day before this observation, there was a radio flare of this magnitude. What we found during our spectral analysis that disk properties are changing, especially the normalization part, not by huge factor, but within 90% confidence level, they are changing. The gamma was not found to vary except the last one where you can see a sharp dip where the gamma varied from 2.40 to 2.27. That means in the dip region, the index was hard. This is for another source, XTJ 1550 minus 564, 2016 work. So here you can see a transition, very smooth, not a very sudden transition, but a smooth transition here of the order of couple of 100 seconds. You can see in the especially in 13 to 60 kV, you can see that in the first region there was a 11 Hertz QPO, and during the transition there is no QPO, and then suddenly it came around 6 Hertz QPO. You can see here pretty clear, yeah. So 6.5 to 13 kV in the middle part. There is a very broad feature, can be classified as type A or maybe broad noise, and suddenly a type C QPOs appeared, and this is 13 to 60, 11 Hertz QPO, then disappeared and then appeared. We found that gamma was very slightly changing, or you can say it's difficult to say. Especially in HXT, you can clearly see that gamma has changed from 2.18 to 2.44 during the transition. Yeah, this is very recent work, and there is a poster also presented by Hari Krishna. Please go through it. So I'm telling very few results, but he has explained in a broad manner. Again, you can see there is a transition so there is a gap between them, but you can see the transition. There is appearance of type B QPO. There is no QPO. Again, here there is a transition from Q to no Q. You can see here, you can clearly see QPOs, whereas very broad feature or no QPOs. Here the harmonic is missing here. There is a change in the centered frequency. Yeah, similarly, again, these are the outburst ASM light curves. You can see around the peaks, you can see these transitions. This is 2003 outburst. This is 2009 outburst. The last one is 2009 outburst. And what we found that all these transitions are basically associated with the type B QPS. We also found that there are transitions which are type C QPS where they disappeared actually. Q to NQ, there is no QPO. There is a QPO here. There is a QPO. This is 6.5 to 13. This is the softer part. This is the harder part PDS. So you can see that in the harder part you can see, but in the softer part there is no QPO again. So there is no QPO in this. So all these transitions are associated with the type C QPOs. So in Hari Krishna poster, he has shown the association with the radio flux also. Yeah, what we found is sometimes there is a change in the disk parameters. Sometimes there is a change in the gamma, for example, power law index, that is 2.50 to 2.32 in one of the last observations. Whereas in, yeah, here also you can say 2.61 to 2.41. So gamma is changing. Sometimes disk parameters are changing. Yeah, you can see here, this is a type C. You can see that there is a KTIN is changed. You can say here KTN has changed, disk temperature has changed. You can see some change in the disk normalization also. Whereas gamma has not significantly changed, especially in this, you can say that there is a change in the gamma here in the one of the C transition, type C QPO transition event. This is one of the nicer result shown by Homan et al. 2020, Maxi J 1820. So the gray shaded region is basically where your type B QPO is present. The red line shows the start of the radio flare, and blue line shows the peak of the radio flare. And before this gray shaded region, there was a type C QPO associated. Okay, so they said there is a presence of type B QPO on the onset of the radio flare, and after 2.3 hours, radio flare was observed very precisely. So you can see that here, the peak is well away from the type B QPO after disappearance of the type B QPO, 2.3 hours. This is one of the best observations for the sudden transition event till now. In Hari Krishna poster also, we found that in 1743, there is a disappearance of QPO, and the radio and X-ray observations are offsetted by around 2 to 3 hours. This is Swift J 1658.2, 4242. Again, you can see this is XMM light curve. This is the new star light curve. You can see there is a sudden transition here. So you can see that during the low state, they found a QPO around 6 Hertz, and in the high state, there is no QPO. What they found is that this temperature is changing. There is like very slight change in the normalization or no change. They have fixed the gamma. Yeah, this is Jitesh work. He's also there. So this is from AstroSat observation, one of the very interesting observation. Again, they found that same source. This is the same source, Swift source. You can see, and high-low flip-flops. These are known as flip-flops. So again, you can see that there is a transition from type C to A QPO. So in the high state, you see type C. In the low state, yeah, the QPO is almost came very broad. And again, what they report is that there is a change in the disk temp. There is a change in the normalization KTNs. Yeah, there is a change in the disk temperature, 1.10 to 1.23. Yeah, left one is for low state and right one is for high state. Yeah, this is under preparation. So we try to study such events in GX339, though Nespoli and other people, Mota et al. Also showed. So we found a few other observation sets where you can see there is a disappearance of QPOs or appearance of QPOs. There is no QPO here. Suddenly there is a type C QPO emerged out. There is a no QPO in the, as the flux is increasing, you found that there is a type C QPO around 6 Hertz. And again, there is a drop, there is no QPO. This particular observation, there is a radio flux was detected just 1 day before this particular, sorry that I have not mentioned MGDs, but 1 day before this observation, radio flux was detected. Again, you see a type C QPO along with a harmonic. What we found is that in these observations, there is no change in the gammas or disk temperature. Only the flux was disk and gamma fluxes were varying. Power law index was varying. These are flip-flop transitions. You can see very rapid flip-flops. These are generally seen in GX339. Also Swift, they have shown it. So in the low, so for the low state and the high state, when we got the PDS in the high state, you can see this is a type B QPO. Sorry, in the low state, we found it's a type B QPO. In the high state, there is a type C QPOs. Similarly for this, not shown the gammas here, but in this particular observation, you can clearly see that there is a gamma. Yeah. Oh, okay. So yeah. So there is a change in the gamma. Yeah. So I conclude that radio flux is associated to the fast transition of type B QPOs. However, we need more observations to prove this. And sudden appearance and disappearance of QPO in the X-ray band in BHPs. Sometimes gamma, that is power law index, is varying, or these properties are changing during the transition. So we don't know it's entirely gamma is responsible or the disk is responsible. Variation of gamma during power law index during flip-flop can be associated to the jet ejection event. As I shown you already, that couple of observation, there is a change in the gamma. So we think that the component cloud is ejected away, and in the low regions we have left behind very strong, but in the temperature wise it's very hot, but size wise it's very small. So the question remains, does jet influence the production mechanism of type B QPOs? So we don't know the answer yet. We need more studies in this. More studies are needed in this direction. Thank you. Thank you all.
Okay, thank you. So one quick question. My question. Anyway, so thanks, Sriram, for the presentation.
Thank you, Sachin. Thank you, Sachin.
Now I'll move to next presentation by Indu K. being here, IIT Indore. We will be talking about jets, big swings, and observations around star black holes. This is the 15-minute talk. So 12 plus 3. So I will be warning after 10 minutes. Okay?
Yes. Yeah.
So the slide and go.
I hope you can see my slides.
Yes. Yes.
Yeah. Hi, I am Indu. First, I would like to thank the organizer of the conference for giving me this opportunity to present my work. This work we have done in this lockdown period with the collaboration of Dr. Bhargav Vaidya and Dr. Christian Fan. Am I audible? So,
yes, you are audible.
Yeah, so title of the talk is the jet D-swing and oscillations around carved black hole. And especially I would like to thank Ranjiv Mishra because he already explained why this kind of study is important. And yeah, in the first day, Amit also explained a bit about the importance of this kind of studies. So as it is discussed by many authors, the astrophysical jets are very common in many astrophysical sources like young star, active galactic nuclei, quasar, gamma ray bursts, those systems which host accretion disks. By definition, it is a collimated beam of matter with very high velocity. The velocity of the jet depends on the central object that is hosting the accretion disk. But what we understand from it that this kind of collimated beam relativistic matter is possible in presence of magnetic field. So the study of GRMSD become essential tools for this kind of studies. A recent observation of EST collaboration there with the polarization map, they have also suggested the presence of magnetic field 1 to 30 Gauss around M87, around the black hole of the M87. So in the last figure, we have shown the very famous image of M87 jet in optical rays. So despite like decades of study and observation, we have huge discrepancies in observational evidence and the theoretical predictions. And especially, we do not know many things like how the jet is launched from the black hole or the accretion disk, how mass loaded onto the jet, or how the jet collimate, or why the jet sign, and etc. etc. There are many open questions. But In this talk, I will be mostly talking about the launching problem of the jet. There are two primary mechanisms which deal with this kind of launching. One is like Blandford-Janaik method, which where the jet is powered by the spin of the black hole, and another is the Blandford-Payne mechanism, where the launching mechanism is magnetocentrifugal acceleration. And this kind of Blandford-Payne mechanism is driven by the rotation of the accretion disk. So interestingly, in this many observation of M87s, they have this Nakamura 2018 plotted the jet radius as a function of distance, the projected distance from the black hole. And what they found that the jet launching radius for M87 is around 5.5 square cell radius, which essentially suggests that the launching mechanism for M87 is probably the Blandford and Janaik mechanism. Whereas similar study on Cygnus A suggests that the jet launching radius is 227 square cell radius, which essentially means that at least some part of the jet is launched due to this kind of Blandford and Payne mechanism. So it is very interesting to study the contribution of Blandford-Janaik and Blandford-Payne mechanism. And in order to do that, we need to solve the GRMSD equations, like mass conservation equation, energy momentum equation, and the Faraday's law. There are many. Although this development of code started lately around 2000 or so, from 2000 or so, but still we have several active GRMSD codes in the community, like HARM, BHAC, Coral, Athena++, ACE-AMR, and the final one is known as Karma. Its name is fancy. And most of these studies done in GRMSD, they use torus setup around black hole, but we want to set up a thin accretion disk around rotating black hole. In order to do that, we use code BHAC, where we set up a thin accretion disk around Car black hole. Earlier, Variolis et al. 2019, they also did similar. They also set up a thin accretion disk and studied the launching of Blandford-Janaik jet using GRMSD code HARM. Their initial setup was based on Beksinski-Witta potential and non-relativistic vertical equilibrium. Whereas for our case, we use the initial condition based on Novikov and Thorne model. And the density profile and the gas pressure profile are presented in panel A and B. And we follow Jenny et al. 2007 to set magnetic field. The vector potential, explicit form of the vector potential is given on the slide. Here, depending on the M parameter, the inclination of field lines, initial field lines are different. The lower value of M implies, here you can see in figure C and D, lower value of M implies inclined magnetic field line and strong colloidal magnetic field line, whereas higher value of M implies more vertical field lines and weaker colloidal component of the magnetic field. And overall, the strength of the magnetic field is set by input plasma beta parameter. So in this slide, we are showing temporal evolution of density profile. Here you can see after the evolution, here in the left figure, the red lines are basically magnetization equal to one contour. So you can see the simulation domain can be divided into three distinct parts. The region which is depicted here with dark blue region is basically the funnel region, where we can find Blandford-Janaik jet, which I will be explaining just after a few probably second. And then we have this equatorial plane, where we see the dense region, which is basically thin accretion disk, and in between we have the disk twin region. So in the right figure, we show the field lines and plot of the vertical velocity. Here we have shown a zoom version of the around the black hole. Here you can see the field lines are rooted into the ergosphere of the black hole, which is a very strong signature of Blandford-Janaik jet. So in order to know more details about this Z and this wind, we plot the density profile along with the field lines in the right figure, in the left figure, and with the contour sigma equal to 1, sigma basically the magnetization, and the minus ACUT equal to 1 contour. And in the left figure, and in the right figure, we plot the galvanic Mach number along with the galvanic Mach number equal to 1 contour by in the black line, and B tor by BP equal to 5 contour. And here we observe that around the funnel region, we observe the ACUT is minus greater than 1. It's always minus ACUT equal to minus greater than 1. Then we observe the Lorentz factor of the order of 10. And in the very near to the black hole, the jet is Blandford-Janaik jet is launched with sub-galvanic velocities, and finally at the far from the black hole, it becomes super galvanic. So which strongly suggests the presence of Blandford-Janaik jet. And then close to the black hole in the Dix-Wick region, we can see that the wind is launched with B tor by BP is greater than equal to 5. And greater than equal to 5, and the flow is super galvanic. So which suggests that the Dix wind around this region is a B tor dominated Dix region, where the launching mechanism is the gradient of toroidal magnetic pressure. Whereas far from the black hole, you can see the equatorial plane is super galvanic, then there is a sub-galvanic region surrounding the this surface, and then it becomes super galvanic, and where the B tor by BP is less than 5, and around the equatorial plane, B tor by BP equal to 1, which suggests that the active Blandford Payne mechanism or the magnetocentrifugal acceleration. So this confirms the presence of BP-driven Dix wind. In this slide, in this slide, we study the inner disk structure. Here we plot the field lines along with the toroidal component of the magnetic field, and here you can see that due to the MRI, the toroidal component changes its sign, and we can see the red island in middle of the blue island, and due to this kind of change in polarization, the magnetic field line can reconnect and form plasmoid. Here you can see, and as it was and plasmoid have many tremendous application in astrophysics. Similarly, in the right figure, we plot the temperature profile. We see that in the B tor dominated Dix wind, where we see the plasmoid and the turbulent motion, the temperature is very high. So it acts as a hot corona around the black hole. So this we call it a Dix wind corona. And then in this slide, we plot the different mass flux rates. So here I will just tell one thing, that due to this, we saw the oscillation in the density profile, density evolution, that inner disk oscillation. We can see the features of the inner disk oscillation in the mass flux rate also. This is the accretion rate in the top panel, and the jet rate, that means the mass flux rate in the funnel region, and the mass flux rate due to the wind. And here we see that lower value of M and lower value of plasma beta always give higher mass flux rate for all these quantities, and they are more prone to oscillations. And from our study, we have drawn a schematic diagram for accretion ejection system, where the central around the region around the central axis is occupied by the Blandford-Janaik jet, and surrounding it we have the B tor dominated Dix wind, which is turbulent and plasmoid, and these things can be found there. And this region is very crucial to save the large scale astrophysical jet, and surrounding that we have the Blandford-Payne Dix wind. And interestingly, this recent polarization map of EHD collaboration, they also support this kind of magnetic field structure around the black hole. So then, using our simulation models, we use this result to rupture code raptor, which is a basically general relativistic ray tracing code, and we calculated the emission mass for this. We use the mass of the black hole to be Sagittarius L star, and we in the left panel we saw the emission map with different viewing angle, and in the right panel we saw the temporal evolution of the emission map with a fixed viewing angle. And using that, we can calculate the variabilities in the flux observed in this kind of system. Of course, for this we are just starting this work, and more study is required to get to know more information about this kind of systems. Yeah, with this I would like to conclude, and thanks.
Okay, thank you, Indu. So any quick questions from this? Yeah, there is a few. Anyway, we can take it. So Pankaj, can you please unmute yourself and
Okay, can you hear me?
Yeah, I can hear.
Yeah, just a clarification. So the plasma beta that you used, is it magnetic field by particle or other way around?
It is the usual plasma beta parameter, the magnetic pressure by gas pressure.
Yeah, okay. And the other thing is that you used Raptor. So it is basically you are doing post-processing, right?
Right, post-processing.
Okay.
So Ranjit, can you please ask?
A quick question. What I wanted to understand is how do you keep the disk thin without having relative cooling?
Exactly. We initial condition is a thin disk, but after some time, we see that most of the matter in the accretion disks are they are going with the wind. Only the equatorial plane, it's that left with kind of thin disk. So this is one of the limitation in our simulation, that we do not have radiative mechanism in our ports. So
the scale height remains small?
Scale height it's always very, very small, because if we simulate it for a very long time, then the scenario will be different. But our interest is to understand the launching mechanism. So we only simulate it only up to certain hundreds of inner ISCO rotation time.
Thank you.
Okay. So Biplab, can you ask yourself? Or?
Yeah. So I wanted to know till which inner disk radius could you find the origin of disk wind? Could you in your simulation find the disk winds originating right up till the ISCO?
This means disk wind.
Yeah.
Yeah, we can see this wind coming up around the ISCO, because after what happened when we start the simulation with the magnetic field, due to the loss of the angular momentum, the flow around the black hole becomes subcapillary, and it start the accretion process. After that, we can see actually this kind of wind from very close to the black hole also.
I see. But the launching of collimated jets won't. Till which squarcial radius could you find the origin of collimated jet?
Okay. The collimated jet, that is basically Blanford-Janaik jet, is always appears from this Argo region of the black hole. And after that, depending on this BTOR dominated disk wind region or the hot disk wind corona, it take its large scale structure.
I see. Okay, thank you.
Okay, thank you, Indu. So we have one last talk of the evening session. Actually, it was somehow missed from scheduling. We are now adjusted here. It will be by Dr. D. Radhika. The title of the talk is Disk Coupling in Stellar Black Hole, a multi-mission view. It's a 15-minute talk, so 12:03, and after 10 minutes I'll give warning. Radhika?
Sure. Am I audible?
Yes.
Is the screen visible?
Yes, yes.
Okay. So I'm going to talk about the disk-jet coupling in stellar mass black hole binaries, and I'm going to present a multi-mission view. And with respect to the title of this workshop, National Perspective, I'll be highlighting some of the national results which probably were not mentioned earlier, or some of them could be a repetition. So major portion of the results are by my research scholar, Atulya, and my collaborator for a decade, Dr. Anuj Nandi, has been there always in the discussion. Well, we started with this particular diagram in the morning. So where you have a compact object at the center, the black hole at the center, then the disk, the pulling of the matter from the companion, and yes, there is some jet ejection happening. So this was explored by several people, especially what was happening within the disk in the X-rays, and then came this kind of general understanding of how the hardness ratio varies with respect to intensity of the source. So you had been seeing this earlier. Interestingly, this was for GX339-4, which unfortunately had very minimal radio observations during its previous two complete outbursts. So we have the hard state where it's a steady jet, and this is where the linear relation between the X-ray luminosity and radioluminosity have been established by Corgel. And for it reaches to a phase of transition over here, that is when the relativistic jets, which are optically thin, ejected out. And once it reaches the substrate, the jet will be quenched. Now, I would like to go back to almost a decade before when I started studying this particular topic. And I started with this particular source, 1859 plus 226. And these are the RST observations. So this is the ASM light curve, and below I have shown the radio. So you can see that for some cases, there were like kind of near simultaneous radio observations showing the flux variations. So there were like 5 flares which we could identify based on the radio observations. And I marked as F11225. But the initial radio observations were continuous, but later it became very sparse. Major highlight, thanks for Mayuk for mentioning one of them in his talk. Major highlight was that, so initially the QPO rises as it is in the hard and hard intermediate state. And when there is a transition to the soft intermediate state, there is suddenly for a few hours when the QPO is not observed, and then it reappears. Similar characteristics continue during the other flares also. Along with that, the power spectra characteristics change, that is the fractional RMS or the total RMS decreases. And also the energy spectra becomes softer, thermal compensation, the compensation component reduces, the flux reduces for the hard component. And for 5 flares, matching with the radio detection, we were able to have understanding. Well, similar results we got when we could identify at this particular situation, something similar happened when there was a QPO, and then again it vanished off. But there was no radio detection here. So this was like a possible detection of a radio flare. Now, this picture also was shown by Mayuk. This was by another source, H1743-322. We also had kind of diagnosed this source. As he mentioned in the morning, so this is 2nd June when the radio flux is very minimal. That is when you have a type C QPO. And this 5th June when the lobe has been already separated, that means ejection has already happened. So there was a time gap, but nevertheless, based on the timing results, Miller-Jones et al. Was able to give a representation of how the matter gets ejected from the nearby innermost portion of the disk. Well, we studied this for almost 8 sources during the period of 2011 to 2016. I would say in several conferences and publications we have presented this. And the common observations are this: QPOs are not present whenever an ejection happens, RMS power decreases, spectra becomes softer. And for most of the sources, it was happening in the soft intermediate state when the transition happened to the SIMS. And unfortunately, not always there was simultaneous X-ray and radio observation. Sometimes there was a delay. And the QPOs does reappear after a few hours or days. Interestingly, for some sources, there has been a partial absence of QPO. So what do I say as partial absence? When I do an energy-dependent study of the power spectra, I see that this particular thing happens only, say, this is in 2 to 5 keV. So in a particular energy band, only it was seen. We generalized this, and it was specified in a paper in 2016, MNRS. Most of the sources which we considered were in this particular region of South Indian state transition, except this 1836 minus 194, which showed these characteristics in the hard intermediate state. It was a failed outburst, but significant radio detection was there, and the radio detection was explained in detail by Russell et al. Also. So, followed it up with B404 Cygni, and we were able to again observe characteristic changes in the spectra, energy spectra. This is new star energy spectra. So we see that the spectra becomes softer when the ejection happened. And B404 Cygni, this particular outburst, it went into multiple ejections in radio, X-ray, and all other bands. And major changes were seen in the spectra, and also in the power spectra, the RMS declined. But yes, this was for the first time when we did not see a QPO before or after. So, and also another point to be noticed was this source was, unlike other transient sources, this never had a proper HID, the proper Q shape. It was so random, the HID was very, very random. In addition, there has been presence of wind detected, and we could study the ion line variation and confirm that one also. So outflows of two kinds were determined in this particular source. So old is obviously always gold. So GRS 1915 plus 105 is what I'm going to talk about in detail. So first discovered in 1992, but the highlight of what we have been talking earlier, Professor Yadav had shown you this particular figure earlier. So that is when these dips occur. This is a beta class we mentioned. So when these X-ray dips occurred and ejection happened, and first peaked in infrared and later in radio. So this came as a Nature publication by Mirabel, and they are studied in detail. But not to forget that we had an Indian X-ray astronomy experiment, the IRS-P3 on board, and so many studies, especially by BCG Paul and group, had happened on this particular GRS 1915 plus 105, and there are so many publications using Indian X-ray astronomy experiment, followed with RXT also. Significant results were seen by RXT. I'm talking about the overall X-ray characteristics, that is the spectra and the rapid timing changes. Now, Fender et al. In 2004, they performed some theoretical explanation, and they said that this is due to the ejection, whatever is happening in IR and radio is due to the synchrotron emission, which is in a jet. And X-ray emission could be a tracer of the accretion flow. Major highlight, yes, going back a bit in years, is Perosi 1999, when he said that whenever there is a plasma which enters a boundary region, where QPO can occur, and something is happening which disturbs this entire system, and kind of temporary disappearance of the QPO, or a temporary disappearance of the inner portion of the disk. So that was for the first time when such understanding came into picture. Now, this is, I would like to highlight the theta class observation. So by two groups, I would say, or one under this name, Sachindra Nayak and A.R. Rao and Santosh Vatavale et al. And so they also said about the soft dips, whenever the soft dips were occurring, and they correlated with the high radio emission. Fender et al. Also reported this. Now, coming to Santosh Vatavale's paper, he talks about how Comptonized component is not present during these soft dips, and how that could, the Comptonized matter is what could be ejected out into the jets, and it is coming out from the innermost region of the accretion disk. Well, so this obviously needed a theoretical support. This was an A&A letter in 2001. So the theoretical support came from this, the magnetized component flow model by Nandi et al., or also called as magnetic rubber band effect. Professor Sanjeev Chakraborty mentioned this in his talk. So we had been hearing about the Keplerian and sub-Keplerian flow, which produces an oscillating shock. And because of this, a region is produced, which they term as symbol, or as this is nothing but the corona, the region of hot electrons. So what if the companion star had a magnetic field? What if it is a late type star and has a magnetic field along with it? And say the magnetic field. Now, obviously, we have the evidence for magnetic field in a black hole by the EHT. So when the magnetic field is present, as the matter is flowing in, the flux tubes also gets amplified, and that collapses catastrophically, pulling out this entire matter in the corona, which gets resulted into jet.
2 minutes.
Okay, I'll be quick. So based on this understanding, we were able to understand, we were able to interpret most of the sources which I mentioned earlier. Coming on to the recent GRS 1915+105, almost 31 observations were there by Astrosat. You can see that this rising phase is similar to a rising phase of a black hole binary. Here also there is a systematic evolution of QPOs, and which all of a sudden there is an absence, transition happening to softer classes. But yes, there is no radio detection mentioned during that. So, but we did find several classes and class transitions which were not reported earlier, and that work is under review in MNRS. My focus is going to be this last stage when the flux almost dropped down, but the source started showing something different. So this is the Ratten 600 radio light curve, and along with that we have put the other radio observation. This is by MALA and this is by Metzgerholm. When the AMALA detected, that is 13th, 16th and 17th May of 2019, there was a continuous increase in the radio flux. Along with that, Astrosat had observed this Jitesh telegram, I would like to refer here, and then Astrosat observed X-ray phase at the same time. Back to following to next observation, which was in June, again a radio detection. There is no Astrosat observation, but we do have others. Then again, coming to the next one was in November, sometime in November, there is again a radio flux, where again we have X-ray observation, but not by Astrosat. Last one was in February 2020. This was the brightest radio flare detected. Unfortunately, not a single X-ray observation is existing. So this is the Astrosat light curve, and we can see this flaring and non-flaring region. So this was the observation on 16th, 15th and 16th. And these are the nicer observations, nicer and near simultaneous observations, which happened a few days after the detection of the major flare by AMALA. So when I come to this, so this is the Astrosat broadband fitting. So you can see, as we said earlier, the non-flaring is what when the flux was low and flaring was when it was higher. You can see the difference in the photon index. There is an increase in the photon index. If I see the power spectra also, that is different. The RMS estimation also shows it to be different. If I consider the follow-up NISA and New Star, which happened on 21st, similar results we do observe there also. So both cases are suggesting of a spectral softening, which has resulted into ejection. Unfortunately, for the 21st, whatever happened here, the follow-up radio observation does not exist. Coming to the June, it was observed by NISA. Once again, a similar result which we are finding. There is a significant change in the spectra and the timing characteristics. And the last one is in November. So nice that NISA and SWIFT had like kind of continuous observation, and we were able to understand the spectral variation and periods. Yeah, I do have mentioned detection of a milliards QPO, which this needs to be confirmed. So this work is still under progress, and we will be completing it soon. So overall, what I want to say is during all these flares, the photon index increases, disk temperature increases, contribution of disk comes into picture, electron temperature decreases. So all these, along with that, RMS decreases. So all these are indications of spectral softening, and which is resulting into ejection of the matter into jets. So here are the salient results. during the radio flare, significant variations are observed in X-ray, and summarizing it for other sources, all these variations which I said. And we also did observe a hard tail in astrosat over here. This hard tail could be due to interaction of matter ejected, whatever got ejected, with the base of the jet. So an IR observation there would have helped. Yeah, I'm almost done. And so all the characters are similar to what was seen earlier in the source. Just one highlight is that we are now seeing these characteristics not, I mean, it's not just the beta or theta classes. You can see it even when there is no such class variabilities. And more broadband observations, especially continuous observation, is required. AstroSat has been helpful to an extent. NICER is helpful now. And in the future, the broadband mission proposed by URSC ISRO should be useful. And thanks to ISRO, Respond for the funding. Thanks to SB Pandey and Girish for considering a request for participation at the last moment. And a shout out to my other collaborators, Dr. Samir Mandal, Vivek Agarwal, and Sachindra Naik. Thank you.
Okay, so thanks, Viveka. So any quick questions on the presentation?
Yes.
No questions? It's like that. Anyway, so I thank all the speakers for this afternoon session to keep on time, all the presentation on time. So thank you, everybody. Now I hand over to
yeah, I think if participants are not too tired, and if there is still something is remaining, we can of course continue our discussions because there is a mention about the discussion session, and there is a separate Slack channel where posters are also there. So interested participants may like to visit the Slack channel as well. And since subject experts are already there, I would suggest to extend discussions towards what we thought earlier, that how in the present circumstances that we are very rich with existing facilities and now upcoming one, how the microquasar and X-ray binaries field could be explored better. So along those lines, I would request Professor Ranjiv Misra and all other senior participants to extend discussions for further 10 minutes or so. So Sachin, it seems that people are really tired, and it's evening time. Everybody has things to do. So if no more questions or no more plans for further discussions, then I would say that again for participants may like to go to Slack channel and look at posters and so on. And Sachin, if there is nothing extra, then I think we should adjourn today's session. Is that fine? Sachin? Hello?
The poster should be there till the end of the conference, right?
Yes, Slack channel is there. So if no more discussions, then I again extend my sincere thanks to all the participants since morning first half session, and then Sudeep Bhattacharya and then Sachin Naik for chairing the sessions, and all participants who actively participated, delivered their lectures, and participated actively during this very lively session. Thank you all, and see you tomorrow when we will be talking about Indian existing facilities, where eminent speakers would be speaking about Indian existing facilities, and that what are the major results. So bye for now.
Okay, thank you, Suti. Bye.
Bye.